are interactions identified only by sign, for positive effect and for negative effect. The mathematical procedures are given in Levins. The technical problems associated with identifying the appropriate graph are not relevant to its use here, which is to demonstrate that community structure determines what happens in communities and that these qualitative results do not depend on the fine details of population-level interactions but only on a few many-to-one qualitative properties. This particular approach deals with systems in a moving equilibrium. More recent work shows that many but not all the results can be extended to more general situations and that even where the particular results are different, the relevant result that the response depends on community structure still holds. Experimental verification of some of the predictions of this analysis was provided in the recent experiments of Bryant and Macaulay. The graphs of Fig 6.1 show some hypothetical communities of a few species. Table 6.1 shows the direction of change in each variable when some parameter change enters the system in such a way as to increase the growth rate of the variable shown in the first column. Model A is a simple nutrient/consumer system. Any increase in the input of nutrient to the system is completely taken up by the consumer, but a change in conditions affecting the survival of A. 1. Affects A and N in opposite directions, generating a negative correlation between them. In Model B, A. 1 is density dependent in some way other than by consumption of N. Now changes in N are absorbed by both N and A. 1 in the same direction. The correlation between N and A. 1 depends on the relative magnitudes of variation entering from above and from below. In Model C, A. 1 is consumed by H. Now, A. no longer responds to changes in N. The changes are passed on to H. Once again we observe that change from below generates positive correlation. Model D introduces a second, inedible consumer. A. 2 picks up all the effect of changing the input of N, leaving A. 1 and H relatively insensitive. Fig 6.1 Graph representation of community structure. In Model E, the second consumer, A. 2, also inhibits the growth of A. 1. The effect of this change in graph structure is seen only in the impacts on H of variation entering the system via N. 1 or H. Finally, Model F introduces a second nutrient, consumed only by A. 2. This alters the responses of N. 1 to parameters entering the system at N. 1 or H, and introduces ambiguities into the responses of H. Table 6.1 The direction of response A. of community variables to parameter changes entering the system at different nodes. An examination of the graph models and of the consequences of parameter change derived from them in Table 6.1 shows the following. 1. The response of a species to the direct impact of the external environment depends on the way that species fits into the community. The response of species A. 1 to direct inputs or changes in N. 1 in models A and B is different from its response in all other graphs, and H responds in opposite ways to the same physical impact in model C and A. 2. Some species respond to changes arising almost anywhere in the system while A. 1 is insensitive to most inputs, responding only to changes arising in H wherever H is present. This might be misinterpreted as insensitivity to the environment or to resource changes, or it might be taken as evidence of lack of competition with A. 2. But this occurs really because H plays the role of a sink that absorbs impacts reaching A. 1 from elsewhere. 3. Some species affect most other variables in the community, whereas changes entering through A. 1 are observed only in changes in H. Thus the graph analysis supports the observation that one or two species may dominate the community, but gives a completely different explanation from one that focuses on that species alone. For a change in the structure of the community may be detectable not at the point of change but elsewhere. The difference between models D and E is only in the A. 2. A. 1 link, but the effects are seen only in the response of H to changes entering at H or N. 1. 5. Under model F in the table we see that changes in parameters produce correlated responses in the variables of the system, and we see that the same pair of variables may have positive or negative correlations, depending on where the variation enters the system. 6. Parameter changes may be the result of natural selection. In general, the response to selection is to increase a parameter having a positive input to a variable, since that parameter increases within population Mendelian fitness. But this positive input may have positive, 0, or negative effects on population size. Population genetics alone does not determine the demographic response to selection. But since population size does affect the numbers of migrants sent out to colonize new sites, there is a discontinuity between population genetic and biogeographic processes that can be bridged only by specifying community structure. 7. The notion of a species being of critical importance or dominant has at least 3 different meanings. H may be the major, or only a minor, cause of death of A. 1. N. 2. May be the main food for A. 2. Or only a supplement. That in itself does not determine whether A. 1 responds to changes in H, or whether A. 2 responds to changes in N. 2. Nor does it answer the question of whether a species is critical to the structure in the sense that, for example, the addition of N. 2 in model F changes the response of N. 1 to its own parameters and to A. 2. 8. The graph analysis opens up new possibilities for research strategy. In model F it indicates where measurements are needed to resolve ambiguities. Consequences of parameter change that are concordant across models are robust results insensitive to details of the models. Where different models give different results we are directed to the critical observation for deciding among them. This dialectical approach to the ecological community allows for greater richness than the reductionist view. It permits us to work with the relative autonomy and reciprocal interaction of systems on different levels, shows the inseparability of physical environment and biotic factors and the origins of correlations among variables, and makes use of and interprets both the many-to-one relations that allow for generalization and the one-to-many relations that impose randomness and variation. Where particular techniques are unsatisfactory, the remedy is likely to be not a retreat from complexity to reductionist strategies but a further enrichment of the theory of complex systems. Abstraction and idealism. One form of reductionist materialism regards abstractions as a form of idealism, so materialism in science necessarily overthrows abstractions and replaces them with some sort of real entities, each of which is then unique because of the immense complexity of interacting forces on each and because of the underlying stochasticity of nature. It is obvious, however, that we cannot eliminate all abstractions, or else nothing would remain but chronicles of events. If any causal explanations are to be given, except in the trivial sense that a historically antecedent state is said to be the cause of later ones, then some degree of abstraction is indispensable. There can be no predictability or manipulation of the world except by grouping events into classes, and this grouping in turn means ignoring the unique properties of events and abstracting the events. We can hardly have a serious discussion of a science without abstraction. What makes science materialist is that the process of abstraction is explicit and recognized as historically contingent within the science. Abstraction becomes destructive when the abstract is reified and when the historical process of abstraction is forgotten, so that the abstract descriptions are taken for descriptions of the actual objects. The level of abstraction appropriate in a given science at a given time is a historical issue. No ball rolling on an inclined plane behaves like an ideal Newtonian body, but that in no way diminishes the degree of understanding and control of the physical world we have acquired from Newtonian physics. Newton was perfectly conscious of the process of abstraction and idealization he had undertaken. He wrote in the De Motu Corporum, "Every body perseveres in its state of rest, or of uniform motion in a right line, unless is it compelled to change that state by forces impressed thereon." Yet he pointed out immediately that even the great bodies of the planets and comets have such perturbing forces impressed upon them, and that no body perseveres indefinitely in its motion. On the other hand, the properties of falling bodies that have been abstracted away are replaced when necessary. Newton himself, in later sections of the Principia, considered friction and other such forces. Landing a space capsule on the moon requires the physics of Newtonian ideal bodies moving in vacuums for only part of its operation. Other parts require an understanding of friction, hydrodynamics, and aerodynamics in real fluid media, and finally, correction rockets, computers, and human minds are needed to cope with the idiosyncrasies of actual events. A space capsule could not land on the moon without Newtonian abstractions, nor could it land with them alone. The problem for science is to understand the proper domain of explanation of each abstraction rather than become its prisoner. Darwin's and Mendel's works, although great triumphs of materialist explanation in biology, are filled with abstractions. Abstraction is not itself idealist. The error of idealism is the belief that the ideals are unchanging and unchangeable essences that enter into actual relationships with each other in the real world. Ideals are abstractions that have been transformed by fetishism and reification into realities with an independent ontological status. Moreover, idealism sees the relationships entered into by the ordinary objects of observation as direct causal consequences, albeit disturbed by other forces, of the actual relations between the essences. Marx, in discussing the fetishism of commodities in Chapter 1 of Capital, draws a parallel with the mist-enveloped regions of the religious world. In that world the productions of the human brain appear as independent beings endowed with life, and entering into relations both with one another and the human race. In a similar way, idealistic, pre-Darwinian biology saw the actual organisms and their ontogenetic histories as causal consequences of real relations among ideal, essential types. This was opposed to the materialistic view, which saw the actual physical relations as occurring between actual physical objects, with any types as mental constructs, as abstractions from actuality. The precise difficulty of pre-Darwinian evolutionary theory was that it could not reconcile the actual histories of living organisms, especially their secular change, with the idea that these histories were the causal consequences of relationships among unchanging essences. The equivalent in Newtonian physics would have been to suppose that if a body departed from perfectly rectilinear, unaccelerated motion, there nevertheless remained an entity, the ideal body, that continued in its ideal path and to which the actual body was tied in some causal way. The patent absurdity of this view of moving bodies should make clear the contradictory position in which pre-Darwinian evolutionists found themselves. In ecology, the isolated community is an abstraction in that no real collection of species exists that interacts solely with its own members and that receives no propagules from outside. But to be useful as an analytic tool, the idea of community does not require that a group of species be totally isolated from all interactions with other species. Confusion on this point may arise from a failure to appreciate that general principles of interaction are not the same as quantitative expressions of these interactions. It is undoubtedly true that every body in the universe creates a gravitational field that, in theory, interacts with every other one. Yet when we get up in the morning, our muscles and nerves do not have to compensate for the motion of every body in the universe or even of every other person at the same house. The intensity of gravitational interaction is so weak that except for extraordinarily massive objects like planets or extraordinarily close objects like nucleons, it is irrelevant, and we can treat our own persons as gravitationally independent of each other. In like manner, all species in the biosphere interact, but the actual matrix of interaction coefficients is essentially decomposable into a large number of submatrices almost completely separated by zeros. The problem for the ecologist is not to replace these zeros by infinitesimally small actual numbers, but to find the boundaries of the submatrices and to try to understand the rather large interaction coefficients that exist within them. Thus it is not an argument against population or community as entities that the boundaries between them are not absolute, just as the existence of some intersexes does not destroy the usefulness in biology of distinguishing males and females. To put the matter succinctly, what distinguishes abstractions from ideals is that abstractions are epistemological consequences of the attempt to order and predict real phenomena, while ideals are regarded as ontologically prior to their manifestation in objects. Stochasticity and statistics. A major trend in ecology and evolutionary biology has been the replacement of deterministic models by stochastic ones, but this has not been the general trend in biology, nor should it be. Stochasticity is not the negation of cause and effect, and stochastic models are not in essential contradiction to predictive models. As a historical fact, the entire development of molecular biology shows the continuing power of simple deterministic models of the Bet machine, and there is not the slightest reason to introduce stochasticity into models of, say, the effect of an increase in adrenaline secretion on the concentration of sugar in the blood. Indeed, stochasticity may be an obfuscation rather than a clarification in such cases. The neurosecretory system is a complex network of nonlinear dynamic relations that are incompletely understood. If two individuals are given identical treatments of a hormone, there may be qualitatively different and even opposite consequences. That is because in such a nonlinear system, the consequences of a perturbation in one variable are strongly dependent on the levels of the other constituents. The lack of repeatability of response could be passed off as the consequence of stochasticity, but to do so would be to prevent progress in understanding and controlling the system. The example of Park's experiments on competition in flower beetles is right to the point. In mixed populations of Tribalium confusum and T. castaneum, sometimes one species was replaced, sometimes the other. Conditions of food, moisture, and so on were made as nearly identical as possible, and the initial population mixtures were also controlled. Niemann, Park, and Scott constructed a stochastic model of this competitive experiment that was consistent with the variable outcome. But in constructing such a stochastic model, which seems untestable, they rejected an alternative that would lead directly to experiment and measurement. This alternative is that there are two stable states of dynamic systems, one at pure Tribalium castaneum, and one at pure T. confusum, and that the domains of attraction of these stable states are demarcated by a separatrix along an axis that has not been controlled in the initial population mix, so the experiments begin sometimes on one side of the separatrix, sometimes on the other. Park did not examine, for example, the effect of small perturbations in the initial age distribution within species, or in the initial actual fecundities of the samples of beetles in each vial. It may indeed be true that notions of cause and effect are inapplicable at the level of the spontaneous disintegration of a radioactive nucleus, but there is no reason to make uncertainty an ontological property of all phenomena. The question of whether non-predictability of outcome is to be subsumed under a general stochasticity or whether previously uncontrolled variables are to be controlled in an attempt to produce predictable outcomes must be decided for each case. If we wish to understand the changes in gene frequency in a population, it may be quite sufficient to invoke the chance nature of Mendelian segregation and the Poisson distribution of the number of offspring from families in a finite population of size n. Such a stochastic explanation is a sufficient alternative to a theory of perfect adaptation by natural selection. It is an explanation at the same level of phenomena as the adaptive story. On the other hand, if we are interested in the consequences of human demographic change, the probability distribution of family sizes is not a sufficient level of analysis, and we must look into the differentiation of family size by region, class, and other factors. The demand that all phenomena must be explicable by deterministic cause and effect, at an arbitrary level of explanation, is clearly doomed to failure, as shown by the attempt to explain all evolutionary change as the result of determinative natural selection. But the assertion that cause and effect at a lower level cannot replace the stochasticity at higher levels, if it becomes useful to do so, is obfuscatory. Moreover, the shift from stochastic to deterministic statements about the world can be made in changing from one level of explanation to another in either direction. Not only can the apparently random be explained as a result of deterministic forces in higher dimensionality with more specification, but a reduction in dimensionality by averaging also converts stochasticity into determination. The stochasticity of molecular movements in a gas lies at the basis of the completely deterministic gas laws that relate temperature, pressure, and volume. Even if the disintegration of a radioactive nucleus is an uncaused event and thus perfectly stochastic, clocks accurate to millionths of a second are built precisely on the basis of the randomness of those disintegrations. Thus stochastic processes may be the basis of deterministic processes, and deterministic the basis of stochastic. They do not exclude each other. Stochastic and deterministic processes interact also at the same level of organization of phenomena, and this interaction is of a special importance in population biology and evolution. The notion of determinism may carry with it the false implication that only a single end state is possible for a process if all of the parameters of the dynamic system are fixed. But this is not true. Because of the nonlinear dynamics of evolutionary processes, there exist multiple possible outcomes for a process even with fixed parameters. In mathematical terms, the vector field has multiple attractors, each surrounded by a domain of attraction. Which endpoint the process actually reaches depends upon the system's initial domain of attraction. Thus the same force of natural selection may cause a population to evolve in different directions, depending upon the initial genetic composition of the population. If in addition to the deterministic force of natural selection, there are random variations in genetic composition from generation to generation because of finite population size and random migration, a population in one domain of attraction may be pushed into another domain and thus may achieve a final state different from what was predicted on the basis of its previous trajectory. Indeed, a good deal of evolution by natural selection is made possible only by stochastic events, because these events allow a population that has been restricted to a domain of attraction in the genotypic space to evolve into other compositions. The synthetic theory of evolution developed by Wright is based upon this exploration of the field of possible evolutionary outcomes by the interaction of stochastic and deterministic forces, both operating at the level of genotypic composition. Again we see that the apparent contradiction between stochastic and deterministic is resolved in their interaction. It is tempting to think that the widespread use of statistical concepts in biology is somehow a step away from idealism and toward materialism. After all, statistical method takes as its material for analysis the real variation among objects. Yet nothing could be further from the truth. Some of the great problems of scientific explanation come from concepts and practices that lie at the heart of modern statistics, which is, in many ways, the embodiment of idealism, at least as practiced by natural and social scientists. In the first place, Statistics does not take variation as its object of study, on the contrary it consists largely of techniques for reducing, discounting, or separating noise so that real effects can be seen. The theory of hypothesis testing and most of the theory of estimation have as their primary purpose the detection of true differences between objects or the assignment of intervals in which parameters of universes are thought to lie. In spite of variation between individuals, while statements about differences or parameters must of necessity be phrased in terms of probabilities, that is regarded as a limitation, not a virtue, by statistical theory. The reason for searching for efficient estimators and uniformly most powerful tests is precisely to minimize the effect of variation between individuals on the desired inferences about ideal universes. The distinction between first and second moments is absolutely fundamental to statistical theory, and the purpose of statistical procedures is to distinguish that fraction of the difference between first moments which is ontologically the same as the second moment from that fraction which arises from different causes, the real differences between the populations. Most aspects of the theory of experimental design, such as randomization, orthogonal plots, and stratification, are substitutes for complete knowledge and control of all relevant variables. The purpose is not to study the error variance but to tame it and minimize it and finally to remove, if possible, the veil of obscurity it interposes between the observer and those ideal universes whose parameters are the object of study. The branches of statistics that seem at first glance to be concerned most directly with variance as an object of study, the analysis of variance and multivariate correlation and regression theory, are, as practiced by natural and social scientists, if not by sophisticated statisticians, the most mystified by idealism. The analysis of variance is a tautological partitioning of total variance among observations into main effects and interactions of various orders. But as every professional statistician knows, the partitioning does not separate causes except where there is no interaction. Yet natural and social scientists persist in reifying the main effect and interaction variances that are calculated, converting them into measures of separate causes and static interactions of causes. Moreover, they act as if main effects were really main causes in the everyday English meaning of the word and as if interactions were really secondary in importance. In this view, interaction is nothing but what is left over after main effects are accounted for. This attitude toward main effects and interactions is a form of the caeteris paribus assumption that plays such a central role in all Cartesian science, but it has become an unconscious part of the ideology of the analysis of variance. The most egregious examples of reification are in the use of multiple correlation and regression and of various forms of factor and principal components analysis by social scientists. Economists, sociologists, and especially psychologists believe that correlations between transformed orthogonal variables are a revelation of the real structure of the world. Biologists are apparently unaware that in constructing the correlation analysis itself they impose a model on the world. Their assumption is that they are approaching the data in a theory-free manner and that data will speak to them through the correlation analysis. If, however, we examine the actual relationship between dynamic systems and correlations, it becomes clear that correlation can create relationships that do not exist. For example, the simplest prey-predator relations predict that as prey increase there will be a consequent increase in predators, so the correlation between prey and predator should be positive. However, as predators increase, all other things being equal, prey should decrease, so there will be a negative correlation in abundance. The spiral nature of the dynamics in the two-dimensional prey-predator space shows us immediately that prey and predator abundances may be either positively or negatively correlated depending upon where in the spiral the populations are historically. The graphic argument shows that the observed pattern of correlation in a system depends on the structure of the system and on the point of entry into that system of parameter changes. Two additional aspects of correlation appear when we examine the time course of a process. Suppose that N is some species that consumes resource R and grows at a rate that depends on its capture of resource and its own mortality, where P is a rate of capture and utilization of R. And theta is the death rate. Or some other function. We do assume for convenience here that theta is constant, so changes in the system enter by way of R. The particular equation describing the dynamics of R is surprisingly irrelevant to the results, which follow. We make use of the fact that the average value of a derivative over some time interval t is. Applying this to the equation for n, we have, where the bar indicates average value and COV is the covariance. Now divide the original equation by n. The left-hand side is so. Substituting this term into the equation above, we have, or, if n has been changing exponentially over this interval, and so COV equals 0. But if n changes rapidly at first and then slows down, n is greater than n/lambda t, and the covariance is negative, whereas if n changes more slowly than exponential and then accelerates, n is smaller and the covariance is positive. But over a very long time the covariance will disappear. The outcome of this analysis is that the correlation between a pair of variables, even in the simplest ecosystems, depends, first of all, on the rest of the structure of the system, second, on the variable at which the external source of variation enters the system, third, on the history of the system, and finally, on the duration of observation. Therefore, no observed correlation pattern between physical conditions and biological variables can refute the view of a mutual determination of species in ecosystems, even when physical measurements alone can give good predictions of abundance or change. If an a-theoretic correlation analysis is carried out, a correlation will be observed and, in the absence of any a priori theory, the correlation will lead to a theoretical story that reflects the particular sign the correlation has in that set of data. Thus, correlations may be the consequence of causal processes, but they cannot be used reliably to infer those processes. Because the methodology of correlation is intrinsically without theoretical content about the real world, any statements about the real world must come from the content imported into the analysis. So if we wish to understand the causes of some variable, say species abundance, by using a correlational approach, it becomes necessary to decide which aspects of the world are to be measured to correlate with species abundance. After the independent variates are chosen, the correlations that are calculated come to be interpreted as real causal connections. So if temperature turns out to be highly correlated with abundance, it will be asserted that temperature itself is an important causal factor, as if the data rather than the observer had chosen this variable. Of course, every investigator will repeat endlessly that correlation should not be confused with causation, and that in the example given temperature may be only a proxy for some other variable or variables with which it is in turn correlated. But such a disclaimer is disingenuous. No one would bother to carry out a correlation analysis if they took seriously the caveat that correlations are not causations. After all, what is the use of the analysis except to make inferences about causation? Unfortunately, in a collection of multivariate data in which the set of independent variables accounts for a reasonable proportion of the variance, it is nearly always the case that a rather large proportion of that variance will be associated with a small proportion of the variables. This loading of the variance onto a small set of variables is a purely numerical consequence of assembling a heterogeneous group of independent variates in a multiple regression analysis. Because of this loading, one or two variates will always appear to be the main dependent variable. Yet if the analysis is repeated with a different set of variables, some other may appear as the main cause. In this way, the practice of multivariate analysis is self-reinforcing, since it appears from the analysis that a few real main causes have been discovered, and so faith in the methodology is built. When extrinsic variables are not introduced specifically as explanatory factors, a complex set of data may be examined internally for a pattern or structure whose discovery is thought to be a revelation about the real world. In fact, it is only a tautological relationship among a set of numbers. The most famous example is the G-factor created in the factor analytic treatment of IQ tests, which is widely believed by psychologists to be a real thing, general intelligence. Statistical methodology in the hands of natural and social scientists thus becomes the most powerful form of reinforcing praxis, of which idealism is the theory. Biology above the level of the individual organism, population ecology and genetics, community ecology, biogeography, and evolution requires studying intrinsically complex systems, but the dominant philosophies of Western science have proved to be inadequate for the study of complexity for three reasons. First, the reductionist myth of simplicity leads its advocates to isolate parts as completely as possible and to study these parts. It underestimates the importance of interactions in theory, and its recommendations for practice are typically thwarted by the power of indirect and unanticipated causes rather than by error in the detailed description of their own objects of study. Second, reductionism ignores properties of complex wholes and thus sees the effects of these properties only as noise. This randomness is elevated into an ontological principle that leads to the blocking of investigation and the reification of statistics, so that data reduction and statistical prediction often pass for explanation. Third, the faith in the atomistic nature of the world makes the allocation of relative weights to separate causes the main object of science, making it more difficult to study the nature of interconnectedness. Where simple behaviors emerge out of complex interactions, reductionism takes that simplicity to deny the complexity. Where the behavior is bewilderingly complex, it reifies its own confusion into a denial of regularity. Both the internal theoretical needs of ecology and the social demands that it inform our planned interactions with nature require making the understanding of complexity the central problem. Ecology must cope with interdependence and relative autonomy, with similarity and difference, with the general and the particular, with chance and necessity, with equilibrium and change, with continuity and discontinuity, with contradictory processes. It must become increasingly self-conscious of its own philosophy, and that philosophy will be effective to the extent that it becomes not only materialist but dialectical. 3. Science as a social product and the social product of science. 7. The problem of Lysenkoism. This chapter was first published in The Radicalization of Science. Edited by H. Rose and S. Rose, pages 32 to 64. T. He Lysenkoist movement, which agitated Soviet biology and agriculture for more than 20 years and which remains attractive to segments of the left outside the Soviet Union today, was a phenomenon of vastly greater complexity than has been ordinarily perceived. Lysenkoism cannot be understood simply as the result of the machinations of an opportunist careerist operating in an authoritarian and capricious political system, a view held not only by Western commentators but by liberal reformers within the Soviet Union. It was not just an affair, nor the rise and fall of a single individual's influence, as might be supposed from the titles of the books by Jorovsky and Medvedev. Nor, on the other hand, can the Lysenko movement be regarded, as it is by some ultra-left Maoists, as a triumph of the application of dialectical method to a scientific problem, an intellectual triumph that is being suppressed by the bourgeois West and by Soviet revisionism. None of these views corresponds to a valid theory of historical causation. None recognizes that Lysenkoism, like all non-trivial historical phenomena, results from a conjunction of ideological, material, and political circumstances and is at the same time the cause of important changes in those circumstances. The bourgeois commentators' view of the Lysenkoist movement is not particularly surprising, for it is entirely within their tradition that a major historical change can be the result of individual decision and the caprice of a powerful person or of a unique historical accident, with no special causal relationship. Thus Jorovsky, whose book calls attention to a great many of the complex forces that contributed to the Lysenkoist movement, nevertheless explains its rise as essentially the consequence of bossism, in which the political bosses of Soviet agriculture, including the supreme boss, Stalin, embraced an incorrect scientific doctrine in a blind and capricious flailing about for solutions to Soviet agricultural problems, problems created by their own irrational program of collectivization. It is rather more surprising that socialist writers, who are supposed to know better, are equally narrow in their understanding. The liberal reformers, like Medvedev, view Lysenkoism as a boil-on-the-body politic, a manifestation of the Stalinist infection that is poisoning a potentially healthy revolutionary organism. Some Maoists restrict their view to the philosophical aspects of the problem, using Mao's essay on contradiction in an attempt to prove, as L.K. Present claimed, that Mendelian genetics is incompatible with the principles of dialectical materialism and that a rigorous application of dialectical method will lead to Lamarckist conclusions. We must reject both of these viewpoints as too narrow. Of course, it is true that authoritarian political structures in the Soviet Union and the bureaucratization of the Communist Party had a powerful effect on the history of the Lysenkoist movement. Of course, it is the case that the methods and conclusions of science contain deep ideological commitments that must be re-examined. But other factors in the material and social conditions of the Soviet Union were also integral to the Lysenko movement. The Lysenko movement, from the 1930s to the 1960s in the USSR, was an attempt at a scientific revolution. It developed in the following contexts: the pressing needs of Soviet agriculture, which made the society receptive to radical proposals, the survival of both Lamarckian and non-academic horticultural traditions, on which it drew for intellectual content, a social setting of high literacy and the popularization of science, which made the genetics debate a public debate, an incipient cultural revolution, which pitted exuberant communist youth against an elitist academy, and a belief in the relevance of philosophical and political issues which put the discussion in the broadest terms. But the movement also took place in the context of the encirclement of the USSR, the Second World War, and the Cold War. Administrative repressiveness and philosophical dogmatism increased, opportunists jumped on bandwagons, and the Cultural Revolution was aborted. In the end, the Lysenkoist revolution was a failure. It did not result in a radical breakthrough in agricultural productivity. Far from overthrowing traditional genetics and creating a new science, it cut short the pioneering work of Soviet genetics and set it back a generation. Its own contribution to contemporary biology was negligible. It failed to establish the case for the necessity of dialectical materialism in natural science. In the West, Lysenkoism was interpreted merely as another example of the self-defeating blindness of communism, but in the Soviet Union and Eastern Europe it is still a fresh and painful memory. For Soviet liberals, it is a classic warning of the dangers of bureaucratic and ideological distortions of science, part of their case for an apolitical technocracy. Our interest in re-examining the Lysenkoist movement is several-fold. First, the interpretation of scientific movements in terms of their social, political, and material context, rather than in idiosyncratic terms, is a major task of intellectual history. More than other fields of historical research, science is steeped in notions of accident and personal achievement as the motivating forces of its history. A materialist history of science is still to be developed, despite the pioneering work of Hessen and Bernal. The Lysenkoist movement is recent and well documented, yet the major scientific differences between Lysenkoists and geneticists have been resolved by developments in genetics. Therefore, the problem has the advantage of being contemporary and yet belonging to the past. Second, the Lysenko controversy raised important issues about the general methodology of science and the relationship of scientific method to the requirements of practical application. These issues remain open. We have in mind particularly the standard techniques of statistical analysis and the requirement of a control for experiments, both of which were challenged by the Lysenkoists. Third, as working scientists in the field of evolutionary genetics and ecology, we have been attempting with some success to guide our own research by a conscious application of Marxist philosophy. We therefore cannot accept the view that philosophy must be excluded from science, and we deplore the anti-ideological technocratic ideology of Soviet liberals. At the same time, we cannot dismiss the obviously pernicious use of philosophy by Lysenko and his supporters as simply an aberration, a misapplication, or a distortion dating from an era that is often brushed aside with the label of cult of the personality. Nor is it sufficient to note that despite Lysenko, Marxism has had signal successes, including its pioneering work in the origin of life. Unless Marxism examines its failures, they will be repeated. In its last years, Lysenkoism was a caricature of the two camps' view of the world, in which the confrontation of bourgeois and socialist science was seen as parallel to the confrontation of imperialism and socialism. Its absurdities could easily lead to a denial by critics of Lysenko that there are two camps, a viewpoint that stresses the common ground of all science in a neutral, technical rationality independent of its uses. It seems likely that the reduction of armed conflict will strengthen this neutral view of science at a time when, we believe, the conflict within science must be made sharper and recognized as more complex. This review is, among other things, part of our own process of self-clarification. The philosophical and scientific claims of Lysenkoism. The main thrust of Lysenkoist research was the directed transformation of plant varieties by means of environmental manipulation and grafting. This work directly contradicted Mendelian genetics. A second line of work emphasized physiological processes which, although not formally incompatible with Mendelian genetics, were certainly alien to its spirit and thus were ignored by geneticists. Some examples of Lysenkoist studies, showing the range of work, are V. R. Katrinsky, on the possibility of directing the segregation of the hybrid progeny of wheat, G. I. Lashik, changes in the dominance of alkaloid characters in interspecific hybrids of Nicotiana. Sysakian's work on the transmission of enzymatic activity by grafting, Turbin's study in which a multiple recessive tomato was pollinated with a mixture of pollen types, each carrying a single dominant and gave some offspring with two dominant phenotypes, Avakian's use of foreign pollen to overcome self-sterility in rye, Olshansky's work on the effect of conditions in the F1 generation on the segregation ratio in the F2. Isayev's claim that the offspring of graft hybrids sometimes show the same kind of segregation met with in ordinary sexual crosses, and Glushchenko's book on vegetative hybridization. The main theoretical structure of Lysenkoism is: 1. Heredity is a physiological process, a result of the whole lifetime of interaction between organism and environment. 2. The organism's assimilation of environmental conditions takes place in accordance with its own heredity. Suitable aspects of environment are selected and transformed, unsuitable aspects are excluded. In the course of the organism's development, the heredity program unwinds like a spring, at the same time winding the spring for the next generation. 3. If the environment is suitable for the normal expression of the organism's heredity, that heredity is reproduced in the reproductive cells. If the environment does not permit the normal expression, it also alters the processes producing the heredity of the next generation. 4. The factors that destabilize heredity and permit its modification are: a. Altered physical environment, as in vernalization. b. Grafting, especially at very early stages of development, with the removal of leaves making the graft dependent on its graft partner. c. Hybridization. 5. The organism's assimilation of nutrients and of the external environment is dominated by its heredity pattern. But in sexual reproduction, each gamete is the environment of the other. Thus fertilization is the mutual assimilation of different heredities. The result is especially labile and subject to environmental influence. 6. The same cause that produces an altered heredity or new varieties, the exposure to a pattern of environment that cannot be assimilated in accordance with the old heredity, is also responsible for the origin of new species. Thus speciation is not a population phenomenon but an expression of individual developmental physiology. This is in keeping with the older Lamarckian view. By and large, the Soviet philosophers sided with Lysenko, whose general approach seemed more plausible from the viewpoint of their interpretation of dialectical materialism. The major philosophical issue was the Lysenkoist claim that the gene theory was metaphysical and the gene a mystical entity. From the earliest days of Mendelian genetics, major biology textbooks in Europe and North America made such statements as germplasm, the continuously living substance of an organism. It is capable of reproducing both itself and the somatoplasm, or body tissue, in giving rise to new individuals. It is the substance, or essence, of life which is neither formed afresh, generation after generation, nor created nor developed when sexual maturity is reached, but is present all the time as the potentiality of the individual before birth and after death, as well as during that period we term life between these two events. The somatoplasm, on the other hand, has no such power. It can produce only its kind, the ephemeral, the perishable body or husk, which sooner or later completes its life cycle, dies and disintegrates. The germplasm, barring accident, is in a sense immortal. Geneticists brushed off such statements as extreme views, but Lysenkoists regarded them as extreme only in frankness and clarity and in no way contradictory to the mood of modern genetics of the 1930s. Geneticists responded that textbooks did not reflect the real thinking of the working geneticists, that they obviously recognized the material nature of the gene, that otherwise they could not hit it with radiation or try to find its molecular nature. However, in order to qualify as a material entity, something more is required than that something be an object or a target for X-rays. It must evolve, develop, enter into reciprocal interactions with its surroundings. Genetics in the 1930s largely ignored these issues. Weismann's theory postulated an immortal germplasm that could be reshuffled but could not be either created or destroyed. The later mapping of the chromosome and the study of recombination reinforced the idea that genetic differences among organisms can arise without altering the genetic material at all. And throughout the period of the debate, genetics did not consider the question of the origin or evolution of the gene. Therefore Weismannian germplasm was, in its essence, anti-evolutionary. It allowed change, but only as the surface phenomenon, the resortment of unchanging entities. The Lysenkoist philosophers counterposed the Weismann-Morgan-Mendel school to Darwinism. And their more politically minded colleagues pointed out that scientific theories which deny the reality of change are generally associated with loyalty to the political status quo. Thus the metaphysical gene theory was also reactionary. Mutations are, of course, changes in genes, but they are accidents or external and not part of the normal development of matter. The rigidity of the gene concept was reinforced when the question of the origin of life was taken up seriously outside of communist circles and was often reduced to the question of the origin of the gene. The relation between genotype and phenotype in genetics is a one-sided one, in which genes determine phenotype but there is no reciprocal influence. Further, determine is simply an evasion of what really happens in development. In the textbooks and in the practice of most geneticists, genetic determination carried with it an aura of fate. The role of environment in the determination of phenotype was of course acknowledged, but in a subordinate way. The genes determine the potential, the environment its realization. The genotype is the size of the bucket, the phenotype is how much of it is filled. Statistical techniques around the notion of heritability attempted to partition phenotype into hereditary and environmental components, but still as separable entities. Among Lysenko's adversaries, Schmalhausen in the USSR and Dobzhansky in the United States were almost alone in emphasizing a more sophisticated view of genotype-environment interaction, in which the genotype was the norm of reaction to the environment. The subsequent development of the whole field of adaptive strategy was derived from their approach. The one-way relation between gene and environment also emphasized the contradiction in genetics that all cells are supposed to have the same genes, even though they produce different tissues. Western science as a whole is structuralist. That is, processes are seen as the epiphenomena of structures. Heredity implies an organ of heredity, memory implies an organ of memory, or engram, language implies an archetypal capacity for language. In contrast, Lysenko's dialecticians emphasized process as prior to structure and saw structure as the transitory appearance of process. To them it was as absurd to look for the organ of heredity as it was to look for the organ of life. Heredity is a dynamic process in which various structures may be involved. The model for the process of heredity is metabolism, the exchange and transformation of substances between organism and environment. Ideas of chance play an important role in two aspects of genetics. First, the laws of Mendel and Morgan are couched in terms of probability. Given the genotype of the parents, it is not possible to predict the genotype of an offspring exactly, but only to describe the distribution of genotypes in a hypothetical, infinitely large, ensemble of offspring. Some genotypes can be excluded, but in general there is no certainty about which of the possible genotypes an offspring will have. For characters of size, shape, behavior, and so on, this uncertainty is further compounded by the variable relationship between genotype and phenotype. Second, mutation is said to be random, by which is meant that mutagenic agents, like X-rays, do not produce a single kind of mutational change in every treated individual, but rather a variety of possible mutations with different frequencies. The same uncertainty exists with respect to so-called spontaneous mutations, which appear unpredictably in individuals and are of many different types. For Lysenkoists, these notions of chance seemed anti-materialist, for they appeared to postulate effects without causes. If there is really a material connection between a mutagenic agent and the mutation it causes, then, in principle, individual mutations must be predictable, and the geneticists' claim of unpredictability is simply an expression of their ignorance. To propose that chance is an ontological property of events is anathema to Marxist philosophy. The response of most geneticists, and certainly those of the 1930s, was that the unpredictability in genetic theory was epistemological only. That is, geneticists agreed that there was an unbroken causal chain between parent and offspring and between mutagen and mutation, but the causal events were at a microscopic or molecular level not accessible in practice to observation and not interesting to the geneticist anyway. They contended that for all practical purposes mutations and segregations were chance events. More recently, geneticists have invoked principles of quantum mechanics to make the stronger claim that the uncertainty of mutation is an ontological uncertainty as well, and here they come into direct conflict with the whole trend of Marxist philosophy. That issue, however, far transcends questions of genetics. The conditions creating Lysenkoism. Medvedev's and Jorovsky's books clearly show how dogmatism, authoritarianism, and abuse of state power helped propagate and sustain an erroneous doctrine and even established its primacy for a time. But a theory of bossism is not sufficient to explain the rise of a movement with wide support nor to explain its form and context. A number of streams converged to give rise to and sustain the Lysenko movement. These were, the material conditions of agricultural production in the Soviet Union, the problems of agricultural experimentation under those conditions, the state of genetic theory and practice in the 1930s, the ideological and social implications drawn from Mendelism, including the eugenics movement, the response of the peasants to the collectivization program beginning in 1929, the class origins of agronomists and academic scientists in the decades after the revolution and the strong cultural revolutionary movement toward popularization of scientific understanding and activity, and the growing xenophobia of the 1930s. Conditions of agriculture. There can be no understanding of Lysenkoism that does not begin with the hard facts of climate and soil in the Soviet Union. Since it is usual both within and without the Soviet Union to compare Soviet and American agricultural production, it is illuminating to make the same comparison of geography. Nearly all of the USSR lies above the latitude of St. Paul, Minnesota, so its general temperature regime is more like that of Western Canada than of the United States. The growing season in the most productive belt, the Chernozem, is short, and the contrast between summer and winter temperatures is extreme, as compared with Western Canada and the United States. Table 7.1 makes the point clearly, showing the dramatic increase in continentality of the climate as one goes from west to east in Europe and Asia along the 50th parallel. Although the population of the Soviet Union is one-third larger than that of the United States, the total harvestable acreage per year is the same, about 360 million acres. The rich black Chernozem soils of the USSR, equivalent to the Great Plains and prairies of the United States and Canada, are in a narrow east-west belt from the Ukraine in the west, passing just north of the Black Sea, to Akmolensk in the east, running roughly along the 50th parallel. South of this Chernozem belt rainfall is 10 inches or less per year and so is much too arid for normal agriculture. North of the Chernozem belt rainfall is 16 to 28 inches per year, quite adequate for agriculture, but the soil is poor, the growing season short, and the winter frosts very severe, so neither winter wheat nor spring wheat is favored. The general problem for farmers in this region is to plant late enough to avoid killing frosts, yet early enough to get a full growing season. The Chernozem belt itself, which is the chief agricultural region of the Soviet Union, lies in a band of marginal rainfall, 10 to 20 inches per year, with frequent droughts that result in catastrophic crop failures. In contrast, the black soil belt of the United States runs north to south in the Great Plains, spans a broad range of temperature regimes, mostly milder than in the USSR, and receives 15 to 25 inches of rain per year, reaching 30 inches in the easternmost sections. In addition, a large central section of the United States, just east of the plains, has 30 to 40 inches of rain, soils 3 to 10 feet deep, a long and mild growing season with summer nights that do not fall below 55 degrees Fahrenheit, that is ideal for maize. This corn belt, which is the basis for meat production, is completely absent in the USSR. Table 7.1 Climatic factors in various agricultural regions. City. Number of frost-free days. Difference between warmest and coldest month. Utrecht, Netherlands. 196. 16.4. Berlin, Germany. 193. 19.3. Kiev, USSR. 172. 25.3. Kharkov, USSR. 161. 28.3. Saratov, USSR. 151. 30.6. Orenburg, USSR. 147. 37.4. Akmolensk, USSR. 129. 37.3. Irkutsk, USSR. 95. 38.1. Pierre, South Dakota. 161. 32.6. Hutchinson, Kansas. 182. 27.8. Ames, Iowa. 159. 30.4. Source. KHW Clauses. Ecological Crop Geography. Lysenko's rejection of hybrid corn and his insistence on the use of locally adapted varieties usually is offered as a prime example of the counterproductive effects of his unscientific theories, while Khrushchev is praised for adopting American hybrid corn breeding. Yet hybrid corn has not been a success in the Soviet Union, precisely because there is no corn belt. In the United States outside of the corn belt, in areas that are more marginal for maize, locally adapted varieties commonly outperform hybrids. These generally poor conditions in the Soviet Union are similar for other crops. Cotton, which in the United States is chiefly produced in the moist warm regions of the southeast by dry farming, must be irrigated at considerable expense in the Soviet Union, since warm temperatures are accompanied there by semi-aridity. The most striking example of the deleterious effect of environment on a staple crop is sugar beets, the standard sugar source in Europe. In Germany and France, with high summer rainfall, yields in the mid-1930s were about 13 tons per acre, of which 34% was sugar content. In the USSR, With dry hot summers, yields were 4 tons per acre, with a sugar content of only 27%. Another problem of Soviet agriculture is that much of the arable land cannot be cropped annually, and it cannot be planted with high-yielding varieties, which remove moisture and nutrients from the soil at a high rate. For example, 45 million acres in Kazakhstan can be cropped only every second or third year. Soviet agriculture must then be more extensive and less intensive than American, both in space and time, although both are non-intensive in comparison with most European practice, for different reasons. Soviet agriculture is extensive because of the generally severe conditions of climate and soil, while the Americans have sufficient favorable climate and land to make intensive agriculture unnecessary and unprofitable. The figures in Table 7.2 for important food crops, taken from the 1930 to 1935 data, show the intensive agriculture of Western Europe in sharp contrast to American and Russian practice. The yields for the USSR are overestimates by perhaps as much as 20% because in most cases they were estimated in the field rather than actually measured after harvest. Table 7.2 Yields of some major crops for the United States and Europe, 1930 to 1935. In general, Soviet agriculture is carried out in conditions that are not only marginal on the average, but of much greater temporal uncertainty and variation. Catastrophes because of drought or severe winter frost occur quite regularly. 2 successive years of drought in 1920 and 1921, coming hard on the heels of the Civil War, caused a catastrophic famine in which more than 1 million people perished. Again, 1924 was a very severe year, and grain supplies were reduced by 20%. This variability and unreliability of temperature and rainfall and the imminent possibility of agricultural catastrophe must be regarded as the leading element driving Soviet farm policy. In regions of poor summer rainfall, seed planted in the spring may not achieve sufficient growth before the dry season. For some crops, notably wheat, a winter variety has been developed. The seeds are planted and begin to grow in the fall, overwinter as very young seedlings, and then start to grow again immediately in the spring, thus achieving a longer total growing season. Winter varieties, however, are subject to catastrophic loss if the winter is unduly severe. Vernalization is a process of chilling and wetting the seeds of winter varieties, then planting them in the spring. The seeds complete their growth cycle without the hazard of severe winter conditions. The question remains open whether the advance in growth over normal spring varieties in fact results in increased yield. Vernalization was known in the 19th century, but Lysenko adopted it and expanded its use to a whole variety of crops and situations. It is no accident that the first wholesale trials of vernalization were carried out after the 2 severe winters of 1927-28 and 1928-29, in which 32 million acres of winter wheat were lost in the extraordinary cold. Problems of experiment and evaluation. The normal American method of testing crop plant varieties is to plant a number of varieties for several years at several locations and choose those varieties with the highest average yield over locations and years, paying some attention to variation between years and locations when the average yields are very close. The underlying model is of normal variation around a mean, the coefficient of variation being fairly low, so any sequence of a few years averaged over a few localities will not deviate greatly from any other sequence. This is, in fact, the model that underlies all normal statistical analysis of experimental science. Events are assumed to be regular and drawn from a homogeneous distribution. But real weather behaves differently. Generally, a sequence of normal years is punctuated at uncertain intervals by one or more severe crashes. While years and locations can be averaged, the value of such averages as predictors is poor, because the coefficients of variation are so high. An analogy from ordinary experimental science makes the distinction clearer. When a new experimental technique is worked out, there is a period during which the experimenter has such poor control over experimental conditions that some replications of the experiment will be clearly deviant and not regarded as part of the normal experimental variation. Not until the experimenter has his system under sufficient control to avoid these deviant cases will he begin to accumulate data to test some hypothesis. The decision that the system has passed from the initial uncontrolled stage of heterogeneous results to the stage of controlled variation is made impressionistically and represents a change in the underlying model of the universe with which he is dealing. In the first stage, averages over all experiments are not appropriate and, if he were forced to characterize the results, he would do some culling, averaging only the normal replications, which represent the potential of the experiment. This is precisely the procedure followed by the Lysenkoists, and by Soviet agriculture authorities even before the Lysenkoist movement, when they reported yields per acre. Obviously, such a culling procedure can be and has been used for self-serving purposes, since there is no objective way to decide which cases are deviant and which are normal. That this pathological model played into the hands of unscrupulous manipulation or was unconsciously used by wishful thinkers cannot be doubted. But the conventional statistician's scornful demand that all the data be averaged in an objective way will not serve either. The immense variations in results make the averages meaningless as predictors. Lysenkoist recommendations had such wide appeal precisely because they were intended to cope with extreme environments. Vernalization, for example, was designed to avoid winter killing of wheat, and sowing in the mud, or super-early sowing, was designed to give plants a very early start against the summer droughts by planting seeds in unplowed fields just after the snow melted. It is revealing that the report on vernalization of a 1931 drought conference carried a warning against drawing hasty negative conclusions from possible individual failures because particular failures are possible, indeed unavoidable. As in every experimental search for new pathways. Apparently it was the hope of the conferees that these experimental pathways would soon come under sufficient control to avoid the particular failures. Normal procedures of variety testing and normal statistical evaluation, giving equal weight to all observations, could not have been carried out successfully in the conditions of Soviet agriculture of the 1930s because the level of agricultural technology and husbandry was too low to buffer against the extremes of climatic variation. It is not certain that even today, conventional plant breeding and evaluation techniques could be successful. What is required is some objective method of dealing with the uncertainties. Perhaps the concepts of maximin and maximax solutions to the game against a capricious nature could be used, although the irony would be great, since game theory is a unique development of bourgeois economics. The state of genetic theory. The Lamarckian theory, that characteristics acquired by the organism as a response to the environment during its lifetime may be transmitted to its offspring, had never really been refuted so much as it had been abandoned with the development of modern genetics. The textbook refutation of Lamarck was the work of Weismann. In Weismann's classical experiment with mice, removal of the tail over successive generations failed to produce mice with shorter tails. However, this was in fact irrelevant to the Lamarckian hypothesis, which never claimed that mutilations were heritable. Lamarck's claim was that active adaptive responses are transmitted to the offspring, and in support of this there was an impressive body of experimental data. Among the classical Lamarckian experiments were those of Geyer, who found eye defects in the offspring of rabbits injected with corneal antibodies, the work of Jollos on the transmission of heat resistance and other traits induced by heat treatment in Drosophila, Cunningham's arguments on the evolution of the hive bee, and McDougall's behavioral experiments. In plants, Daniel studied graft hybridization, and Lesage adapted cress to particular conditions and claimed the transmission of the adaptation over 6 or more generations. Bali, working with flax in North Dakota, claimed to induce disease resistance which is transmitted. About 1939, Aister described experiments in growing corn in different parts of the United States. The kernels showed different color patterns, and under California conditions more of the color changes extended into the germplasm and this became genetic. Reynolds claimed that feeding thyroid extract to flower beetles had a greater effect on the next generation than on the animals fed the thyroid. Weismann's argument was not based merely on his negative experimental results. Prior to the rediscovery of Mendel's laws, he had already formulated the distinction between germplasm and somatoplasm and had argued that inheritance of acquired characters was impossible because of the anatomical separation of the somatoplasm and germplasm early in development. Reviewing the embryological argument, Beryl and Lew concluded, there is little doubt that he read into his observations ideas that were in a sense already in the air. But it is primarily on the basis of strict recapitulation that Weismann propounded the migration of the primordial germ cells, to which he so stubbornly adhered that he seemed to have defended it to the extent of disregarding the truth. His interpretation of the germ cell origin of Corinne serves to illustrate how far imagination can be pushed to suit a preconceived idea. The weight of authority, however, of the Weismann-Nussbaum combination convinced many later workers of the existence of facts they could not observe. A special form, one with a long pre-Lysenko history, of the inheritance of acquired characters is graft hybridization, in which grafted plants acquire and supposedly transmit some of the characteristics of their graft partner. Grafting is most effective if done at an early stage of development. Thus techniques such as transplanting plant embryos to the stored seed nutrient endosperm of other varieties or producing genetically different endosperm by using mixtures of pollen provide the most favorable conditions for vegetative hybridization. The equivalent process in animals is the use of mixed sperm that penetrate the chicken egg without actually fertilizing the nucleus, metabolize for a while and serve as an internal mentor or guide to development. Bailey discussed the uses of graftage in plant propagation and added, there are certain cases, however, in which the scion seems to partake of the nature of the stock, and others in which the stock partakes of the nature of the scion. There are recorded instances of a distinct change in the flavor of fruit when the scion is put upon stock which bears fruit of a very different character. The researches of Daniel show that the stock may have a specific influence on the scion, and that the resulting may be hereditary in the seedlings. Thus when Lysenko and his followers began to put forward claims of directing hereditary change in the 1930s, Lamarckism was not a dead relic dredged up from the past. Although it had been rejected almost universally by geneticists, it was still very much alive in paleontology and horticulture and had an extensive literature of experimental results that had never been adequately refuted. Geneticists were largely unaware of, or indifferent to, the Lamarckian tradition. They regarded it as a carryover from prescientific folk science. Insofar as they confronted Lamarckism at all, they rejected it out of hand because the organisms used were not well characterized, the characteristics supposedly modified were not the clear-cut phenotypes of fruit fly mutants, and the research reports were especially deficient in statistical sophistication. Geneticists assumed that Lamarckian results could be explained by hidden selection processes. In any case, the impressive successes of Mendelian genetics and the chromosome theory made it simply unnecessary to consider the vague allusions to physiological interactions in explanation of dubious claims by not quite respectable authors. Meanwhile, genetics itself was changing, and some of the new phenomena were difficult to assimilate. There were the dower modifications, changes induced in lower organisms that were transmitted in diminishing degree over as many as 20 generations. New kinds of material and extrachromosomal inheritance were being described. Hereditary particles outside the nucleus were postulated. And hints were given as to the special role of the nucleic acids in heredity. The Lysenkoists watched this literature very closely. For them, the ad hoc hypothesis and ignored data presaged the final fall of the gene theory. The contrasting reactions of geneticists and Lysenkoists to the Griffith experiments show how two opposing paradigms can each emerge reinforced from the same experience. A number of different strains of the pneumococcus bacteria exist which can be distinguished by their virulence or non-virulence and by whether the outer capsule is present or absent. Griffith found that live pneumococcus of one variety acquired some of the characteristics of dead bacteria of another strain injected into the same host animal. From the point of view of genetics, this was an important step in the identification of the genetic material as nucleic acid. From the Lysenkoist point of view, the heredity of one strain of bacteria was transformed by exposure to a specific environment, namely killed bacteria of the other strain. This transformation was therefore by definition the inheritance of an acquired character, and the experiment was widely quoted by Lysenkoists. The important point is that they were formally correct, and that for them this formal precision completely obscured the scientific significance of the experiments. This same approach characterized the Lysenkoists' treatment of the other anomalies of genetics and cytology. Mendelian genetics asserts that the nucleus controls heredity, but the so-called plasmagons refuted this. Chromosomes were supposed to be linear arrays of genes, but the best microphotographs of chromosomes showed a distinctly nonlinear structure, with thousands of loops coming off the chromosomes in a so-called lamp brush structure. All of the scientific possibilities opened up by newly discovered phenomena were obscured by a legalistic "is this or is it not the inheritance of acquired characters? Does this or does it not show extranuclear inheritance? Is genetic change directable or not?" Ideological and social implications of genetics. It is essential to distinguish between what we might call the minimal theoretical structure of a science, which is dependent upon unspoken ideological assumptions, and a kind of ideological superstructure that is built upon the minimal structure but is not logically entailed by it. For Mendelian genetics, the minimal structure includes the laws of Mendel and the Weismannian principle that the material substance whose behavior is formally described by the Mendelian laws cannot be altered in a directed and adapted way by information from the environment, but that the phenotype of an organism is the outcome of the biosynthetic activities of genes in a particular sequence of external and internal conditions. The ideological superstructure that has been laid on this theory by various geneticists includes notions of the limits set to the phenotype by the genetic potential, the notion that what is inherited is somehow fixed and unchangeable, that organisms are determined by their genes. By acting as if this ideological superstructure were, in fact, the substance of genetics, geneticists invite a misplaced quarrel with the minimal structure itself. Zavadovsky foresaw the inevitable attack on Mendelian genetics that was being invited by biological and genetic determinism, and he understood the pernicious eugenic elitism that geneticists were reading into their science. He warned against the extreme environmentalist counter-reaction that would attempt to destroy all of genetics in order to assert the plasticity and perfectibility of human society. He was the first, as far as we know, to point out that Lamarckism was anti-progressive, since it implied that centuries of degradation and brutalization of workers and peasants had made them genetically inferior. In the mid-1920s, most Soviet and Western geneticists propagated an elitist and racist eugenic ideology. Koltsov and Filipchenko, among others, discussed the possibilities of breeding superior types from the ranks of the intelligentsia as well as from those members of the lower classes who had been in the vanguard of the revolution. Eugenicists also claimed that the genetically best elements in the population were being outbred by the worst and that this trend might grow worse with population control. This kind of naive genetic determinism of human behavior naturally invited ideological attack. The treatment of the gene merely as a cipher, a bookkeeping device, uncoupled genetics from physiology. Thus Bateson explained the Mendelian view to the New York Horticultural Congress roughly as follows: the organism is a collection of traits. We can pull out yellowness and plug in greenness, pull out tallness and plug in dwarfness. This uncoupling, so attractive to geneticists and to Anglo-American analytical reductionists, was offensive to Lysenko's group, which saw heredity as a special case of physiology. Mendelian genetics, which made the possibilities of artificial selection depend on the fortunate occurrence of useful genes. A small minority of the mutants imposed limits to the progress of plant breeding that were socially unacceptable to Soviet agriculture because of its needs. On the other hand, a model in which the creation of hereditary variation proceeded at the same pace as its selection promised unlimited progress, once physiological knowledge was sufficiently sophisticated. The traits used by Mendelian genetics to develop and argue its theory are clear-cut mutants in Drosophila and a few other organisms. These mutants are a special kind of variant and are usually inviable in nature. They were chosen for their unvarying expression so that they could be followed easily, while the complicated processes of variable expression so common to adaptive, quantitative, and agronomically important traits were ignored. Many of the mutants and chromosomal abnormalities were artificially induced by radiation at dosages so far beyond those that occur in nature as to make it appear that Mendelian genetics dealt with a special class of laboratory phenomena but could not, in principle, deal with problems such as adapting fruit trees to the far north. The reaction of the peasants to collectivization. Unlike the Chinese Revolution, which had a strong political base among the peasants, the Bolshevik Revolution could not count on a political and revolutionary peasantry, even though 80% of the population was rural. Thus, while Chinese agriculture rapidly passed from cooperative to collective chiefly by persuasion and local voluntarism, the Russian peasantry, steeped in a petit bourgeois notion of eventual individual land ownership and encouraged in that concept by the market economy of the new economic policy, was totally unprepared for the collectivization required by a rational socialist economy. For the Russian and Ukrainian peasant, collectivization meant appropriation of the land and agricultural products by the urban population. It was all the same to the peasant whether the product of his labor was taken by a landlord or by a revolutionary government. For all, it was not his revolution. The pressing demand to feed the urban working population forced collectivization to proceed much faster than the political state of the countryside could support. When the wholesale collectivization of agriculture began in 1928, before the long and difficult task of revolutionizing the peasants was accomplished, it was met by forceful resistance and sabotage. Agricultural production was wrecked by the plowing under of crops, refusal to sow and harvest, the wholesale slaughter of livestock, and attacks on agricultural officials. This force was met with greater and more terrible force by the state, which eventually won the day for collectivization but at a great cost in lives, material wealth, and political development. Crop yields in 1929-30 were 15 to 20% below the pre-collectivization figures and much further below the optimistic projections of the first 5-year plan. Hostile writers like Jorovsky and Jasny laid the blame for these losses on the collectivization program rather than on the peasants' use of force and sabotage to protect their private property. This point of view blinded these authors to the reality of the wrecking and sabotage that characterized Soviet agriculture at the end of the 1920s and in the 1930s. It was entirely reasonable for the agricultural officials to believe the charges of wrecking leveled by Lysenkoists against their opponents as an explanation of the failure of proposed methods. An atmosphere of hostility and distrust, grounded in bitter experience, permeated the relations between the state agricultural organs and the mass of farmers. Here we come to another aspect of the normal-abnormal model of production discussed in relation to climate. The very real sabotage of agricultural production led to suspicion that instances of failure of Maturinist methods, which, after all, showed striking successes in some years and some localities, must be the result of abnormal conditions created by the willful resistance of saboteurs among the farmers and agricultural scientists. Class origins of scientists and agronomists. The government's and parties' suspicion of the more academic pure scientists, including most of the geneticists, arose in part from their actual histories. Most of the senior scientists of 1930 had been members of the intellectual middle classes of pre-evolutionary Russia. Many had favored the February Revolution but had strongly opposed the Bolsheviks. Men like Vavilov, who was enthusiastic about the socialist revolution from its early days and who displayed great enthusiasm for the possibilities of science and agriculture in the new society, were the exception. Nevertheless, most of the agricultural specialists and scientists were kept on in responsible positions because the state seemed to have no choice. Not only in science, but in all branches of technology and management, unsympathetic managers and technicians had to be employed in socialist enterprises if a complete breakdown was to be avoided. The Soviet authorities were conscious of the difficulties in such pre-evolutionary holdovers. In contrast, Lysenko represented the Russian equivalent of the horseback plant breeder, who came from peasant origins and received the bulk of his technical training after the revolution. Over and over again the polemic of Lysenkoist and anti-Lysenkoist contrasted the priests of aristocratic and lily-fingered science with the mujik's son who was illiterate and ungrammatical. This contest between the effete middle-class intellectuals and the close-to-the-soil practical agronomists was subtly extended to include a conflict between theory and practice, a vulgarization of Marxism. In every aspect the conflict in agriculture was a revolutionary conflict, posing the detached, elite, theoretical, pure scientific, educated values of the old middle classes against the engaged, enthusiastic, practical, applied, self-taught values of the new holders of power. That is why Lysenkoism was an attempt at a cultural revolution and not simply an affair. One element of the cultural revolution was terror. Jorovsky, after a thorough analysis, concluded that, any way one searches it, the public record simply will not support the common belief that the apparatus of terror consciously and consistently worked with the Lysenkoites to promote their cause. He pointed out that the general class divisions between geneticists and Lysenkoists would, in any event, result in more geneticists than Lysenkoists suffering under a revolutionary terror. While that is undoubtedly true, the existence of a revolutionary terror, the preponderance of Lysenkoists among state officials, and the occasional veiled suggestions by Lysenkoists that they did have access to the organs of terror would have been quite sufficient to inhibit the overt activities of geneticists. Speculations on the way the revolutionary terror might have operated if there had been no historical and class divisions between Lysenkoists and geneticists really miss the point that the struggle was, in large part, a class conflict. A dispute among plant breeders and geneticists does not invariably become a national cause célèbre. However, under Soviet conditions of the 1930s, it quickly became a public issue. One of the early achievements of the Soviet regime was mass publishing. Long before paperbacks became a lucrative business. In the United States, the USSR was publishing world classics, scientific works, poetry, and political tracts in cheap editions of tens or hundreds of thousands. The ubiquity of bookstores is a striking feature of socialist cities the world over. Within this general literacy, science played a special role. There was widespread consciousness of the Soviet Union's relative backwardness and of the urgency of rapid technological advance through science. The development of the academies of science of the non-Russian republics was considered a major step in liquidating the cultural vestiges of Tsarist colonialism in Central Asia and the Caucasus. This interest in science merged with the older, traditional socialist belief that scientific understanding can help change the world for the better. That belief made evolution and cosmology, at least, a part of the general liberal education of socialist workers, and before that it had led Engels to write essays on mathematics, tidal friction, human evolution, and cosmology. The Soviet cultural interest in science was especially excited by the broadest large-scale theories. Vernadsky's concept of the biosphere, Sukakev's biocenosis, which attempted to treat whole systems, such as forests, Vasily Williams' soil science, which treated the soil as a living system in coevolution with its vegetation and with agricultural practice, Oparin's opening up of the origin of life, and Pavlov's exploration of the organization of behavior were both intellectually exciting and aesthetically appealing. The general alertness to and interest in science was heightened by the special practical concern with agriculture and the food supply. Here Lysenko had a decided advantage. He was on the offensive, promising advances where geneticists advocated caution. He mobilized large numbers of farmer innovators, whose exploits in plots on collective farms were publicized along with those of the Stakhanovite innovators in industry. The excitement of bold, sweeping theories, popular inventiveness, the rejection of academic elitist stodginess in the face of novelty, and defiance of the received wisdom created an exuberant cockiness, as Stalin had described it some years earlier in his pamphlet Dizzy with Success. The exultation in the achievements of the early years of the revolution led to a sense of omnipotence, of daring to do the impossible, of intolerance toward doubters, which Stalin was able to perceive, describe, and denounce, though he could not quite resist it. Xenophobia. The established academic authority distrusted by Lysenkoists included both Soviet and foreign geneticists. This feeling was originally part of the iconoclastic exuberance and anti-elitism shared by other sections of the society. But as political and philosophic issues became more prominent in the debate, foreign science was increasingly seen as hostile, as part of the capitalist encirclement. On the naive assumption of a simple one-to-one relation between someone's views in genetics and his or her general political outlook, the Lysenkoists used the anti-Soviet or racist attitudes of foreign geneticists to discredit their science. Sympathy with those scientific views was increasingly assumed to imply sympathy with foreign politics as well, and any close intellectual ties of Soviet and foreign scientists justified suspicions of disloyalty. Within a short time the healthy demand for Soviet intellectual independence was converted into a grotesque xenophobia. Through this route Lysenko's opponents were subject to political suppression, the most notorious episode being the arrest of Nikolai I. Vavilov in August 1940. Vavilov, a pioneer in plant genetics and the evolution of cultivated plants, was seized while on a field trip in the western Ukraine and charged with wrecking activities. The particulars included belonging to a rightist conspiracy, spying for England, leadership in the Labour Peasant Party, sabotage in agriculture, and links with anti-Soviet émigrés. He was sentenced to death by a military court, and although this was later commuted to 10 years imprisonment, Vavilov died in prison in 1943. From the point of view of the Lysenkoists, the charges of disloyalty removed their leading opponents and silenced other critics, but from the viewpoint of the police apparatus, the victim's scientific views and international contacts were merely evidence of anti-Soviet activities. Intellectual wrecking deliberately wrong decisions made for the purpose of sabotage was a respectable accusation in the Soviet Union. In the early 1930s several British engineers were convicted, apparently justly, of sabotaging some of the projects of the first five-year plan. Later, in the major purge trials, physicians were accused falsely of murdering the writer Maxim Gorky by deliberately prescribing treatments that endangered his already weak lungs. This tradition was continued into the post-war period in the infamous doctor's case, in which leading physicians were accused of plotting the deaths of Soviet leaders. It would not be correct to interpret the anti-foreign hysteria of the late pre-war and early post-war periods as a simple revival of Russian nationalism. Rather, it represented a new, typically socialist form of xenophobia derived from a distorted appreciation of real problems. Scientists in newly post-colonial countries are very aware of the need for intellectual independence. They recognize that the Western hegemony of science is an instrument of domination. They are aware of the dangers of an excessive regard for established centers of science, which leads to the illegitimate transfer of techniques, reinforces the hierarchical, elitist social structure of science, and fosters the ideology of a neutral technocracy. In this context, the lesson of socialist xenophobia is not that socialist scientists should return to the fold of the international community of science as the only alternative to a Lysenkoist rampage. Rather, it leads to the demand for active evaluation and selection of those aspects of foreign science that can be incorporated into the structure of socialist science and to a militant resistance to scientific colonialism. This requires a total rejection of the simplistic bureaucratic dogmatic Marxism that sees only the unity of phenomena and therefore equates the philosophy, scientific content, social context, and political ideology of foreign science, without seeing the heterogeneity and contradictions in it. Ideologically, it means a reaffirmation of dialectical analysis, and this in turn depends on free discussion without administrative fiat. The apogee and decline of Lysenkoism. In 1940 there was still lively debate on the genetics question in the USSR, but by 1948 Lysenko had won the official backing of the party and the ministries. Some of his opponents lost their positions, others, who pretended to go along with him, continued at their institutes. Some transferred to the biophysics programs under the protection of the Institute of Physics. A few, like Schmalhausen, conducted a spirited rearguard defense of genetics. What had happened in the interim, of course, was the war, Reconstruction, and the Cold War. In 1946, in Fulton, Missouri, Churchill announced the Cold War. In 1947 the Cominform was organized to replace the defunct Comintern, and Andrés Danov put forth his thesis of the world divided into two camps. Communists were driven out of the post-war coalition governments in France and Italy, and by 1949 the North Atlantic Treaty had been signed, the first of the network of United States-dominated alliances encircling the socialist world. Effective intellectual contact between the Lysenkoists and geneticists all but ceased. A few of Lysenko's supporters attended international genetics congresses, but Soviet anti-Lysenkoists did not appear even when they were on the program. The genetics congresses deplored their absence and made plans to urge them to defect and offer them jobs in the West. Meanwhile, most of the Lysenkoists' work was ignored in the capitalist countries where, aside from the occasionally quoting of absurd claims for purposes of ridicule, interest centered on the administrative abuses of an aggressive Lysenkoism backed by the Soviet Communist Party. The disinterest in the scientific side of the dispute was such that in 1948, when an advertisement in Science offered translations of several of the best Lysenkoist research papers, only 8 people responded. In the context of the Cold War, even the suggestion that Lysenko's work ought to be examined cost Ralph Spitzer his position as a professor of chemistry at Oregon State University. The very limited contact between Lysenkoism and genetics was through anti-Lysenko Soviet and East European geneticists and Western scientists who were either pro-communist or not so blinded by the hysterical anti-communism of the times that they refused to examine the claims. Schmalhausen in the USSR and Waddington in Great Britain finally were able to show the basis of the apparent inheritance of acquired characters through the discovery of genetic assimilation, the process whereby latent genetic differences within populations are revealed but not created by environmental treatment and therefore become available for selection. Scattered researchers in Japan, France, Switzerland, Britain, and the United States repeated some of the experiments of Lysenko's group, but these were exceptions. In several Western countries leading biologists were effectively driven out of the communist parties because of their opposition either to Lysenko or to their party's endorsement of Lysenko. Thus another possible channel of communication was cut off. In this context of Cold War and the two camps doctrine, Lysenkoism became more strident and politically opportunist, more reckless in its claims. Whereas earlier Lysenkoism had emphasized that it is not at all easy to modify the heredity of organisms, and that responses to the environment are often barely perceptible, later Lysenkoists claimed to transform wheat into rye in a single step. Lysenkoists were never as ignorant of Western genetics as their counterparts were of Lysenkoist work. However, they used this literature mostly to search for admissions of the incompleteness of genetic theory, of the understanding of chromosome behavior, of possible cases of extranuclear inheritance, and so on. For example, Present quoted Franz Schrader, the American cytologist, as admitting that in the cytology of Drosophila itself there is much that does not conform to what we have set up as the standard course of events. This search for gaps, admissions, ambiguities, symptoms of a crisis in genetics, had something of the spirit of a Jehovah's Witnesses tract on evolution, in which paleontologists' comments on gaps in the fossil record are taken as evidence that the whole theory is false, and that its more perceptive practitioners recognize this. This approach, which we interpret as a crude, simplistic interpretation of the two camps doctrine, according to which socialist science had to reject and overthrow bourgeois science lock, stock, and barrel, made it extremely difficult for Soviet biologists to respond to new phenomena in genetics. All results were read as either still holding to the Morgan-Mendel doctrine or as tentatively departing from it. The experimental refutation or reinterpretation of Lysenkoist results probably had very little to do with the decline of Lysenkoism. As long as it maintained its institutional, administrative, and ideological coherence, Lysenkoism could filter out disturbing arguments or evidence, assimilate the results of genetics into its own structure, and remain intact. A paradigm has a semi-permeable boundary. The decline of Lysenkoism was accelerated by the development of modern genetics only after it lost its protective boundary. First of all, it did not fulfill its promises to Soviet agriculture. Agriculture remained the critical issue in the economy during the Khrushchev administration and afterward. But the same cause that had contributed to the rise of Lysenko in the 1930s now had the opposite effect. Meanwhile, economic planning and administration had become increasingly depoliticized, the domain of experts and technicians. The slogans now were not so much revolutionary innovation as business-like efficiency, cost accounting, balance sheets. The goal was not to develop an alternative, socialist technology but to adopt the most advanced American methods. This change was symbolized by Khrushchev's visit to the Garst farm in the American Corn Belt. At the same time, the incipient cultural revolution of the anti-elitist, populist element of the era of Stakhanovites and peasant innovators aborted, and the prestige of academic authority was reconsolidated. Perhaps for this reason Lysenkoism has retained a certain attractiveness in countries that are actively fighting the battle against the elite academy. Lysenko's administrative repressiveness has been rejected, but courses in Darwinism-Michurinism are still taught in some of the agricultural colleges of developing socialist countries, and visiting lecturers are sometimes queried about Michurin's teachings. In some capitalist countries certain Maoist sects are pro-Lysenko, some only vaguely, others with great firmness and conviction. For example, a pamphlet of the Sussex student movement in 1971 described Lysenko as a great upholder of materialist method of investigation and study in natural science, who firmly opposed all the unscientific methods of seeking facts to prove preconceived notions in biology that's still being promoted today. Because Lysenko upheld the scientific method of seeking truth from facts, he is now called by the scientific experts a crank. With the ebbing of the more raucous Cold War rhetoric and the development of an active coexistence approach, the two camps model of science lost its appeal. Emphasis shifted to underlining the common ground and similarity of Soviet and American science. The sporadic warnings that coexistence in international politics did not imply coexistence in ideology were, at least in science, a futile rearguard action. The opposition of Lysenkoism and traditional genetics, previously a matter of pride, now became an embarrassment. The weakening of the political police power, the return of exiled geneticists, the urgency of settling accounts with the repressive aspects of previous administrations coincided with the ideology of the specialists, the demand for freedom of scientific research not only from the imposition of ideological and political demands, but also from the influence of ideology and politics. Did Lysenkoism affect Soviet agriculture? It is commonly assumed that Lysenkoist agricultural techniques and biological doctrines had a serious effect on agricultural production. After all, if genetics is important for plant breeding, and plant breeding is important for agricultural production, then the serious errors propagated by the Lysenkoists must have disrupted progress in agricultural production. Yet what is the evidence for such a disruption? Whatever the figures for agricultural output, it can always be stated that they would have been higher if not for Lysenkoism. But the logic of such counterfactuals is not compelling, and we could as easily postulate that they would have been lower, except for Lysenkoism. What we can do, however, is to compare the history of Soviet agricultural production before, during, and after the predominance of the Lysenkoists with the history of American agriculture of the same period. We then have both an internal comparison through time and a cross-comparison. Can we see in such comparisons the postulated negative effect of Lysenkoism? We have chosen to look at wheat yields for this comparison, since vernalization of winter wheat was the first Lysenkoist recommendation and one that the movement came to be identified with. Table 7.3 shows indices of wheat yields from 1926 to 1970 in the Soviet Union and the United States. The yields in the Soviet Union are overestimated during the 1930s by as much as 20%, but the figures after the war do not suffer from this problem, nor are the base years affected. The comparisons are remarkable. Both American and Soviet productivity decreased during the 1930s, though certainly for different reasons. In the United States because the Depression reduced capital investment in agriculture, in the USSR because there were political problems associated with collectivization as well as problems of capital investment. During the war years the USSR suffered a catastrophic loss of productivity, while in the United States productivity was recovering. Beginning in 1950 both countries began a period of rapidly increasing yields, which kept pace with each other, the Soviet increases being somewhat higher. We should note that 1948 to 1962, the period of Lysenkoist hegemony in Soviet agrobiology, actually corresponded to the period of most rapid growth in yields per acre. Moreover, even a time delay hypothesis, supposing that the effects of Lysenkoism on genetic research were felt only later, is at variance with the observed continued growth in yields per acre. The data in the table are even more remarkable in that during this period the total acreage occupied by wheat increased in the Soviet Union from 30 million to nearly 70 million hectares, while American acreage shrank from 60 million to 45 million acres. Thus Soviet yields increased in spite of bringing large amounts of new and marginal land into cultivation, while the opposite process was going on in the United States. Table 7.3 Yields of wheat relative to the base years 1926 to 1928. Years. United States. Soviet Union. 1926 to 1928. 100. 100. 1929 to 1931. 98. 104. 1932 to 1934. 82. 93. 1935 to 1937. 87. 97. 1938 to 1940. 96. 113. 1941 to 1944. 118. 1945 to 1947. 118. 72. 1948 to 1950. 116. 106. 1951 to 1953. 116. 135. 1954 to 1956. 128. 130. 1957 to 1959. 159. 172. 1960 to 1962. 169. 184. 1963 to 1965. 175. 162. 1966 to 1968. 181. 213. 1969 to 1970. 207. 236. Source: Historical Statistics. For particular crops and particular situations, Lysenkoist doctrines may have stood in the way of solving some specific problems, but there is no evidence that Soviet agriculture was in fact damaged. Soviet yields followed the same upward trend as yields in other advanced technologies, chiefly as the result of massive capitalization of agriculture, through the use of pesticides, fertilizers, and farm machinery. Can there be a Marxist science? Lysenkoism is held up by bourgeois commentators as the supreme demonstration that conscious ideology cannot inform scientific practice and that ideology has no place in science. On the other hand, some writers are even now maintaining a Lysenkoist position because they believe that the principles of dialectical materialism contradict the claims of genetics. Both of these claims stem from a vulgarization of Marxist philosophy through deliberate hostility, in the first case, or ignorance, in the second. Nothing in Marx, Lenin, or Mao contradicts the particular physical facts and processes of a particular set of natural phenomena in the objective world, because what they wrote about nature was at a high level of abstraction. The error of the Lysenkoist claim arises from attempting to apply a dialectical analysis of physical problems from the wrong end. Dialectical materialism is not, and has never been, a programmatic method for solving particular physical problems. Rather, dialectical analysis provides an overview and a set of warning signs against particular forms of dogmatism and narrowness of thought. It tells us, remember that history may leave an important trace. Remember that being and becoming are dual aspects of nature. Remember that conditions change and that the conditions necessary to the initiation of some process may be destroyed by the process itself. Remember to pay attention to real objects in space and time and not lose them utterly in idealized abstractions. Remember that qualitative effects of context and interaction may be lost when phenomena are isolated. And above all else, remember that all the other caveats are only reminders and warning signs whose application to different circumstances of the real world is contingent. To attempt to do more, to try to distinguish competing theories of physical events or to discredit a physical theory by contradiction is a hopeless task. For every point of genetics supposedly contradicted by dialectical materialism, we can show that in fact there is complete support. To the Lysenkoist claim that Mendelism is idealist and formal, we respond that on the contrary Mendel solved the problem of heredity precisely by concentrating on the actual pattern of variation among the offspring of a cross, rather than by trying to sum up the results in a single idealized description, as others did. Mendel's revolutionary insight was that variation was the thing in itself, and that by a study of the pattern of variation he could bring together the two apparently contradictory aspects of heredity and variation under a single explanatory mechanism. Seeing the two contradictory elements, heredity and variation, as dual aspects of the same phenomena was a triumph of dialectical thought. Of course, there is a certain level of abstraction even in Mendel, and he took care to remove some kinds of real variation from his considerations. But the reproduction schemes in capital are also abstractions. In each case the degree of abstraction is appropriate to the problem and does not obfuscate it. To the Lysenkoist claim that genetics erects the gene as immutable and unchangeable, we reply that on the contrary an essential feature of genetics is the mutability and variation of genes. If genes were not mutable, genetics could not have been studied, for there would have been no heritable variation. To the Lysenkoist claim that the template hypothesis of the gene assumes that God must have created the first genes, we reply, remember that the conditions necessary to the initiation of some process may be destroyed by the process itself. It is, in fact, a triumph of Soviet biology that we begin to understand the conditions for the origin of life and of prebiotic evolution and to see how the evolution of life has destroyed the possibility of present abiogenesis. To the Lysenkoist claim that genetics erects a barrier between gene, soma, and environment, we reply that on the contrary developmental and molecular genetics has elucidated the exact material pathway from DNA to protein to environment and from environment to protein to DNA, but that such pathways do not happen to include directed changes in DNA from environmental contingencies, because there is no material causal pathway for such directed changes. It is pure metaphysical idealism to claim that the dialectical principle of interaction demands that all possible forms of interaction must, ipso facto, exist. To the claim that genetics does not have a correct view of the internal and external conditions for change, we reply with the metaphor from Maus. On contradiction. That an egg will not develop into a chicken unless it is kept at the right temperature, but that a stone will never become a chicken at any temperature. That is precisely a paraphrase of the outlook of developmental genetics, which asserts that a given phenotype will result only if the genes of the organism are operating in an appropriate environment, but only some genotypes can have that result, no matter what the environment. A dialectical view can make a number of positive contributions in biology, but the Lysenkoists did not pursue them completely or else applied them at inappropriate levels. Marxism stresses the unity of structure and process. Lysenkoists were justified in rejecting the view that sought explanations in terms of visible structures. It was valuable to expect and investigate the various physiological processes that accompanied the visible fusion of cell nuclei. But in counterposing process to structure, their view was more like that of anarchism, which sees structure as rigidity, death, and enemy of process. The emphasis on process resulted in seeing the cell as a blur of interconnections among blurs. In the end, they preserved the structure-process dichotomy. Marxism stresses the wholeness of things, both between the organism and its surroundings and within the organism. Even among Marxist undergraduates in the 1940s in the United States there was discussion of the need for feedback from the cytoplasm to the genes in development. But Lysenko did not seriously consider the relative autonomy of subsystems, while genetic dogma allowed only a one-way interaction. It was only much later that the modern genetic view arose, in which metabolites combine with some genes to regulate the activity of other genes. It is not clear to us whether Monod's own Marxism was relevant to the discovery. Marxism stresses the integration of phenomena at different levels of organization, but Lysenkoists saw only the intermediate level, that of the organism and its physiology. It was a one-dimensional scheme in which molecular events were dismissed as chance intrusions, and the population and community levels were ignored as dynamic entities in genetics or evolution. This despite the pioneering work of Gauss in Moscow at the same time, which opened up the modern ecology of coexistence. The view of evolution as the simple consequence of individual genetic modifications meant that Lysenkoists in fact had no evolutionary theory distinct from adaptation. Although Marxism stresses the interpenetration of an object and its surroundings, and although Lysenkoists stressed the importance of environment, they never really took it apart. They did not differentiate among regular and sporadic, predictable and unpredictable aspects of environment and local and widespread, short-term and long-term variations. Therefore they could not separate the different kinds of adaptive responses at the individual and population levels. Early Marxists had already pointed out the intimate relationship between random and determinate events, in which remotely related chains of causality look like chance. Random processes have determinate results, and in general the categories are not mutually exclusive. But by linking the uncertainty principle and indeterminacy to an attack on causality and on the intelligibility of the universe, Soviet Marxists became hostile to the creative role of random processes in evolution and therefore biased both against mutation as a source of evolutionary variation and against the probabilistic models of population genetics. A naive Marxism made Lysenko the enemy of change. One way in which a Marxist viewpoint can inform scientific work is by encouraging an alternative paradigm to the analytic Cartesian method. Such an alternative stresses system properties as the primary objects of study, as opposed to the conventional emphasis on separate elements, to which are added as a secondary refinement the interactions between them. The methodology of the analysis of variance, which separates out main effects and interaction, drives analysis in quite a different direction than does a complex systems analysis. This latter is not the same as an obscurantist holism that denies any possibility of drawing material causal connections. A major success of a complex systems analysis derived, in part, from a conscious application of a Marxist worldview, is the theory of community ecology, with its emphasis on the community matrix and on species interactions. A more common use of a Marxist approach is in the analysis of apparently unresolvable contradictions in a science. For example, in evolutionary genetics at the present time there are serious contradictions between the standard explanations and the observations on genetic variation within species. But the explanations, which are all equilibrium and steady-state theories, allow no role for historical processes. They are based on single genes rather than on whole genomes. When complex genetic systems are analyzed and when assumptions of equilibrium are relaxed, the contradictions disappear. We have described the Lysenko movement as a failure in several ways. By linking a stand on scientific issues to basic political partisanship, it brought the whole repressive apparatus into genetics and had disastrous effects on Soviet biology as a whole and on many scientists individually. By depending increasingly on party and administrative support, it undercut its own potential for an anti-elitist cultural revolution. It also failed to fulfill its potential as a scientific revolution and a revitalizer of agricultural technology. The potential and the failure of the Lysenko movement can be traced to the same sources: the Marxist philosophical framework, which opened up exciting insights but shut off their creative fulfillment, and behind that the social gap between rural and urban USSR. That gap split Marxism into two trends: the complex, involuted, dogmatic philosophy of the professional academic Marxists and the common sense, naive, simplistic, and often anti-intellectual folk Marxism of the Lysenkoist innovators. The insight provided by Marxism might have been strengthened and the crudities modified if it were not for the way the two camps model was interpreted. The confrontation between socialist and bourgeois science was seen in the military metaphor as an implacable battle ending with victory or defeat. There was no sense of interaction. Enemy scientific writings consisted of the outrageous or of admissions. We have already pointed out how this prevented any creative assimilation of new developments in genetics. It also made partisanship the test of quality and resulted in a decline in the general level of Lysenkoist research. It established a one-way external interaction between philosophy and science, in which the philosophers interpreted and blessed or condemned particular scientific views, but scientific advances never developed the theoretical richness of Marxism. There is some danger that the errors of the Lysenkoist movement and recurrent vulgarizations of Marxism, which even now repeat those same errors, will inhibit Marxist scientists from making a fruitful use of their worldview. We hope that a proper understanding of the history of the Lysenkoist movement will be of some help in bringing the deep insights of Marxism into the practice of science. Present, an attorney by training, joined Lysenko first as a polemicist and then did some experimental work. He was an especially strident, dogmatic, and abusive participant in the debates. Jean-Baptiste Lamarck, author of Zoological Philosophy, argued that evolution occurs through the inheritance of acquired adaptive responses to the environment. Boris Hessin, director of the Moscow Institute of Physics, made an ambitious, but only partly successful, attempt to give a materialist interpretation of the early history of Western physical science. See Hessin. J. D. Bernal, a British Marxist physicist, gave a Marxist interpretation of the history of sociology science in his two main historical works. 8. The Commoditization of Science. M. Modern science is a product of capitalism. The economic foundation of modern science is the need for capitalists not only to expand horizontally into new regions, but to transform production, create new products, make production methods more profitable, and to do all this ahead of others who are doing the same. Its ideological underpinnings are congruent with these needs and also with the political philosophy of the bourgeois revolution: individualism, belief in a marketplace of ideas, internationalism, nationalism, and rejection of authority as the basis of knowledge. As capitalism developed, so did the ways in which science participated. From a luxury consumption for the aristocracy, science became an important ideological weapon in the struggle against feudal theology and a resource for solving practical problems of the economy. After the long depression in the last part of the 18th century, there was a definite upsurge of inventions and innovations in industry and agriculture. The number of patents registered in Great Britain rose from 92 during the 1750s to 477 in the 1780s. Agricultural societies were established around that time, and advances in animal breeding and management resulted in the formation of cattle breeds, such as Hereford. The weight of cattle marketed in London doubled in the course of the 18th century, and that of lambs tripled. In the early 19th century, agricultural journals began to be published. The leaders of the bourgeois revolutions recognized the potential of scientific research for military and commercial power. Among the earliest scientific societies were the Royal Society, in 1662, the American Academy of Arts and Sciences, founded in 1780 by leaders of the Revolution in New England, Franklin's American Philosophical Society, and the Naval Observatory in Greenwich. In France, the Directorate founded the École Polytechnique in 1795, and Napoleon urged scientists to develop munitions, as well as a synthetic indigo dye to replace the imports from India that were cut off by war. The systematic surveying and cataloging of the biological resources of tropical regions conquered by European countries led to a flowering of systematic biology under the leadership of Linnaeus. By 1862 the Morrill Act in the United States set up the land-grant colleges of agriculture and mechanical arts in recognition of the importance of scientific knowledge for the improvement of farming and mining. Throughout the first century of the Industrial Revolution, science enlarged its role as an externality of the capitalist expansion, like roads and lighthouses, and as a way to solve particular problems. But science was not yet a commodity. Its application was still uncertain, its potential still mostly untapped, its product still often an after-the-fact explanation of empirical innovations. The production of commodities, the expending of human labor to produce objects or services for sale certainly antedates capitalism. But under capitalism the commodity form of economic activity penetrated increasingly into all aspects of human life. In 1607, in the rarely performed Timon of Athens, Shakespeare lamented this commercialization. Gold. Yellow, glittering, precious gold. Thus much of this will make black white, foul fair, wrong right. Base noble, old young, coward valiant. Ha, you gods! Why this? What this, you gods? Why, this? Will lug your priests and servants from your sides. Pluck stout men's pillows from below their heads. This yellow slave will knit and break religions, blessed accursed. Make the whore leprosy place thieves. And give them title, knee, and approbation. With senators on the bench. 2 centuries later Marx and Engels wrote in the Communist Manifesto. The bourgeoisie, wherever it has got the upper hand, has put an end to all feudal, patriarchal, idyllic relations. It has pitilessly torn asunder the motley feudal ties that bound man to his natural superiors and has left no other bond between man and man than naked self-interest, than callous cash payment. It has drowned the most heavenly ecstasies of religious fervor, of chivalrous enthusiasm, of Philistine sentimentalism, in the icy water of egotistical calculation. It has resolved personal worth into exchange value and in place of the numberless infeasible chartered freedoms has set up that single, unconscionable freedom free trade. The bourgeoisie has stripped of its halo every occupation hitherto honored and looked up to with reverent awe. It has converted the physician, the lawyer, the priest, the poet, the man of science, into paid wage laborers. Activities that previously were the direct result of human interactions, entertainment, emotional support, learning, recreation, childcare, even human blood and transplantable organs or the use of the womb have now entered the marketplace, where human relations hide behind impersonal buying and selling. Each time a new aspect of life is commoditized, some resistance is expressed as outrage at the debasement of previous values. When the price of bread was freed to respond to the market, bread riots broke out among the English working class. The commercialization of the means of communication and the information monopoly led to the concerns raised by Third World delegates at UNESCO in the 1980s and the call for a new information order. The commercialization of healthcare forced people to raise the issues of national health service or insurance. The commoditization of science, then, is not a unique transformation but a natural part of capitalist development. And we discuss it not to express outrage but to examine the consequences of this change for scientific activity. The commodity form establishes equivalences among very different objects. Although a camel is not equivalent to a blanket, the value of a camel is equivalent to the value of a certain number of blankets. C is not equal to B, but V equals V. By way of the qualitatively equivalent exchange values of objects, it becomes possible to trade them and thus to transform them into each other. The market achieves what the alchemist could not, In 1980, lead could be transformed into gold in the ratio 500 pounds of lead for 1 fine ounce of gold. This ability to establish equivalences among dissimilar objects made trade the predominant form of exchange for the products of human labor outside of the individual household. There are of course other forms of exchange: customary gift-giving, sharing, redistribution in periods of hardship, ritualized exchanges. But even within the family, distribution may be dominated by commodity relations, as when the best food is given to the wage earner or when women have to struggle to control their own earnings. Commoditization also implies a giant step in abstract thought, in that the distinct objects are seen as both economically similar and physically different, the difference and the similarity both being prerequisites for trade. Before exchange can be completely commoditized and before exchange values can emerge as an objective economic property of goods, exchange must be frequent enough for the law of large numbers to operate. The idiosyncratic preferences of individual purchasers, their relative abilities to bargain, their individual urgencies are smoothed out when the same objects are regularly bought and sold, when a purchaser can reject an offer and look for the same product elsewhere, when a producer can expect other customers. The commoditization becomes more profound when investors can put their capital into those enterprises that promise greatest profits, and the availability of labor allows investors to treat people, even highly skilled people, as generalized human labor power, an interchangeable cost of production. By the end of the 19th century, scientific production was an essential part of the chemical and electrical industries. But not until the mid-20th century did science become a commodity on a massive scale. As such, it has the following characteristics. Research has become a business investment. Within corporations of the technical industries, some 3 to 7% of sales is reported as expenditure on research and development. Investing in research, which is one of several ways of investing capital, competes with other ways, such as increasing production of existing products, purchasing more advertising, hiring lawyers or lobbyists, buying up businesses in other fields, busting unions, bribing cabinet ministers of potential customer countries, and so on. All possibilities are measured against each other on the single scale of profit maximization. It is widely known that research expenditures are the first to be cut back when a corporation suffers economic reverses, presumably because technical innovation has no immediate payoff, while increased advertising, labor costs, and material costs can be immediately reflected in profit. Studies of corporate decision-making repeatedly show that the typical decision horizon of managers is at most 3 to 5 years. Since research often has no payoff within such a period, it is most dispensable. At the same time, the costs of long-range research are socialized by changing the locus of the work from individual enterprises to public institutions such as universities and national institutes. In this way, by tax subsidization, no individual firm need risk an investment, and the total costs are spread over the entire tax base. When such socialized research comes close to producing a marketable product, the final development stages are taken back into private hands in order to realize an exclusive property. This is the picture, for example, in the development of new varieties in agriculture. State experiment stations develop lines, which are then released to certified seed producers. The lines then become general property and are taken up by seed companies who fine-tune them and sell the results to farmers. The extreme form of research investment is the scientific consulting firm, whose only product is the scientific report. Here it is most obvious that the test of quality of the report is the client's satisfaction rather than peer review. If the report is an environmental impact evaluation, satisfying the client means convincing the appropriate regulatory authority that the company is complying with the law and that its activities are not harmful, and doing this for minimum cost. The relationship of the consulting firm to corporate client is complex. The consultant obviously prefers a big contract to a small one and therefore may push for a more thorough investigation than the client wants. On the other hand, because the field is so competitive, the consultant has an incentive to keep costs down. The result is that the consultant does just enough research to ensure that the environmental ruling will be favorable, to document those problems that are likely to arise, and not to look for trouble. Such ventures are highly risky for consulting firms. Their major asset is the goodwill of clients, since the capital consists mostly of computation facility and office furniture. There is a high rate of turnover of companies in environmental consulting. Once the scientific report becomes a commodity, it is also subject to two other features of the business world: the stagecoach can be hijacked, and the beer can be watered, that is, scientific commodities may be stolen or debased. Both kinds of entrepreneurship, the appropriation of the work of others and the falsification of results in order to publish accounts of success or to beat out competitors, are a growing problem. Although scientific frauds occurred in the past, everybody knows about the Piltdown hoax, and priority fights did occur among individuals vying for prestige. Scientific frauds now have a rational economic base and so may be expected to increase. Scientific discovery has become quantifiable. A corporation can estimate how long it takes on the average to develop a new drug or computer, with how much labor, and at what cost. Therefore, a research and development company or corporate division can look at scientific activity as generalized human labor, rather than as a way to solve particular problems. Scientists have become scientific manpower. As such, they are subject to costs of production, interchangeability, and managerial supervision. The division of labor within science, the creation of specialties and ranks, now becomes increasingly rationalized. The creative parts of scientific work are more and more restricted to a small fraction of the working scientists, the rest are increasingly proletarianized, losing control not only over their choice of problem and approach, but even over their day-to-day, and sometimes, their hourly, activity. Scientific management, first developed for the auto industry in the infamous Taylor system at Ford, has been extending into commerce, office work, and scientific research. The managerial approach self-consciously sees the labor force as objects to be used for the ends of the managers. The fragmentation of skills, and the resulting increase in specialization, is derived not from the intellectual needs of a field but from the manager's cost accounting. It is cheaper to train one laboratory hematologist and one urinologist than to prepare two general medical technicians. Therefore their labor power is cheaper, wages are lower, obsolete parts can be fired and replaced. Furthermore, the fragmentation and descaling consolidates control over the divided workforce. But descaling in scientific work makes for greater alienation. The producers do not understand the whole process, have no say over where it is going or how, and have little opportunity to exercise creative intelligence. Once the labor is alienated in this sense, once science is just a job, increased supervision is necessary. The burdensomeness of that supervision makes for further alienation and encourages corruption or indifference. It also takes control out of the hands of scientists and gives it to managers. The researchers themselves, and even the administrators of science, are no longer responsible primarily to their peers but, rather, upward in the hierarchy, to the controllers of resources. One byproduct of this phenomenon is that research proposals submitted to granting agencies become longer, more detailed and cautious, and are a less honest reflection of the research intentions. The awarders of research money, concerned with justifying their decisions, opt for caution and demand increasing documentation. Scientific labor must itself be produced. Universities and vocational schools aim at preparing the various grades of scientific labor at minimum cost, turning the education process itself into an external service for the personnel departments of private enterprise. This exerts a pressure on the educators for economic efficiency. Don't have the students overqualified, concentrate on what they need to know, shorten the duration of graduate study, get more PhDs for the buck. At the elementary education level, this pressure means back to basics. The utilitarian approach is not universal and is not always so crude. Educators often have their own goals that clash with the prevailing social trends. But even the more innovative programs produce people for the less clearly defined assignments of ruling and keeping the system flexible. Scientists react to this commoditization in opposite ways. On the one hand, they deplore it. Many of them, recruited from the middle class, chose science as a way to escape the world of trade. They chose to engage in a kind of labor whose product was a use value, worthwhile for its own sake rather than for exchange. They resent the loss of the old esprit de corps and the selfless dedication to truth which was the organizing myth of pre-commodity science. They resent the proletarianization of scientific labor and their loss of autonomy, and they resist, in individualistic ways, the imposition of managerial controls and bureaucratic determination of worth. If they organize, they avoid calling their associations unions. On the other hand, scientists rush to take advantage of new entrepreneurial opportunities. Some, especially during the brief period of American affluence following Sputnik, chose a career in science as one of several alternatives that would provide financial and other rewards. Some 2/3 of all scientists working in the U.S. are employed by private industry and business, where the pursuit of profit is the frankly recognized goal. The transitional condition of scientists as a stratum of professional intellectuals who are in the process of losing their professional status and being incorporated into the structure of capitalism exacerbates the contradictions in their ideological positions and their social action. These vary from defiant assertions of individual responsibility and dissent, through cautious criticism, and studied indifference, to servile sycophancy, from elitist resistance to being bureaucratized and proletarianized to realistic or enthusiastic participation in the new order, to alliance with other alienated sectors in the struggle against capitalism. As a result of these developments, the class divisions that plague our society as a whole also cut across the ranks of science. The majority of the 1 million or so working scientists in the United States form a scientific proletariat. They sell their labor power and have no control over their product or their labor. At the opposite end, a few thousand at most form a scientific bourgeoisie, investing in research and determining much of the direction of research and development. In between these extremes is the group of petty bourgeois professionals working alone or in small groups in universities and research institutes. Although they may be motivated by a great diversity of concerns, their activity depends increasingly on obtaining funding from government agencies, private foundations, or corporations. For them the research grant has become a necessity. And the relation between the grant and the research has gradually been transformed, whereas initially the grant was a means for research, for the entrepreneurs of science, the research has become the means to a grant. The capital inputs for science have become major industries. These include chemicals, apparatus, culture media, standardized strains of laboratory animals, and scientific information. One consequence is that the development of scientific technology is often separate from the scientific research it is intended to serve. The technology is not directed at finding the cheapest or best way to study nature but at gaining profit from specific markets. In third world countries, sales representatives urge the new scientific institutes to have the best, the most modern equipment long before spare parts, repair service, or reliable electric power are available. The president of the country may pose at the dedication of a shiny new 16-channel electroencephalogram for the Psychiatric Institute, but he would not show up for the trial run of buckets filled with banana mash used for surveying fruit flies. It is more dramatic to found an institute than to keep it running. Therefore, there is now a rich tradition of telling about underutilized or broken or abandoned facilities throughout the tropics. At present it costs about $100,000 a year to keep one scientist working in the United States, the equivalent of the wages of perhaps 5 industrial or service workers. In third world countries, scientists' salaries are lower, but equipment and supplies cost more, and infrastructure is often not available. It may require the labor of 50 or more workers to provide the resources to support one scientist. Originally, scientific journals were published by scientific societies to take the place of personal communications. Now, however, publishing companies have moved into publishing scientific books and journals. Company representatives often flatter and cajole scientists into writing another textbook in, say, population genetics, because we already have good sellers in molecular genetics and developmental genetics, and this would complete the line. What is published now depends on the publishers and editors' need to fill the journal and the authors need to be published in time for tenure review, a job hunt, or a raise. The question rarely arises, is this publication necessary? Therefore, a significant part of the much-cited information explosion is really a noise explosion. The commoditization of university science results from the financial needs of universities. They consider scientists to be an investment in 4 ways: for obtaining research grants from government agencies and corporations, for converting scientific reports into public relations and the prestige into endowments, for raising the standing of the university as the basis for raising tuition and attracting students, and, finally, for sharing in the patents of inventions made by university faculty. As a result, the allocation of resources within a university is influenced by the prestige and earning capacity of the various programs, and scientists in a number of universities report pressure from their administrators to turn their research in more affluent directions, such as genetic engineering. The conditions of existence of the scientific strata in the capitalist economy reinforce the beliefs and attitudes scientists receive as part of the general liberal conservative heritage. Despite a broad range of variation in scientists' beliefs, and despite the contradictory beliefs we all hold, there does exist a coherent implicit ideology that can legitimately be designated bourgeois. It includes the following characteristics. Individualism. The bourgeois atomistic view of society, as applied to science, asserts that progress is made by a few individuals. Scientists see themselves as free agents independently, pursuing their own inclinations. Just as in astronomy the difficulty of admitting the motion of the Earth lay in the immediate sensation of the Earth's stationariness and of the planet's motion, so in history the difficulty of recognizing the subjection of the personality to the laws of space and time and causation lies in the difficulty of surmounting the direct sensation of the independence of one's personality. Nowhere is the sensation of independence stronger and the deception more pitiful than among intellectuals. Individualism in science helps create the common belief that the properties of populations are simply derivable from those of the unchanged arced atoms of populations or societies. It also transforms the subjective experience of career ambition into the invention of selfishness as a law of evolution. A crucial element of individualistic ideology is the denial of that ideology. Elitism. This assertion of the superiority of a small minority of intellectuals often leads to the belief that the survival of humanity depends on the ability of that minority to cajole and con the rest of the people into doing what is good for them. This bias is especially pronounced in science fiction accounts of resistance to political oppression, in which a few dedicated scientists conspire to outwit the rulers. This elitism is profoundly anti-democratic, encouraging a cult of expertise, an aesthetic appreciation of manipulation, and a disdain for those who do not make it by the rules of academia, which often reinforces racism and sexism. The dismissal of folk knowledge has contributed to disasters in agricultural development. The elitist view supports a managerial approach to the administration of intellectual life and sees the co-optive self-selection of the academic and corporate elite as a reasonable way to run human affairs. In the internal theoretical issues of science, elitism perhaps contributes to the belief in the notion of hierarchical organization and to the search for the controlling factor that fits into the reductionist worldview, which retards the study of the reciprocal interpenetration of parts in favor of a chain of command model of genetics, society, and even ecosystems. Whereas the individualistic view favors a model of the world in which the parts are essentially independent, the elitist paradigm imposes an organization that precludes autonomy. Pragmatism. In Western ideology, pragmatic is a term of praise, in contrast to ideological, which is pejorative. For scientists, pragmatism means accepting the boundary conditions imposed by commoditization and specialization. It means getting on with the job without asking why, a stance immortalized in Tom Lehrer's song about the missile expert: if the rockets go up, who cares where they come down? That's not my department, said Werner von Braun. Since the major pathway by which scientists affect policy is through their advice as consultants to decision makers, being effective requires maintaining credibility. Therefore, advice must be limited to the domain of the acceptable. The dread of the raised eyebrow that withdraws credibility acts to impose not only prudence in giving advice but also, eventually, to narrow the intellectual horizons of the advisors. In the pragmatist's eyes, strong feelings about the injustice of social arrangements are necessarily suspect as ideological, reflecting immaturity as against scholarly cool separation of thinking from feeling. Scientists may once have had to struggle to establish the principle that all claims about the world must be validated by evidence. Neither appeals to authority nor one's own wishes are allowed to carry any weight in scientific controversy. Some separation of thinking from feeling was probably necessary to establish the legitimacy of science. But once it became absolute, that separation became an obstacle to self-conscious scientific practice. It obscures the sources of our preferences about directions to take or methods to use. It imposes a formalized introduction to scientific papers, pretending to move the individual scientist out of the process of creative work through the pitiful device of removing first-person pronouns, adopting the grammatical form that Susan Griffin described as the passive impersonal. More important, after questions of fact are formally freed from questions of value, they are not easily rejoined. While philosophers devote lifetimes to discussing how to relate the is to the should, scientists are free to build all kinds of weapons, buffered by the impersonal vocabulary of cost-effectiveness, kill ratio, and such terms, from acknowledging the effects of the products of their labor. Finally, the supposed superiority of thinking over feeling implies that those who withhold feelings are superior to those who express them. One result is that women, socialized in our society as the custodians of feeling, must either suppress themselves in order to be allowed to do science or must be systematically underestimated, as if more emotional meant less rational. Reductionism. The specialization of scientific labor and of command functions from research creates a model of scientific organization that is easily seen as the model for the organization of the world. Nature is perceived as following the organization chart of our company or university, with similar phenomena united under a single chairman, distinct but related phenomena under a common dean, and unconnected events belonging to different schools or divisions. Thus specialization in practice joins with atomistic individualism to reinforce the reductionism that still predominates in the implicit philosophy of scientists. As socialists, we do not criticize the commoditization of science in order to appeal for a return to the times before science became a commodity. That would be as futile as the antitrust laws, which seek to recreate precisely those past conditions that gave rise to the trusts. Our intent is different. The commoditization of science, its full incorporation into the process of capitalism, is the dominant fact of life for scientific activity and a pervasive influence on the thinking of scientists. To deny its relevance is to remain subject to its power, while the first step toward freedom is to acknowledge the dimensions of our unfreedom. As working scientists, we see the commoditization of science as the prime cause of the alienation of most scientists from the products of their labor. It stands between the powerful insights of science and corresponding advances in human welfare, often producing results that contradict the stated purposes. The continuation of hunger in the modern world is not the result of an intractable problem thwarting our best efforts to feed people. Rather, agriculture in the capitalist world is directly concerned with profit and only indirectly with feeding people. Similarly, the organization of healthcare is directly an economic enterprise and is only secondarily influenced by people's health needs. The irrationalities of a scientifically sophisticated world come not from failures of intelligence but from the persistence of capitalism, which as a byproduct also aborts human intelligence. In a world in which some countries have broken with capitalism, it is important to emphasize that the way science is not how it has to be, that its present structure is not imposed by nature but by capitalism, and that it is not necessary to emulate the system of doing science. 9. The political economy of agricultural research. This chapter is a composite of an article, Agricultural Research and the Penetration of Capital. Science for the People. 14, 12-17, and a paper presented at the Gramsci Institute, Palermo, Italy, in October 1983. He direction of technical change in capitalist agriculture and the research strategies that support this direction are the result of two kinds of factors: the quest for profit by industry and the pursuit of social control by the capitalist class as a whole. Profitability and solvency. On the face of it, agricultural production in the United States seems to present a difficulty to political economic theory. An important sphere of production seems to have resisted the usual penetration of capitalism. Ships and shoes are produced by a relatively small number of very large corporations with huge capital investment, but the production of cabbages has remained firmly in the hands of 2.5 million petty producers. Why has technological change and concentration of capital, as seen in manufacturing, transportation, and extractive industries, not taken over agricultural production as well? An answer sometimes given is that agriculture has simply lagged behind and that monopoly capitalism is finally catching up with it. The number of farms is decreasing, the average size of farms is increasing, and big enterprises are taking over huge acreages. This answer does not really meet the facts, however. Of the 3 million farm operators who disappeared between 1900 and the present, 2 million were tenant farmers. The proportion of all farms run by managers rather than family units has not changed, and big corporations have actually divested themselves of farmland in recent years. There is simply no rush to make farms into immense General Motors corporations. The basic problem in analyzing capitalist development in agriculture is the confusion between farming and agriculture. Farming is the process of turning seed, fertilizer, pesticides, and water into cattle, potatoes, corn, and cotton by using land, machinery, and human labor on the farm. Agriculture includes farming, but it also includes all those processes that go into making, transporting, and selling the seed, machinery, and chemicals used by the farmer, and all of the transportation, food processing, and selling that go on from the moment a potato leaves the farm until the moment it enters the consumer's mouth as a potato chip. Farming is growing peanuts, agriculture is turning petroleum into peanut butter. We claim that if agricultural production is viewed as a complete process, capital has completely penetrated it in the United States, and technological change has played the same role in that penetration as it has in all other productive sectors. That is, the owners of large amounts of capital are the ones who control and profit from agriculture. A corollary of this claim is that agricultural research, although directly responsive to the demands of farmers, is, in fact, carried out on terms set by the concentration of capital. The most striking change in the nature of agricultural production in the United States since the turn of the century is in the composition of inputs: the seed, fertilizer, energy, water, land, and labor used by the farmer in production. The total value of these inputs in any year can be calculated by weighting the physical amount of each by its price, adjusted for inflation. This value can then be compared from year to year by establishing some year as an arbitrary base with the index value 100 and expressing all other years relative to it. The total value of inputs into farming rose from an index value of 85 in 1910 to about 100 in 1975, which is not a very great increase, but the nature of these inputs changed drastically. Inputs produced on the farm itself went from an index value of 175 down to 90 between 1910 and 1975, while the index value of inputs purchased from outside the farm rose from 38 to 105. That is, farmers used to grow their own seed, raise their own horses and mules, raise the hay the livestock ate, and spread manure from these animals on the land. Now farmers buy their seed from Pioneer Hybrid Seed Company, their mules from the Ford Motor Company, the hay to feed these mules from Exxon, and the manure from Union Carbide. Thus farming has changed from a productive process, which originated most of its own inputs and converted them into outputs, to a process that passes materials and energy through from an external supplier to an external buyer. The consequence of this change can be seen in the sources of the market value of consumer products. At each stage of a productive process, as a raw material is converted to a partly finished form, then to a finished product, and then into an item for the consumer, some value is added to the material by the labor expended. Iron and coal are cheaper than the steel that is made from them, the steel is cheaper than the girder made from it, the girders cheaper than the bridge built from them. At each stage the transformation of form by the labor expended on it adds value, and the total value added is the difference in price between the original raw materials and the final product consumed. At present only 10% of the value added in agriculture is actually added on the farm. About 40% of the value is added in creating the inputs, and 50% is added in processing, transportation, and exchange after the farm commodities leave the farm gate. Another facet of this structure is that, although the percent of the labor force engaged in farming has dropped from 40% in 1900 to 4% in 1975, the number of those who supply, service, transport, transform, and produce farm inputs and farm outputs has grown. For every person working on the farm, there are now about 6 persons engaged in off-farm agricultural work. To sum up, farm production is now only a small fraction of agricultural production. The second major historical fact concerns the detailed nature of the production process on the farm and of farm productivity. Total farm productivity, measured as the ratio of farm outputs to farm inputs, went from an index value of 53 in 1910 to 113 in 1975. That is, for each dollar spent by the farmer on inputs, the value of what the farmer produced more than doubled. It is extremely difficult to estimate total inputs in the 19th century, but labor productivity increased, depending on the crop, by a factor of 2 to 3. The increase in farm productivity took place in stages corresponding to important technological innovations. The first period, from about 1840 to about the turn of the century, was marked by a tremendous increase in labor productivity because of the introduction of farm machinery. The steel plow, the harvester, the combine, and the stationary steam engine increased labor productivity in grain production, for example, up to 8 times in dry regions where full combines could be used. This development in machinery, however, stagnated for a time around the end of the 19th century because of the lack of traction power. Only small multiple plows could be pulled by horse teams. Stationary steam engines for threshing had to be fed with grain by horse and wagon, and rudimentary steam tractors were not easily maneuvered. Then, after the First World War, the automotive industry developed flexible, powerful, mobile traction. Invention of internal combustion engines, diesel engines, the differential allowing rear wheels to move independently, and inflatable tires resulted in farm tractors that could pull heavy loads and maneuver in tight places. The final spurt of farm machinery adoption was between 1937 and 1950. The third major change came after the Second World War. Chemical inputs to farming increased by a factor of 7 between 1946 and 1976. This happened for 2 reasons. First, chemical plants had been built at government expense during the war, so chemical companies found themselves with immense unused plant capacity. The price of fertilizer fell dramatically compared with other inputs. Second, the European export market increased dramatically, so farm production had to be stepped up quickly, and the use of more fertilizers was the fastest, cheapest way. There are 3 features to note about these technological changes. First, they were the product not of agricultural research but of entrepreneurial capitalism. Cyrus McCormick and Obed Hussey, who invented reaping machines in the 1830s, were typical inventor entrepreneurs of early industrial capitalism, and the flourishing of the first phase of mechanization was a consequence of industrial capitalism. McCormick was a Virginia farm boy who invented a successful reaping machine in 1831, patented an improved model in 1834, and in 1841 established a large factory for its production in Chicago. The improvements in traction power were a direct spin-off of the development of the automobile as the leading American industry, and the fertilizer and pesticide revolution was a consequence of the economic structure of the chemical industries and of strong export demand. Second, for all cases, but especially for mechanization, labor process is at the heart of the change. Farmers, like other producers, are under a constant pressure to reduce labor costs. The introduction of the reaper came 20 years before the labor shortage of the Civil War. But in addition, farmers are under an unusually strong pressure to control the labor process, not simply to reduce the payroll. A strike by harvest workers results in total loss of the product, not simply postponement of production. Workers' carelessness can cause crop loss or damage, but it is very hard to supervise farm labor or to regulate its speed. For that reason, piecework is common in harvesting, but piecework puts a premium on total speed without quality control. Mechanization provides control over speed and quality, as well as guaranteeing production. No strikes, no shortages. In this connection, it is interesting that the early vegetable farming machines were simply large horizontal platforms, pulled by a tractor, on which workers lay to tend or harvest the plants. The farmer or foreman drove the tractor. This reverse assembly line, in which workers are moved across the work, not only reduced the labor force but also controlled the speed of work and allowed close supervision of the process. It was made possible by Henry Ford. Third, the effect of the technology has been to reduce the value added on the farm and increase the value of purchased inputs. That is, the chief consequence of technological innovation to increase on-farm productivity has been to make on-farm productivity less and less important in determining agricultural value. Major changes in all aspects of farming technology have been in the same direction. Thus hybrid seed is a purchased input replacing the older self-generated seed, mechanized irrigation replaces labor-intensive ditching, and so on. It is important to note that not all changes in value added on the farm are the consequence of technological change in agriculture. Changes in factor prices in inputs and processing as a result of technological or political changes also change the proportion of value added on the farm. Where does agricultural research fit in? The research carried out by suppliers, seed companies, machinery companies, chemical companies is clearly designed to maximize the use of purchased inputs. But socialized research has the same goal. Our field studies of research scientists in state agricultural experiment stations give a consistent picture. Research workers usually come from farm backgrounds, or at least from small-town agricultural service communities. Their ideology is to serve the farmer by making farming more profitable, less risky, and easier as a way of life. They also say that benefits to the farmer will trickle down to the consumer. In actual practice, most agricultural research is directly responsive to the demands of farmers. But the critical point is that the farmers' demands are determined by the system of production and marketing in which they are trapped. Thus the farmer becomes the agent by which the providers of inputs and the purchasers of outputs use the socialized establishment of research. Agricultural research serves the needs of capital by responding to the demands of farmers, because capital totally controls the chain of agricultural production and marketing. On the production side, the influence of capital is obvious. Farmers buy and use huge amounts of herbicides instead of cultivating their fields. Weed science departments in schools of agriculture spend their time testing and evaluating herbicide treatment combinations, leaching rates, and toxicity. Agricultural engineering departments design machines for applying herbicides and redesign other machines for use in weed-free fields. Plant breeders breed for earliness to take advantage of herbicide treatments. In plant breeding, the hybrid seed method has become omnipresent. It is advantageous to seed producers because it makes the purchase of seed from a seed company necessary. but the main objective of the hybrid breeding is to produce varieties that work best with heavy use of fertilizers. All phases of research are directed by the nature of purchased inputs. Hybrid corn is a striking example of how inputs that used to be produced by farmers are now purchased. In the 1930s, corn was harvested by hand, and farmers obtained seed for the next year's crop by picking out good-looking ears during the harvest and saving them. Since then, self-produced seed has been increasingly replaced by hybrid corn, the seed for which must be purchased from a seed company every year. Hybrid corn, like any other hybrid plant or animal, is produced in 4 stages. First, corn strains are self-pollinated generation after generation to produce so-called inbred lines, each of which are genetically very homogeneous but different from one another. Second, the inbred lines are crossed with each other in all combinations to find a hybrid combination that has higher than average yield. Third, the inbred lines that went into the superior hybrids are grown in large numbers to make enough plants for seed production. Finally, the lines are crossed in massive numbers to produce the seed for sale. All of these steps need special isolation fields, lots of skilled labor, and some scientific knowledge. No farmer can afford to make his or her own hybrid corn seed, so he or she must buy it from the seed company. Moreover, the farmer must buy it every year because the hybrids, if allowed to reproduce, do not breed true and will not produce such high yields as the original hybrids. In fact, seed companies do not carry out the first 2 stages of the operation themselves. They depend on state agricultural experiment stations, funded at public expense, to find the best inbred lines. Then the companies use those lines to make the seed and the profit. Most of the hybrid corn seed now used in the Corn Belt, which is produced by 4 different seed companies, derives from a Missouri and an Iowa inbred line developed by the state experiment stations. Farmers began using hybrid corn because it gave an initial increase in yield over the open-pollinated varieties that farmers themselves had been propagating. Since the 1930s, immense effort has gone into getting better and better hybrids. Virtually no one has tried to improve the open-pollinated varieties, although the scientific evidence is that if the same effort had been put into such varieties they would be as good as or better than hybrids by now. On the contrary, there has been pressure by seed companies and commercial animal breeders to produce hybrid soybeans, chickens, cattle, and so on, and to convince farmers that their hybrids are better. Cargill and Northrop King, to name 2, have spent millions in attempts to make hybrid wheat that is superior to the usual varieties. They have not yet succeeded, but if they do, they will make millions selling wheat seed every year. At present, wheat farmers need to buy new seed from the seed companies only every 3 to 5 years. On the marketing side, the same dependence is evident. Just as the procession of farm inputs, seed, fertilizer, pesticides, and machinery is highly monopolized, so farm outputs are purchased by monopoly buyers. Cargill buys grain, Hunt buys tomatoes, Anderson Clayton buys cotton. Cargill pays for soybeans based on the regional average protein content. But there is a negative correlation between yield and protein, so it does not pay a farmer to use a higher protein variety with lower yield. Therefore plant breeders go for yield, not protein. The tomato canneries' contracts with farmers govern all the inputs and require delivery of a particular type of tomato at a particular time. Again, breeders comply with the demands of the farmers for just the right tomato. In summary, because farmers are a small, although essential, part of the production of foods, the conditions of their part of production are set by the monopolistic providers and buyers of farm inputs and outputs. The agricultural research establishment, by serving the proximate demands of farmers, is in fact a research establishment captured by capital. The farmers are only the messengers of messages written in corporate headquarters. Next we can ask, who benefits? For most of the period since 1930, farm productivity has risen faster than productivity in other sectors of production and much faster than production in services, which are a relatively poor sector in productivity. Who has benefited from this increase? The consumer has not benefited. The average price of food has risen more rapidly than the average of all prices. The ratio of food prices in 1970 to that in 1930 was 2.48, the ratio for all purchased goods and services was 2.33. So food has become not cheaper but relatively more expensive, even though farm productivity has risen more rapidly. It is very difficult to get reliable information on changes in nutritional levels. Studies are contradictory. The only major change in overall consumption of basic nutrients in the last 20 years has been an increase in fat and a decrease in carbohydrate consumption. There has been no long-term change since 1910 in proteins, and the information on calories is contradictory. People are not eating more and are not eating more cheaply. The farmer has not benefited. Total farm debt outstanding in 1910 was $800 per farm. In 1977 it had grown to $37,000. Of this 45 times increase, only 3 times is accounted for by inflation in the same period. Taking account of the growth in the size of farms, the debt per acre has grown from $3.50 to $91. This should be weighted against the inflationary change in average market value of farmland of $42 per acre in 1910 to $405 per acre in 1977. So debt rose from 13% to 23% of the value of real assets. The expense of farm production has gone from 48% of gross receipts in 1910 to 70% at present. Thus the pressure on farmers and the danger of bankruptcy from variations in price and yield are greatly increased. While the total value of farm real estate has exploded, this is paper value. Farms cannot be liquidated profitably in large numbers in one area, and they have represented a real liability at inheritance because of the inheritance tax. The risk of farm failure remains high, the hours long. For family farmers the conditions of work have improved to the degree that driving an air-conditioned tractor is better than sweating behind a mule. Net income per operator has increased 2.5 times since 1910, but much, if not all, of that is from elimination of the poorest farm sector, tenants and sharecroppers. Input and output capital enterprises have benefited. The providers of inputs have become very rich, not directly from increases in productivity but from the mode of those increases, high capital inputs. Seed companies are making very high profits and recently have been bought by the large chemical companies. The companies that produce herbicides, insecticides, and fertilizers have realized enormous profits. At this moment farm machinery providers, like the automotive industry, are in serious financial trouble, because machinery inputs have leveled off, replaced by chemical inputs. On the marketing side there has been a tremendous growth of grain and transportation companies, food processing industries, and supermarket chains, all of which have acquired very great capital since the Second World War. This sector, which has clearly gained from productivity changes, accounts for the slippage between increases in farm productivity and increases in the relative cost of food to the customer. Finally, we may ask why capital penetration in agriculture has taken this particular form, with monopolistic supply of inputs to and monopsonistic purchase of outputs from a vast population of small farm entrepreneurs. Why has capital not taken over the farms themselves? There are 4 reasons why it has not. First, purchase of farmland ties up huge amounts of capital that has low liquidity, no depreciation value for tax purposes, and uncertain market price, and that produces a low return on investment. Second, farming is physically extensive, so it is not possible to bring large numbers of workers and productive processes together in a small space. Third, for similar reasons the labor process is difficult to supervise and control. Fourth, the turnover rate of capital is limited by the annual cycle of growth, or even longer in the case of large livestock. The test of these assertions is in the exceptions such as poultry production, which is vertically integrated by large capital entrepreneurs, that is, the same corporation operates at every level of production. The same firm produces many of the inputs, does the breeding, grows the birds, slaughters and processes them, and sells them en masse to fast food chains and supermarkets. Poultry takes little space and lends itself to factory organization of production, with depreciable capital equipment and an easily supervised labor process. Moreover, the cycle of capital does not depend on an annual growth cycle and can be compressed further and further. Indeed, a main focus of poultry breeding is to shorten the growth period, while holding constant the amount of feed consumed. Farmers, then, are a unique sector of petty producers who own some of the means of production but whose conditions of production are completely controlled by suppliers of inputs and purchases of outputs. They form the modern equivalent of the putting out system of the pre-factory era. They are the conduits through which the benefits of the agricultural research enterprise flow to the large concentration of capital. Because of the physical nature of farming and the structure of capitalist production and investment, this is a stable situation and must be understood not as an exception to the rule of capital but as one of its forms. Social objectives of agriculture. A second major factor determining development of capitalist agriculture is the goal of social control. The long-term strategy of Alliance for Progress, the World Bank, and other developers has been to create a technically progressive entrepreneurial rural bourgeoisie to replace both the older landed oligarchies and the semi-capitalist peasantries and remaining subsistence agriculturalists. This new class would cool out peasant rebelliousness and provide a more flexible base of political support for international capitalism than the present regimes. This perspective also guides agricultural research. The World Bank's discovery of the small farmer is paralleled by the new direction of the agricultural research network toward problems of rain-fed agriculture, marginal lands, and appropriate technology. Science in a revolutionary society must examine agriculture in its broadest context. First, agricultural planning must be integrated with an overall ecological perspective for all land use. Land that is not cultivated forests, wetlands, mangroves plays an important role in the economy of nature, a role that gets lost in the narrow cost-benefit analysis of profit maximization. Changes in land use cause changes in the relationships of water, weather, air quality, and wildlife. And agricultural technology alters more of the environment than just the land actually being farmed. Second, agricultural planning must pursue multiple goals, including production for food, industry, and foreign exchange, improvement of nutritional quality, protection of the health of agricultural workers and consumers, protection of the environment, a buffering against natural and human-made disasters, minimization of demands on resources, especially unreliable or costly resources or those whose production damages the environment, equitable partitioning of the population between urban and rural settlement, including provision of employment, promotion of social relations favoring cooperative decision-making, a long-range perspective, and political initiative, reduction of barriers between manual and intellectual work. The intellectual problems in organizing a suitable planning process are immense and will require new ways of integrating diverse kinds of knowledge and recognizing the inseparability of the natural and social. Third, because nature is complex, any intervention in the rich network of interacting variables is likely to have many indirect and unexpected consequences, some of which negate the original purpose of the intervention. The major failings of many bold schemes for improving agriculture have come about from the failure to recognize the intrinsic complexity of the system and its often contradictory behavior. The one problem, one solution approach simply doesn't work. For instance, consider the use of insecticides as part of the Green Revolution. In the laboratory, a new pesticide kills several specimens of a harmful insect. This suggests that application of the pesticide in the field will control that pest, reduce crop damage, increase yield, provide more food, and make life better for people. This effort is often ineffective or even counterproductive for many reasons. The pest may acquire resistance. Evolution can be very rapid under the intense selection of heavy pesticide use. Competitors of the major pest may move in to replace it. Outbreaks of these so-called secondary pests are becoming more common. Use of pesticides has resulted in mites becoming major orchard pests. Predators or parasites of the pest may decline. The predators are harmed in two ways: by direct poisoning and by the killing of their prey, so the prey, the target of the pesticide, experiences an increased death rate from poisoning but a reduced death rate from predators. The outcome may be either an increase or decrease of the pest, depending on the ways in which other species interact with these. Minor pests often attract predators and parasites to the crop, which then help control a major pest. If the minor pest is destroyed, damage to the crop may increase. The pesticide may kill soil invertebrates that do not affect the crop directly but are important for fertility of the soil. A drop in fertility increases the farmer's dependence on cash to buy fertilizers. Where terrestrial agriculture is closely interspersed with aquaculture, the pesticide may reduce pond productivity by killing fish, shrimps, or their food organisms. Pesticides poison farmers. There were some 1/2 million cases of pesticide poisoning in the world in 1972. Pesticides contaminate drinking water and impair the health of the whole rural population. Differences among peasants in access to pesticides and related technologies enhances rural inequality, class differentiation, and landlessness. Also, the availability of pesticides for particular crops encourages monoculture. An attempt to control pests should begin with an examination of the whole ecosystem in its heterogeneity, complexity, and change. This runs counter to the usual paradigm, reinforced by the division of labor in applied science, of isolating the smallest parts of problems and changing things one at a time. Fourth, nature cannot be homogenized and kept constant by massive inputs. The heterogeneity of nature is desirable. Mixed land use provides buffers against the unexpected, slows the spread of pests, and allows for management of the microclimate. It can improve local nutrition, spread the demand for labor, preserve soil fertility, reduce the danger of erosion, and lessen the need for long-distance transport of food. The goal of a mosaic pattern of land use is especially threatening to the developmentalists, who argue, we have just escaped from the chaotic heterogeneity of the minifundia and achieved the rational, easily managed homogeneity of industrial agriculture. Now you want to turn back the clock and prevent us from having what the advanced countries have achieved. We answer that the progression has been from the spontaneous heterogeneity of the minifundia, through the homogeneity of agribusiness, and can move on to the planned heterogeneity of an agriculture that is ecologically and socially more rational. We differ from the radical developmentalists in rejecting the managerial view of nature and the illusion of complete control, and in respecting the heterogeneity and interconnectedness of the world. Fifth, in contrast to both the backbreaking pre-industrial, labor-intensive agriculture and the capitalist high-technology, capital-intensive agriculture, we propose a gentle, thought-intensive technology in which the object of research is not to find new inputs but rather to find ways to reduce inputs. One need not be a Marxist to be interested in polyculture or biological control of pests. But only a revolutionary dialectical perspective fits the parts into an integral strategy. The following are elements of the technology we want to develop. The diversity of crops should be increased by domesticating of new species. A mosaic pattern of land use should be established combining field crops, perennials, orchards, forest, and agriculture in a way that benefits the whole region rather than maximizes production of each plot separately. The sizes of the plots would be determined by their effectiveness in preventing outbreaks of pests, which depends on the mobility of both pests and predators. For instance, some ants forage for prey as much as 10 or 20 meters from their nest. A forest-dwelling species of ants might control pests in adjacent fields that are 20 to 40 meters wide. Their mutual microclimatic interactions modify climate downwind for a distance of about 10 times their height. Water holding provides refuges for wildlife, convenience for labor, including compatible machinery. Farming techniques shall include crop rotation, recycling of crop residues, and encouragement of soil microflora and invertebrates to promote soil fertility. The pest control system would be based on a community of invertebrates and microorganisms within the plot that would be resistant to invasion. The system would include generalist predators, more specialized parasitoids, and endemic or introduced diseases of pests that would act if pest outbreaks escaped the control by predators. We would also search for insects that eat fungal spores and useful nematodes. Such a scheme does not trust to any magic bullet but is based on understanding the agroecosystem as a biological community. To maintain such a community, we would have to grow plants that provide nectar for adult wasps, protected nest sites for ants, and other such aids. Outside the plots would be refuges for birds and bats, which can cover large areas and catch insects in flight. We would establish polycultures, mixtures of plants that jointly maximize use of solar energy, have different nutrient requirements, suppress weeds, discourage pests, attract predators, and maintain favorable soil and above-ground microclimates. Plant breeding would be aimed at selecting plant varieties for their performance under these conditions. Animal genetics would work to strengthen the predators of pests. Organization of knowledge. The ecology of every farm is different, and the best combination of land use, crops, and interventions would have to be custom-built for each place. Such a goal is beyond the capacity of even the largest agricultural research and extension system. However, taking a new direction in science would include finding new kinds of knowledge. In particular, we seek a system that combines the detailed, intimate, often sophisticated but local and particular knowledge that farmers have of their own land with the generalized, more abstract and theoretical knowledge coming from research centers. One way to promote this is by undermining the class barriers between full-time scientists and farmers and the mutual suspicion that accompanies it. This is a political task. Also, we must recognize that science is not the only source of rational knowledge and understanding. All knowledge comes directly or indirectly from experience and reflection upon that experience. People have been learning about nature, social relations, and themselves since our species began. This popular knowledge has created the only sustainable agriculture the world has seen, a large body of herbal and medicinal knowledge, even common sense concepts of systems dynamics such as positive feedback, overshoot, and oscillatory instability long before they were formalized mathematically. Developmentalists are inclined to dismiss folk knowledge as superstition, but we oppose both the elitist contempt for that knowledge and the sentimental learn from the people attitude that believes anything a folk says. Along with this ideological struggle, we have to carry out epistemological research into exactly what kinds of knowledge and ignorance people have. Mexican anthropologists have been doing this in the peasant cooperative village, or ejido. And the Cuban meteorologist, Fernando Boydell, has been investigating the knowledge of wind held by charcoal makers, electric power line workers, and irrigation windmill operators, recognizing the need to translate their knowledge from their special craft jargons. Finally, we must organize local research activity by farmers and establish naturalist, ecological, and farming clubs, especially in the schools. In the revolutionary societies of the Third World, the need for a new kind of science is often obscured by the urgency of immediate problems and the shortage of scientific resources. Radical developmentalism is often in conflict with a more dialectical approach, but the conflict is softened by two circumstances: the opposing views are often held by the same people and the disagreements do not correspond to class divisions or economic interests. The outcome of these struggles is still in doubt. Developmentalism has on its side the extreme urgency the countries face in all areas of applied science, the linear progressivism that is a frequent vulgarization of Marxism, and the failure to struggle for a creative dialectical materialist approach to science. The dialectical approach is favored by a growing awareness of the failings of capitalist science and the inadequacy of its emulators, by the possibility of a long-range approach to problems, and by a still small revolutionary movement within science. When the foregoing essay was shown to Isidore Nabi, he pointed out that all the tendencies of agricultural research about which we have written have, in fact, been realized in the development of the wonder crop, Calaqua. One of the few really new food plants to be introduced into agriculture since the potato. Nabi was kind enough to provide us with his notes on this development, which we reproduce here. Calaqua, wonder crop for the millennium. Call-aqua, the only member of the family Neutrinulaceae, is a rare plant found in small scattered populations throughout the humid and semi-arid tropics. Many peoples are apparently aware of it. In Haiti it is called merde de terre. In the Anglophone Antilles, fool's turnip; in Puerto Rico, vaciolino, or mojon dorado. It is not cultivated anywhere, but native peoples of the coasts of New Guinea and Queensland always carry slabs of call-aqua with them when swimming in shark-infested waters. The fish are not repelled but simply will not eat anyone so equipped. In the past, however, it may have been used as food. Archaeologists have found seeds identified as call-aqua in strata 800,000 years old in association with bones of Homo decrepitus, an extinct relative of our own ancestors in which successive generations were of diminishing size until they finally disappeared. Homo decrepitus is a puzzling species, and scholars do not agree on the causes for its extinction. However, a recent intriguing theory is that because of excessive social welfare, they could not balance their budgets. The call-aqua story is a unique example of private initiative liberated from the constraints of big government. The USDA's International Germplasm Survey collected genotypes of call-aqua from Honduras, Lebanon, Grenada, and Diego Garcia and studied the basic genetics and agronomy of this remarkable root. The Upgill Cyanogen Company's Cytoseed subsidiary then introduced genes from each of these into a composite line named Prophet No. 6. Senior geneticist Albert Dirk explained that modern genetic engineering techniques were used instead of conventional crossing because Upgill Cytoseed has laboratories equipped for biotechnology but no greenhouses for growing plants to maturity. Upgill then patented the species. Call-aqua is uniquely easy to grow. The tough, heavy, spear-tipped seeds can be spread by airplane over land that has not been previously prepared. The seeds penetrate even the rockiest soils and develop quickly into an odd-looking giant root that grows 1/3 above ground and is capped by 4 rubbery leaves. The root is covered by a thick outer skin of fine irritating hairs that give off an unpleasant odor. The root itself is 100% nutrient-free. No fertilizer is required since the plant contains no protein or minerals. Furthermore, it is completely pest-free since no insect or fungus could develop on it. Call-aqua's unusual biochemistry allows it to resist all known pollutants, heavy metals, industrial wastes, and carcinogens. All substances in its environment are absorbed and stored without transformation in small nodules in the root, giving it a grainy texture. Call-aqua grows rapidly and may be harvested whenever the market is favorable. Harvesting is most easily done with the new Updeer bulldozer blower combine, which loads the field onto conveyor belts where giant fans remove the soil as the call-aqua moves toward market. In this period of economic uncertainty, a major incentive for the production of call-aqua is its guaranteed and limitless market. The federal government plans to purchase 2 million tons a year to be distributed as aid to developing countries under the new Food for Freedom program, which also includes Twinkies and Green Berets. Recipient countries will undertake to build permanent port and processing facilities and to educate the consuming public. Further, when the aid is phased out after 5 years, the developing countries will continue long-term purchases with credits provided by the Bank for International Hegemony. BIH economists note that unlike other crops, for which demand saturates at some asymptote, there is no limit to potential consumption of call-aqua since it passes rapidly through the body and never satiates. In addition, it has a number of special markets. The USDA has declared call-aqua to be a vegetable within the norms for the school lunch program. A major European corporation plans to incorporate call-aqua in its new infant formula, while the New England Board of Reform Rabbis has decided that call-aqua is a non-food and therefore suitable for Yom Kippur use. It is rumored that a trade delegation from China is negotiating a long-term purchase of call-aqua as part of the 3 modernizations. 10. Applied Biology in the Third World, the Struggle for Revolutionary Science. This chapter is based on a paper presented at the Gramsci Institute, Palermo, Italy, in October 1983. D. E. Bates. about the nature of science in the Third World are very different from those in Europe and North America. In the industrial capitalist countries, science is already deeply entrenched in institutions, intellectual life, public policy, and technology. It is a fact of life. Even debates about science policy accept science as given and argue mostly about the uses and abuses of or access to science. Modern science was created in these countries. If the earlier glow of a science linked to liberation has become increasingly tarnished, there is still pride in its achievements and nostalgia for its promise. In some ways, the fate of science parallels that of bourgeois democracy. Both were born as exuberant forces for liberation against feudalism, but their very successes have turned them into caricatures of their youth. The bold, anti-authoritarian stance of science has become docile acquiescence, the free battle of ideas has given way to a monopoly vested in those who control the resources for research and publication. Free access to scientific information has been diminished by military and commercial secrecy and by the barriers of technical jargon. In the commoditization of science, peer review is replaced by satisfaction of the client as the test of quality. The internal mechanisms for maintaining objectivity are, at their best in the absence of sycophancy toward those with prestige, professional jealousies, narrow cliques, and national provincialism able to nullify individual capricious errors and biases, but they reinforce the shared biases of the scientific community. The demand for objectivity, the separation of observation and reporting from the researcher's wishes, which is so essential for the development of science, becomes the demand for separation of thinking from feeling. This promotes moral detachment in scientists which, reinforced by specialization and bureaucratization, allows them to work on all sorts of dangerous and harmful projects with indifference to the human consequences. The idealized egalitarianism of a community of scholars has shown itself to be a rigid hierarchy of scientific authorities integrated into the general class structure of the society and modeled on the corporation. And where the pursuit of truth has survived, it has become increasingly narrow, revealing a growing contradiction between the sophistication of science in the small within the laboratory and the irrationality of the scientific enterprise as a whole. Euro-North American science, like democracy, has been marketed to much of the Third World. Its advocates praise its values, bemoan its deficiencies, and assert its superiority over all alternatives. But if European and North American science is already a caricature of the science seen by its enthusiastic advocates, it comes to the Third World as a caricature of that caricature. Science appeared on its shores as the technology of conquest. Knowledge of plants and minerals provided the means of exploitation, and every new advance in the understanding of soils or flora allowed new and deeper penetration by the colonizers. Even the disinterested collecting of specimens or artifacts was a plundering of resources for the enrichment of the intellectual life of the metropolis. It filled their museums. British plant breeding increased the yield of the rubber plant tenfold, making possible the plantation system in Malaya. Sugar technology meant slavery. Research in tropical medicine was aimed first at protecting the health of the administrators and their troops. Later, when the high mortality of laborers could no longer be replaced by recruiting immigrants, medicine turned to diseases that impaired labor efficiency. Finally, in the wake of colonial rebellion, public health became an instrument of pacification and was closely tied to private health industries as a new profitable investment. Science came into the Third World as a rationale for domination with theories of racial superiority, of progress, and of its own intellectual superiority. If in the first instance one could speak of the expansion and conquest as a result of the technological superiority of some peoples over others, in a second stage the technological superiority and the greater military capacity was made synonymous with rationality, and in the final stage the rationality was no longer presented as a cause of the domination to be converted directly in its justification. The historic fact of European expansion is transformed into a natural phenomenon, a necessary consequence of the expansion of reason over the world. A rationality was transformed into rationality. A way of knowing was transformed into science, a procedure for knowing became the scientific method. The vast enterprise of dominating the world in a few centuries was sufficient argument to demonstrate the imposition of European reason as a universal and necessary development. Finally, science entered the Third World as a form of intellectual domination. After the troops depart, the investments remain. After direct ownership is removed, managerial skills, patents, textbooks, and journals remain, repeating the message that only by adopting their ways can we progress, only by going to their universities can we learn, only by emulating their universities can we teach. One student of science development even calculated the optimum structure of a research establishment for Latin America by averaging the ratios of full professors to associate professors to assistant professors to graduate students and technicians for all the countries of Western Europe and North America. It is our thesis that many of the critical theoretical issues, the class versus universal nature of science, its relation to other kinds of knowledge, the role of the dialectic in natural science and of class struggle within science, which are treated as philosophical problems in Europe, will be fought out in Third World countries as part of the political struggle for complete, real independence and as part of the struggle to build science in socialist countries. There are four main approaches to science in the heterogeneous assemblage of colonies, semi-colonies, neo-colonies, and former colonies with different degrees of independence, which we refer to loosely as the Third World. These approaches differ in the ways they cope with the contradiction of science as imperialist domination/science as progress. The least critical approach is sycophantic pragmatism. It accepts not only science but also its agendas as progress. It considers that a fully developed national science is a luxury incompatible with Third World poverty and therefore opts to limit research investment to narrowly defined secondary modifications of the results of world science, to local research and development. This approach is common in the most colonized of Third World countries. Its consequences are reinforcement of economic and intellectual dependence, economic policies based on subordination to international capital, intellectual dependence, and often the emigration of scientists who want to do fundamental research on a world level. The next two approaches are developmentalist. Developmentalism looks at progress as occurring along a single axis from less to more. The task of the less developed is to catch up with the more developed and even surpass them on their own terms. Developmentalists are uncritical of the structure and ideology of science, although they see that in foreign hands science may work against national interests. Therefore they seek an independent example of world science. There are conservative and radical branches of developmentalism with very different social bases and political perspectives. They share the view that science is progress, but they differ about whom the progress is for. The conservative branch of developmentalism is strongest in countries where a national bourgeoisie is in power. They are allies but not tools of imperialism, manifesting an entrepreneurial nationalism while oppressing their own peasants and workers. This branch is also powerful in countries where a colonial civil service became a ruling bureaucracy in a relatively smooth manner and aspires to become a national bourgeoisie. Conservative developmentalism faces a contradiction. Maintaining a competitive position requires encouraging scientific creativity. It needs universities in which not all students concentrate in law, medicine, or civil engineering. But universities are also dangerous when students are encouraged to think. They may think about things you don't want them to think about. Different regimes have attempted to solve this problem in different ways. Specialization in academic pursuits is one strategy. A compartmentalized knowledge means not only disciplinary specialization and the differentiation of the scientists among themselves, but also the impossibility of a connected grasp of reality and a critical judgment of it. The application of the specialists to the study of small realities, connected to whole at best by abstract and formal relations, impedes the critical evaluation of this totality. This specialization is achieved by stressing applied physical sciences, engineering, and mathematics, as in Brazil, abolishing whole academic departments, such as philosophy, or founding private scientific technical colleges physically removed from the ferment of the national university. But such specialized education is not only a question of curriculum, it carries with it a view of the world as well. Specialists begin to see nature as subdivided into domains that parallel the table of organization of their university, ministry, or company. Problems are recognized, but in isolation from each other, to be solved by separate interventions that leave the whole unchanged. Thus to the technocratic specialist, malnutrition is treated with dietary supplements, pollution, with standards for each molecule, pest problems with the right poison. Impressed by the importance of precise scientific information, the technocrat is equally adamant in refusing to pursue a problem beyond the narrowest possible boundaries of his or her speciality and in refusing to allow considerations from the broader areas to inform his or her own work. Conservative developmentalist regimes also make use of direct force. The alternate subsidizing of universities and military intervention in them has spread Argentine scholars all over Latin America. The more secure regimes can adopt a strategy of co-optive liberty in which scientists can think and discuss all questions within the confines of the national university and can publish scholarly tracts, but cannot circulate their conclusions as popular pamphlets or organize to carry out their programs. This strategy results in a curious kind of abstract applied science in which innovative plans are created to improve agriculture, promote health, and protect the environment, with the tacit understanding that they will never be put into practice. Radical developmentalism starts from different political premises. It is anti-imperialist, committed to serving the people, even socialist. Radical developmentalists accept part of the critique of science, that it has become commoditized, that it is used for profit and war, that it tries to monopolize knowledge. Radical developmentalists want a national, fully developed science with an agenda determined by the needs of the people. They typically promote the popularization and participation in science, and they open the doors to scientific education to everyone. They call for expanded health services, improved standards for occupational health, and conservation programs. In capitalist countries, radical developmentalists are dissident critical voices against the plunder of their national resources, against the hegemony of foreign intellectuals, against profit-oriented health services. But in revolutionary societies, where they are usually the dominant voice in science, radical developmentalists play an ambiguous and often harmful role. The ideology of modernization, of unidirectional progress has a powerful hold on their thinking. This often combines with a deeply felt sense of urgency to meet the needs of the people and results in a narrow pragmatism, the promotion of specialization, and the enthusiastic adoption of the already proven successful methods of production and of research. They are impressed by the flashiness of advanced science. This approach allows them to plant monocultures of timber to get wood for housing as fast as possible, but it underestimates the dangers of pest outbreaks. They will clear forests to plant food for the people and dismiss the warnings of erosion. They will import toxic pesticides and hope to prevent poisonings by improving protection of farm laborers, but they remain unconvinced of suggested ecological impacts. The one major difference between the short-sightedness of radical and that of conservative developmentalists is that the radicals have no real interest in hiding the harm caused by modern technologies, while the conservatives have a direct or indirect commitment to corporate profit. Radical developmentalists can be convinced by argument that a course of action is socially harmful. Once they become aware of particular ecological issues, they are concerned. For example, at the first National Ecology Conference in Cuba in 1980, representatives of the food industry were the ones who raised the problems of environmental deterioration caused by the accumulation of rice husks near the mills and of mango seeds near juice factories. In contrast, the economically rational but socially irrational actions of the conservative developmentalists can be reversed only by political confrontation, in which scientific argument is merely one weapon. But radical developmentalism is unable to cope with the contradiction between science as growth of human knowledge and science as class product. They concentrate on the first part of the contradiction and reduce its opposite to a concern about the uses and abuses of science. The other part of the contradiction is represented by other movements separately, by the humanist and mystical anti-science ideologies. These approaches see only the oppressive, imperialist aspect of science and reject it more or less completely. They see quantification and abstraction as dehumanizing, and technological application of science as destructive. They counterpose a gentle, spiritual, or humanistic holism to the reductionism, compartmentalization, and aggressive exploitation of Euro-North American science, and often stress its foreign, alien character. Within the world Marxist movement, radical developmentalism has coexisted with the revolutionary, dialectical critique of science. It has been reinforced by that passive acceptance of necessary stages of progress which often passes for historical materialism. This approach is strengthened by revulsion at Lysenko's efforts to create a self-consciously distinct Marxist science, and by the role of international scientific cooperation in promoting peaceful coexistence or fighting hunger and disease. In Europe, radical developmentalism fits in with the Euro-communist plea for respectability and acceptance by saying, "See, we aren't really all that outrageous. We may differ within science but not about science, which is part of our common heritage. In fact, only we can free science to come into its own." In contrast to radical developmentalism is the revolutionary, dialectical critique of science, which attempts to recognize both aspects of the contradictory nature of science. Although Marxists have contributed to this critique as individuals, it has developed mostly outside of institutionalized Marxism in the context of the movements for feminism, the New Left, ecology, alternative healthcare, and radical science in industrial capitalist countries and around the edges of national liberation movements in the Third World. This viewpoint has not yet found a coherent, integral programmatic expression. Its main idea is that modern science is a product of the bourgeois revolution and the age of imperialism. It was created mostly by Euro-North American white middle-class males in ways that meet their own material and ideological needs, and it is supported, encouraged, and tolerated mostly by Euro-North American white bourgeois males. These conditions of its origin and existence cannot but penetrate all aspects of science. In particular, the social determination of science operates both locally and on a world historic scale. On the one hand, the science of each country is part of world science, a product of the international development of capitalism, and, on the other, it reflects the particular history of that country, its position in the international system, the origins and functions of its own scientific community. The result is not some homogenized universal science that smooths out national particulars, but rather a pattern of uneven development of science paralleling that of capitalism. We must understand this uneven development before we can engage constructively in international scientific cooperation. The science of the industrial capitalist countries is a privileged science, made possible by the economic surplus accumulated from the whole world. The abundance of physical resources, libraries, universities, and scientists permits both extensive research aimed at practical goals and theoretical explorations aimed at more general understanding of nature. But this science is crippled because it is subordinated to the general interests of the bourgeoisie and deprived of the opportunity of working toward truly human goals by commercialization, militarism, internal organization, and ideology. It is bourgeois science. The designation bourgeois is not a judgment of the validity of any of its conclusions but a recognition of its historical contingencies. Marxist scientists in the industrial capitalist countries share in the privileges afforded by the economic surplus. We cannot use these resources, however, to develop a science that really serves the long-range and global needs of our peoples. Our best analyses are often unrealistic, that is, incompatible with capitalist relations or implausible within the constraints of the dominant ideologies. In association with political movements we can struggle for improved health, more rational agriculture, and better environmental protection. And we can polemicize against the most oppressive ideological creations used to justify oppression. At the same time, we are free of the daunting responsibilities of constructing the new socialist societies, which dominate the lives of our comrades in the revolutionary countries. This isolation and privilege allow us to pursue investigations and to elaborate theory in a way that is often quite general, subtle, and powerful, but that is also condemned to over-abstraction. Third world science is also incomplete and one-sided. It is limited by lack of physical resources, libraries, and communication with world science. It suffers from the intellectual hegemony of world science. In the capitalist Third World, science suffers from the simultaneous under- and overproduction of scientists, underproduction compared to the country's needs but overproduction in relation to the country's capacity to equip and support science and to carry its research results into practice. It is distorted by the process of recruiting scientists into a civil service where upward mobility is conditional on prudence before daring. The revolutionary societies of the Third World have the same shortage of resources, an overwhelming disparity between the urgent needs of the people and the limited material and intellectual resources to meet them. The planners' Marxist intellectual commitment to long-range and global issues comes into partial conflict with this urgent political commitment. When Marxist scientists from industrial capitalist countries and revolutionary Third World nations collaborate in socialist development, we bring different strengths and weaknesses, and we are equally products of our very different social conditions. The typical errors of those from capitalist countries are over-abstraction and long-range concerns. Marxists from revolutionary nations are more likely to err toward pragmatism. We meet to build a solidarity against two common distortions. On the one hand, the repetition of old patterns of Euro-North American arrogance and domination, complemented by Third World deference toward the advanced and titled experts and, on the other hand, the guilt-driven passivity of the Western scientists complemented by the revolutionary nationalism of the host country. The basis for cooperation is that world science, although concentrated in some countries, was made possible by the labor of the whole world and legitimately belongs to all peoples. Revolution anywhere in the world is heir not only to the history of struggle of that people but also to over a century of international political and intellectual struggles. Therefore the revolution belongs to all of us who oppose imperialism and fight for socialism. A central task for a Marxist program of international solidarity in science is to examine the contradiction of science as class product/science as progress in human knowledge, to recognize the historicity of science and therefore not to assume that the science developing now in the Third World must recapitulate the history of Euro-North American science. We have to raise anew the questions of conducting practical research in a fundamental way, finding the appropriate subdivisions of the sciences, reconciling the conflicting needs for specialized knowledge and broad overview, integrating professional and popular knowledge, and training revolutionary scientists. Scientific collaboration is the locus of both cooperation and conflict. When Marxist scientists work with non-socialist scientists in the UN, or in national and private development or aid programs, the relationship is one of cooperation within conflict. The cooperation is founded on a shared scientific culture and the stated objectives of the programs, say, improving health or agriculture. But this takes place within a conflict, while we see the struggles for health and agriculture and environmental protection as aimed toward building a new society with basically different relations among people and with nature. The sponsors of these programs see them more as means to preserve the existing societies. The working scientists usually do not deal with these global objectives but, rather, see themselves as pursuing humanitarian, non-political objectives such as reducing hunger. But a precondition for their employment is that they will pursue these goals subject to the constraints of realism. Nutritional programs must not ask about the distribution of wealth. Plant pathologists do not touch land tenure. Agricultural economists assume production for profit. At different times the cooperative or the conflictive aspects may be in the forefront, but the basic relationship is one of cooperation within conflict. On the other hand, relationship between revolutionary scientists of industrial capitalist and socialist Third World countries is one of conflict within cooperation. The cooperation derives from the common goals of building socialism and opposing imperialism. The conflict arises from our different experiences within our own societies. While those who have been excluded in the past from world science stress the need to join in and share its fruits, we who have been immersed in the most modern bourgeois science are more impressed with the need to criticize it. While socialist planners suffer from the lack of expertise in hundreds of specialties, we are more aware of the oppressiveness of the cults of expertise. While they see the production of scientists with advanced degrees as triumphs of human labor and therefore honor titles as measures of progress, we more often see the degrees and titles as part of a system for the regulation of privilege and co-optation and therefore often scorn them. While we struggle for a science that negates the most oppressive features of the scientific life of our own countries, our comrades have a greater sense of the urgencies of their nascent economies. These differences are of course neither universal nor absolute, and listing them is already a step toward resolving them. But they indicate some of the dimensions of conflict within cooperation that must be understood as a prerequisite for effective international solidarity. Needless to say, the processes of conflict within cooperation are possible only if embedded in the broader solidarity of anti-imperialist struggle. This critique, unlike more nationalist responses to science, does not automatically reject the findings of science as false or irrelevant because they are foreign or historically contingent. But it insists that that contingency must be explored at each point before decisions are made about what to adopt from world science. For the revolutionary societies of the Third World, the major problems of applied ecology in Third World countries are linked to agriculture, public health, environmental protection, and resource management. Here we concentrate on agriculture and refer only briefly to other areas. The pragmatists and the conservative developmentalists agree in their approach to agriculture. A modern, progressive agriculture would attract foreign investment through agribusiness, transfer and adapt a capital-intensive high-technology approach based on plant breeding, chemical fertilizers, pesticides, irrigation, and mechanization, and draw the peasants into the national and international market through specialization in cash crops. The political goals are the creation of a technically progressive and aggressive rural bourgeoisie, to be the political base of support for dependent capitalism, and a rural proletariat, which may struggle for economic goals but may not challenge the system. The increased food production or earnings on exchange would cheapen wage goods in the cities as well. This model for agriculture has been implanted unevenly in many areas of the Third World and has been subject to many kinds of criticism. Most of these criticisms apply also to the industrial societies, but they are especially important to the Third World. First, high-technology agriculture destroys its own productive base. Increased erosion, lowering of water tables, salinization, compaction of soils, depletion of nutrients, and destruction of soil structure are threatening agriculture everywhere, but under the tropical conditions of most Third World regions, these problems are exacerbated. In more prosperous regions they can be hidden for a while by increased investment. In regions of deep soils and adequate rainfall distribution, they can be ignored for decades. But in the fragile habitats into which commercial agriculture is expanding, this is less possible. It must be recognized that capital-intensive high-technology agriculture is an ecologically unstable system. The high-technology monocultures increase the vulnerability of production to natural and economic fluctuations. The plant varieties developed for the Green Revolution give superior yields only under optimal conditions of fertilizers, water, and pest management. They have been selected to put most of their energy into grain rather than vegetative parts, and the resulting stout dwarf stems make it easier for weeds to outgrow them, making herbicide use mandatory. Their reduced root growth increases the plant's sensitivity to a shortage of water. Irrigation buffers the crop against the vagaries of rainfall but increases the farmer's sensitivity to the price of fuel. High nitrogen fertilizers and the growth-stimulating effects of herbicides make the plants more vulnerable and attractive to insects. The use of fertilizers offsets local variations in soil nutrients but makes fertilizer prices part of the environment of the roots of plants. And monoculture removes diversity as one of the traditional hedges against uncertainty. Despite modern agricultural technology, crop loss to pests has not been reduced since 1900 and probably is increasing. With increased areas sown to a single highest yielding crop, more species of pests invade the crops. The use of pesticides often creates new pest problems by destroying the predators of pests. Commercial seed production reduces varietal diversity and disrupts the processes of local adaptation and diffusion that created our present crops. Modern technology adversely affects the health of populations. Pesticides are poisons. The World Health Organization estimated some years ago that 500,000 people are poisoned, and some 5,000 die from pesticides each year. Where government regulation of chemicals is weakest, where protective measures are not available, where children accompany their parents into the fields, where illiteracy makes warning labels irrelevant, where aircraft carry out the spraying, pesticide poisoning is at its worst. The diversity of crops has declined as farmers have opted for the most profitable product. Grass crops respond better to the new technologies and therefore have pushed out chickpeas and other legumes. Soybeans produced for cattle feed displace black beans, so protein production increases but available food protein declines. Selection of crops for total yield and measurement of the value of chemical inputs for their effect on yield often result in declining nutritional value of crops. Modern technology in agriculture under capitalism alters the rural class structure. Tenants are evicted and replaced by wage laborers who have no land for supplementing subsistence production. Land is increasingly concentrated, and the surplus rural people move to the cities, where they join the masses of the unemployed. Particular innovations have particular consequences. Herbicides replace hand weeding and therefore increase unemployment among women. Monoculture generally increases the unevenness of demand for labor. While young men are relatively free to follow the crop cycle, unmarried women with children are able to farm independently only on the basis of a crop mixture that spreads the labor requirements. And since new technologies are almost always made available only to men, technical progress in agriculture promotes sexist inequality. Modern agricultural technology results in environmental deterioration. Runoff of fertilizers leads to eutrophication of lakes. The added nutrients favor the growth of edible species of algae, which then decay, absorbing oxygen and leading to oxygen-deficient conditions that kill fish and invertebrates. Increased erosion speeds up the silting of lakes and ponds and increases turbidity, so production of aquatic life declines. Pesticides penetrate the whole ecosystem, killing wildlife, and often favoring not only agricultural pests but also disease vectors. When cotton, which is very dependent on pesticides, is introduced into new regions, malaria often increases. The promise of high yields encourages farmers to expand cultivation of annual row crops into forests, upslopes, and in general into more fragile habitats. Most agricultural development schemes attempt to overwhelm nature by technology and to dismiss indigenous knowledge, thus guaranteeing unpleasant surprises, undermining the capacity of farmers to understand what is happening, and reinforcing ideological domination. The intellectual foundations of modern agricultural science are dominated by short-range pragmatism, narrow specialization, and reductionism, which prevent the kind of broad vision that could anticipate the problems, which otherwise come as surprises. This viewpoint is rooted both in the prevailing philosophy of science and in the commoditization of science. The final, disturbing conclusion is that modern high-technology agriculture is a successional stage ecologically, an unstable relationship to nature that is rapidly running its course and must be replaced by a radically different system of production. But neither conservative nor radical developmentalists draw this conclusion. 11. The pesticide system. This chapter was first published in The Pesticide Syndrome. Edited by Linda Siskin. Understand the pesticide problem. We have to examine the three principal aspects of pesticides, as chemical substances that move through the environment in specific ways and poison living things, as commodities, produced and sold for the sole purpose of making profit, and as the products of research, reflecting the state of the art and the system of beliefs of the researchers as well as the way that research is organized. Pesticides are big business. In 1973, some $1,344 million worth of herbicides, insecticides, fungicides, nematicides, and rodenticides were sold in the United States, representing a physical quantity of 1.3 billion pounds, or between 1 and 2 pounds per acre for the whole country. Production is controlled by perhaps 80 to 100 primary manufacturers, including such giants as Shell Oil, Mobil, DuPont, Monsanto, Tenneco, Merck, Ciba-Geigy, American Cyanamid, and Union Carbide. Their products are then formulated by about 1,800 companies, which market them to dealers or directly to consumers by mail order. It is expensive to develop a new pesticide. Hundreds or thousands of potential products are screened for each one that eventually enters the market and thence the biosphere. Research managers estimate that it costs $8 million to $10 million, spread out over 5 to 10 years to develop a product. Once released, it competes with other products aimed at the same pests. If successful, it becomes a target for Me Too research by other companies, which look for ways around the patent or wait until the patent runs out. Since pesticides are commodities, they will be developed and produced only if they promise a good profit. Not only must they sell, but the rate of return must be at least as good as that from alternative corporate investments, improving production efficiency, bribing bureaucrats, intensifying sales efforts, renting a military junta, opening a car rental business, or buying a seed company. To be competitive, a new pesticide must have an expected market of some $10 million to $12 million annually. This means that it must be directed at a major pest of a major crop or must be a broad-spectrum poison. Any delay in the licensing of a product, or any demand for more complete testing of toxicity or environmental impact raises the costs and cuts into profit. Therefore, the corporation is resistant to learning about the environmental impact, reluctant to allow tight licensing regulations, hostile to environmentalists, and skeptical of alternative approaches to pest control. It will express these attitudes in its public relations efforts, allocation of research funds, briefs before hearing boards, presentations at professional associations, and articles in trade journals. The result of the search for ways to turn oil into commodities that farmers will buy is usually a broad-spectrum poison with the following major properties. 1. It must be a poison, toxic at the recommended rate of application. 2. It must be soluble in the spray materials at the levels that will be used. 3. It should be persistent enough to effect a kill, but as complaints about unintended impact became more common, there is an advantage to more toxic and less persistent materials. Pesticides have 3 important properties. First, they turn into something else. Either after being absorbed by organisms or in the soil, under the influence of light and bacteria, the original molecules are transformed. At first, the disappearance of a pesticide was taken as evidence that it was no longer having an effect. But we now know that aldrin turns into dieldrin in the soil, and that after being absorbed by plants, some herbicides become mutagenic. Therefore, evaluating the impact requires tracing the chemical transformation of the pesticide. Second, they are toxic, and the broader the spectrum, the less predictable the scope of their toxicity. Further, there is a tremendous variation in the susceptibility of organisms to a pesticide according to species, stage of development, physiological state, and environment. Some effects are immediate and some show up only gradually or under special circumstances. For instance, DDT is fat-soluble and therefore accumulates in the fatty tissues of animals. The fats are broken down during critical stages and during starvation. At other times it is held isolated from vital organs and is more or less tolerated. Third, they move through the environment, which itself is very variable. Even over very short distances there are differences of soil temperature, dry spots and moist spots, particles of sand and of decaying organic matter, and a tremendous diversity of chemicals. Each pesticide has its own pathway of movement. Some dissolve in water and soak down into the soil or are washed off the fields by rain, some do not dissolve in water but adhere to soil particles and are wind-blown. Some concentrate in plants. But in all cases they are distributed very unevenly, so in some places the concentration is 1,000 times greater than the average, and in other places it may be almost totally absent. To be effective, most pesticides must enter the bodies of the pests. Before and even after they die, the pests move around, often over long distances, and may be eaten by other organisms, who also move around. Therefore, the impact of the pesticide on the ecosystem may be far removed from the place of application. Farmers use the best methods of pest control available to them, but what determines what is available? The methods of pest control that have been used over the last 3 or 4 decades are the product of the combined research efforts of private industry, the Department of Agriculture, and the state universities. For private industry, the direction of research is dictated by the goals of direct profitability, certainty, and breadth of market. The public laboratories have quite a different assignment, yet until recently their research effort in pest control was not too different from that of the chemical industry. For one thing, the strategy of the U.S. Department of Agriculture has always been aimed at increasing the technological input into agriculture. Pesticides fit within that strategy. They seem to work, and they accorded with the philosophy of short-range pragmatism that dominates agricultural research. The entomology departments of the state universities worked cooperatively and shared a common culture with the chemical companies. This is not an exposé of scandal, if one accepts the role of private enterprise in the economy and the commitment to a modern, capitalist, capital-intensive agriculture. This collaboration was quite natural. The public facilities tested the pesticides produced by private manufacturers and used the fees charged to subsidize student fellowships. Industry gave research grants to entomologists. Extension agents echoed the recommendations of sales representatives. During most of the period in question, the bulk of pest control research and publications dealt with chemical control. So it is not surprising that we know a lot more about chemical than about biological control, and that the pattern of our knowledge and ignorance reinforce the pesticide treadmill. The USDA is not well known for self-criticism. It responded to Rachel Carson's book, Silent Spring, almost as angrily as the chemical industry. There is no evidence that the pesticides are harmful, and we knew it all along and are watching it closely. And if you never stood by when a farmer lost his crop to boll weevils, who are you to talk? And we have the most productive agriculture in the world, so shut up. When questions arise of possible harmful effects of pesticides, the defenders of the products always try to narrow the scope of the inquiry to their most immediate, direct, and measurable consequences and then downplay them. The critics of pesticides, on the other hand, urge that the ecosystem is strongly interconnected, highly variable, and vulnerable. Thus, debates around environmental impact become debates on philosophy of nature. Are things readily isolated or richly interacting? Is the average behavior of chemicals and organisms an adequate basis for decision-making, or must we be concerned with the unevenness of the world? Shall we be realists and stick to measurable costs and benefits, or shall we concern ourselves with all kinds of consequences of what we do? Gradually we see a confrontation of the worldviews of mechanistic reductionism and of dialectical materialism. But confronted with the question, if we can't use pesticides, what should we do? The critics of pesticides have only very general answers. The potential of biological and integrated control of pests is recognized, but the detailed knowledge needed for immediate practice is lacking. It is not that integrated control is inherently more difficult, but rather that the past history of research, as created by economic interest and theoretical biases, has conspired to give a pattern of knowledge and ignorance that reinforces the continued concentration on the search for magic bullets. Therefore, the struggle to change agricultural technology is also a struggle to change the direction of research, a change that can be imposed on the industry only from the outside by the direct and indirect victims of pesticides in collaboration with dissident scientists. 12. Research needs for Latin community health. This chapter is based on a talk given to a symposium on Latin community health at the Boston Area Health Education Center in September 1982. Here is at present no general theoretical approach to the health of Latin American communities in the United States. This is not surprising, since there is no general theory of the health of any community. We have clinical knowledge, procedures for diagnosing and treating the major life-threatening diseases, which are not unique to the Latin communities. We have statistics demonstrating the frequencies of causes of death among Latins and much less certain statistics on morbidity. These are still a long way from a description of the health pattern, although they do show special problems at the epidemiological level. We have some information on healthcare resources, or at least the institutional resources serving areas with concentrations of Latins. And, finally, we know that the major Latin communities in the United States, Chicanos and Puerto Ricans, are poor communities and that in a general way poverty is related to poor health. But we do not understand the structure of that poverty, nor do we know the specific pathways linking aspects of poverty with health effects. We can begin by establishing some prerequisites for developing such a theory. This will require a better characterization of the Latin communities, methodologies to cope with the special problems of gathering and interpreting information in those communities, and advances in the use of techniques for studying complex causation in changing systems. These techniques, which would be beneficial to public health in general, are perhaps especially urgent for public health work among Latins, Blacks, and Native Americans, groups that are experiencing rapid change and that, because of their poverty, are especially vulnerable to decisions made outside of their communities. First, the communities we are concerned with have not been precisely identified. Given the high mobility of people with unstable employment and the rapid changes in urban patterns, census data lags woefully behind the realities of Latin demography. The patchiness of neighborhoods means that attempting to use census tract data is like looking at the community through a warped mirror. Camade Frixas has shown that computerized searches based on Hispanic surnames are subject to a wide margin of error. On the one hand, Puerto Ricans have many names in common with other Spanish-speaking peoples and with the Portuguese. On the other hand, names such as O'Neill, Kahlberg, Galib, Pietri, Gautier, and Yambo are perfectly respectable Puerto Rican names of non-Spanish origin. Intermarriages result in mixed families that are partly assimilated either into or out of the Puerto Rican community, a situation that is not easily encompassed by formal definitions. The inclusion of the category Hispanic in the census still does not distinguish nationalities, although the demographic, economic, and social structures of, say, Cubans and Puerto Ricans are different. Nor does it include the children of migrants, who were born in the United States. The high residential and occupational mobility of Puerto Ricans interferes with epidemiological studies in two ways. First, people move away and drop out of longitudinal studies. Even if a sample includes Latins in proportion to the whole population at the start, they will be underrepresented at the end. Further, those who move may differ in important statistical characteristics from those who stay in one location for many years. We guess that those who move are a more vulnerable subpopulation, so longitudinal studies will tend to underestimate health problems among Latins as a whole. Second, most retrospective studies of environmental or occupational exposure to health hazards require sample populations who have been exposed for 5 years, or even longer for suspected carcinogens. Therefore, most Latin populations will be underrepresented in these studies both because of their high mobility and because the occupations in which they are concentrated also have high turnover rates. Two necessary conditions for an adequate description of the health situation of these communities are having permanent, transferable health records and taking a less atomistic view of the environment. While the general demographic considerations mentioned above affect the denominators of any epidemiological measures of frequency, the numerators are also often imprecise. Once we go beyond simple mortality data to morbidity, new problems arise. First, there are inconsistencies in reporting diagnoses. Second, the relation between clinically seen cases and total cases depends on many factors related to the availability of medical care, willingness to use it, and beliefs about what constitutes a legitimate complaint. School attendance records might be useful indicators of children's health if we knew what parents considered sufficient justification for absences and how often kids were kept home for other reasons or were absent without parental approval. The ratio of clinic visits for, say, Cardiovascular disease to mortality from those causes would be some indicator of the utilization of medical facilities by different populations, with a low ratio indicating underutilization. But all of these statistical approaches will ultimately lead to ambiguous results without more in-depth sociological investigation. And any such research is weakened by the common perception among Latins, which has often proved accurate, that giving true information to the institutions of society will result in harm to themselves. Therefore, we must find non-threatening ways for the Latin communities to help gather the necessary information. Health workers should be recruited from the communities, the health services should cooperate with community organizations, and health service workers should maintain informal ties with the communities they serve. The characterization of the Latin communities is flawed in a more serious way than by statistical biases. The usual sociological euphemisms, such as minority, disadvantaged, low income, or inner city, recognize only quantitative variations within the American population, obscuring qualitatively distinct situations. The fundamental reality is that all of the peoples included in these categories are oppressed peoples. They were either brought to North America involuntarily as slaves, or were conquered and expropriated in their own homeland, or were colonized and forced into migration by the colonial conditions of their homeland. Oppression produces a coherent and persistent pattern of exploitation, repression, and racism, which in turn generates conditions of high chronic unemployment, low income, unstable employment, unhealthful working conditions usually with little or no union protection, poor housing, abuse by police and other public institutions, high levels of residential mobility, and stress. These conditions are accompanied by a consciousness of lack of power, the expectation of unsympathetic or condescending treatment from educational, health, welfare, and other public institutions, and the experience of racist contempt for their culture and language. The Latin communities are not transitional communities. Puerto Ricans have been in New York since the middle of the last century, and since the massive migration began, several generations have grown up in the Puerto Rican dispersion. Yet the community persists as a historically continuous, culturally distinct, bilingual, oppressed people. Without a frank recognition of this reality, theories of Puerto Rican health and programs for health improvement will prove illusory. Toward a concept of environment. The Center for Disease Control makes a major distinction between factors of environment and factors of lifestyle. Presumably, the environment affects whole regions or occupations uniformly and is beyond a person's control, while lifestyle is chosen by an act of will and can be altered by conscious choice. We think this is a harmful dichotomy, not at all in keeping with the ecological viewpoint of environment. Ecologists see the organism as being in interaction with its environment. The organism actively selects its environment, modifies it, responds to it, and even defines it. Environment is not a passive out there, a given for everyone in the neighborhood. For instance, news of a blip in the stock market is very much a part of the environment of financiers but is not part of that of the unemployed, non-investors. Stress is increasingly recognized as part of the ensemble of risk factors, but what constitutes stress depends on who you are. Furthermore, environment is not a given, beyond people's reach. Although a single individual may not be able to improve air pollution in Boston, environment is not beyond the reach of collective social action. On the other hand, the activities of the individual, the so-called lifestyle choices, are not freely chosen. It is true in the immediate sense that people decide what they will eat, but food costs and time available for a lunch break, as well as access to vending machines and cafeterias, determine the choices that are actually made. At a deeper level, people's choices are influenced by their experience and beliefs as to whether they can control their lives. Those whose situation is such that history mostly happens to them and who have no sense of making history, those whose precarious economy limits meaningful planning to weeks, these people find it more difficult to act on risk factors that operate on a scale of years. Therefore, it makes sense to see particular environmental circumstances as determining the probabilities of various choices, which then become part of the person's environment. Any analysis of lifestyle must take into account the degrees of freedom available and the constraints acting on decisions. For dependent members of a household, the choices of those in charge constitute their environment. The dichotomy between environment and lifestyle has two other consequences. It separates into different categories the same physical factors, such as cigarette smoke and other factors affecting the lungs, which places obstacles in the way of a coherent theory of community health. And it opens the way to victim-blaming policy decisions by exaggerating the freedom contained in people's choices. In our view, the relation between choice and constraint was best summed up by the Godfather's proposal of an offer they can't refuse. The constraints on the lives of oppressed peoples present the limited choices available. Within those constraints they often make conditionally rational choices. For instance, a man's decision to smoke may increase his risk of heart disease and cancer in the long run, but as one of the few ways he has of coping with stress, it may save the lives of his wife and children. Our assumption of conditional rationality means that we cannot expect to change behavior by education alone. Rather, we must alter those circumstances that make such harmful choices seem optimal. Separating what is around an organism from what the organism does is also harmful in the study of occupational health, which is all too often limited to identifying chemicals in the shop. But working is not just a location, it is also activity, the pace of work, the degree of concentration required, the adequacy of toilet facilities, the duration of lunch breaks, the demands on particular muscles, the type of supervision, the monotony, the noise, the freedom to change position, and the temperature. All are part of the occupational environment. We need detailed information about how these factors interact in those occupations where latents are concentrated. Meanwhile, a good rule of thumb is that the more the conditions of work rhythm, pace, temperature, pattern of exertion, and so on deviate from the patterns of human activity during our previous evolution, the more likely that health will be adversely affected. Environment has its time course. Something that happens to the organism alters it in some way. The altered state may be permanent or may be gradually erased once the original stimulus is removed. For instance, one's nutritional state with respect to B vitamins depends on one's food intake over the last few days, while caloric reserves change over weeks to months, and the immune system reacts to and recovers from stresses on a scale of weeks. The inseparability of the psychosocial and the physiological. For more than a generation, the category of psychosomatic has been recognized as an attempt to bridge the gap between everyday physical medicine and psychiatry. However, all too often it has been used as a dismissive term, a way of handing a problem back to the opposite discipline. More recently, the interaction of physical medicine and psychiatry has been assigned more precise content. It has been recognized that a person's social experience and consciousness can act on the autonomic nervous system, the endocrines, the immune system, and therefore on health. One line of work has focused on stress. Emotional and physical trauma may lead to suppression of immune responses on a scale of weeks, to increased vulnerability to cancer and heart disease over a longer period, and to a concept of generalized risk of impaired health in general. A second line relates personality types to risk, the most popular expression of this being the recognition of type A and type B behavior in relation to heart disease. This individualistic approach usually takes personality as given without looking into the genesis of personality. Another approach recognizes societal events as traumatic, for example, unemployment rates related to suicide by way of depression. Applying these studies to Latin communities requires several changes. First, the community scales of stress must be calibrated for the different Latin communities and extended to include experiences common to those communities. The present scale includes events such as moving, but not migrating, eviction, or loss of job, but not chronic unemployment, death of a friend, but not awareness of another police shooting in the neighborhood. There are no items for a teenage pregnancy in the household, or a language barrier, racist insults, or society's hostility to people on welfare. Once identified, these experiences must be calibrated and quantified. As Karezek and others have shown, Stress alone is not a sufficient determinant of risk. A person who experiences a lot of stress but has a high degree of autonomy, of control over his or her minute-to-minute activity, will suffer less than someone with fewer degrees of freedom. The working and living conditions of Latin communities tend to deprive their members of many degrees of freedom that constitute the homeostatic system for coping with stress. The options of taking a short break, calling in sick, resting for a day or so, going to the movies or a restaurant, or working out at a gym are not generally available to people in these communities. The range of choices available, on the scales of minutes, hours, and days, is important in determining the pathways by which a stressful event percolates through the system and affects the health of the stressed person and the person's close associates. Does the stress end up as blood pressure or a snack and increased blood sugar, as smoking, or an angry outburst, as a day off or child abuse? The point is, in physiology as in ecology, everything goes somewhere. Where it goes will depend on the person's prior physiological state in terms of those experiences that legitimate or prohibit particular pathways. If stresses were essentially individual events, they would affect different people at different times, allowing the unstressed to take care of the stressed. But some economic and social stresses hit a whole community. Some people are affected directly, others by the perception of a threat to their well-being. This can have opposite consequences. If each person responds separately, the stresses can multiply and reinforce each other. One person's depression and lapsed child care may meet another's drinking while driving, thus increasing the accident rate. On the other hand, if the stress is shared as a community problem, collective efforts to solve it may succeed in ameliorating the problem or in creating a supportive atmosphere that cushions some of the consequences. A theory of stress must include community stress in relation to community structure. The conceptual framework of risk and disease requires separating independent variables from dependent variables. But the distinction between a risk factor and its consequences is not always clear-cut. For instance, a bout of disease may be a very stressful experience because of the anxiety it generates, loss of work, an unpleasant hospital experience, or other reasons. Then there is a reciprocal relationship of positive feedback. If this is the case, and if the positive feedback is strong enough, then the system is dynamically unstable. If a person is in good health for a while, then gets sick, this may act as a new stress, setting up for the next disease. The clinical record will show one disease after another, often of apparently unrelated etiology. On the other hand, if the positive feedback is less strong, each disease experience may be essentially an independent episode. In some cases, minor illnesses actually reduce risk, with an occasional day in bed serving as part of a homeostatic mechanism that paradoxically preserves health. Then the diagram would show negative feedback. The risk-disease feedback is an important part of a person's health pattern. It differs among people for many reasons and should be part of the epidemiological characterization of a community. Inseparability of occupational and community health. At the present time, occupational health and community health are separated administratively, covered by very different legislation, and usually practiced by different people, whose constituencies overlap only loosely. Even more damaging is that they are separated conceptually. From the viewpoint of community medicine, the workplace is an extraneous source of statistical noise, while from the occupational health perspective, home conditions are confounding variables. Yet people's lives are wholes. The lungs subjected to metal dust in the shop breathe hydrocarbons at home, the bus driver whose back is bounced and beaten and bumped at work may suppress anger at home by tightening his back muscles, the stresses occasioned by a sick child may increase the chances of a clothing worker driving an industrial sewing machine needle through her finger. Community and occupational health interact in several ways. The same specific insult to the body may take place at work and at home. Or the same organ may be assaulted through different pathways at home and at work. The stresses in one location may increase vulnerability to dangerous events in the other. Emotional stresses at home may reduce immunological responses to infection at work. A person may cope at home with work stresses by destructive mechanisms such as smoking, or may pass them on to spouse or children by physical abuse. Exhaustion on the job may mean less careful childcare at home and more accidents, or less energy for cooking and more reliance on prepared food. Stresses at home may show up as accidents at work. Diseases that develop or are discovered in one place may be ameliorated in the other. Leg circulation problems because of diabetes may lead to a recommendation that the patient be given work that does not require standing all day, or exhaustion at work may lead to a recommendation for more rest at home. But job specifications or family relationships may prevent the patient from carrying out these recommendations. From the perspective of allocating responsibility, evidence of an input from home is used to exonerate the working conditions and vice versa. What is needed is a way to trace causal pathways back and forth. From work to home, to look at such measures as total insult to the lungs or heart rather than judge each component by a separate set of tolerable levels, and to focus on interactions among health-affecting components and seek whole system modes of intervention. The unit of epidemiology is not the individual. Although most studies take the conditions of individuals as the basic dictum and then derive frequencies from this, in reality people live together in groups, usually family groups with some additions or subtractions. And what happens to one member of the family affects others. With infectious disease, this is most obvious. But chronic disease affects other members of the household through loss of income, emotional stresses, disrupted patterns of child care. The parents' conditions of employment, wages, stresses on the job, traveling time to and from work, unemployment may determine the nutritional status of all members of the household. Factors leading to alcoholism in one family can result in traffic injuries to members of another. When causal pathways crisscross from person to person, an individualistic model will regard most of the important events as external, whereas they are really part of the same network. That is the Latin reality. Healthcare and its utilization. Health professionals tend to consider the provision of medical services as being almost equivalent to a public health program. However, in many cases the most important contribution to the health of a community may be a tenants movement or a job program. Although medical services are not everything, they are obviously important. At present, emergency services at least seem to be widely available to urban Puerto Ricans and are willingly used, but other kinds of care are accessible and less utilized. In our view, it is important to understand the patterns of health service utilization, first, to get accurate morbidity information and, second, to plan for improved service. A useful starting point is a model in which the probability of someone getting health service depends on its availability and on the ratio of desperation to reluctance. The desperation comes from the perception of a threat to life or health and therefore depends very much on the person's beliefs about what illness is and what constitutes an acceptable part of life. For instance, is chronic fatigue part of life? Is it a sign of weakness to complain about it, or is it a legitimate medical complaint? The answer will influence the stage at which diabetes and other conditions are first diagnosed. The records of one Boston area clinic show a strongly skewed sex ratio in clinic visits, with women outnumbering men. This is most marked for minor ailments. As the seriousness of the condition increases, the sex ratio becomes more even. The skewing of the ratio is absent in children, appears suddenly in the teens when patients have autonomy to decide whether to seek care, and tapers off after retirement or unemployment. Reluctance to seek medical care is strongly related to the loss of time or wages. In addition, expectations about the outcome of a visit and availability of alternative curative or supportive resources will influence the decision. Any strategy for improved health care must deal both with people's beliefs about illness and with the real economic and emotional penalties attached to using clinic facilities. Conclusions. An ecologically sound, comprehensive approach to the health of the Latin community must combine sociological and medical understanding of the specific experiences of Puerto Ricans as emigrants from a colony, of the general conditions affecting all oppressed peoples, and of the nature of the linkages between external events and human physiology that are relevant to all people. Research is needed to identify the latent realities, to trace the pathways of interaction among the workplace, the community environments, housing conditions, nutritional patterns, the ways in which stresses percolate through the system, the degrees of freedom people have for coping with stress individually and collectively, and the beliefs that promote or impede such coping. 13. What is human nature? Here is no more vexing and confused question in biological and social theory than the issue of human nature. What do we mean by human nature? Does it exist? If so, in what does it consist? The debates around the relationship of the human species to other animals have taken on very different significance at different times. In the 19th century the debate was between idealism and materialism. Idealism, represented mostly by theology, made the differences between us and them absolute, arising from separate special creation and the introduction of the soul. The materialists emphasized our links to the rest of the animal kingdom. And since for Darwinism the gradualness of evolution was a critical feature both for understanding and for demonstrating it, they stressed the continuity of human and primate evolution. Marx insisted that human history was part of natural history. By this he meant that the human species arose through its interactions with nature, that, like other animals, people have to eat and reproduce, and that human history should be understood not as the unfolding of great ideas or ethical advancement, but as the ways in which people act on nature to survive and the social relations through which production and reproduction are carried out. Engels developed the theme further in his essay The Role of Labor in the Transition from Ape to Man. Despite, or because of, his Lamarckian biases, Engels captured the essential feature of human evolution, the very strong feedback between what people did and how they changed. He saw environment not as a passive selective force external to the organism but rather as the product of human activity, the special feature of the human niche being productive labor and cooperation, which channeled the evolution of hand and brain. For Marxists the evolution of humans from prehumans and the inclusion of human history in natural history presupposed both continuity and discontinuous, qualitative change, but for most materialists evolution meant simply continuity. In our time, despite the recent upsurge of conservative creationism, the materialist view has prevailed. Now a new alignment has arisen in which the opposing sides are reductionism and dialectics. The reductionist view makes the continuity between human and prehuman evolution absolute, while dialecticians emphasize the emergence of evolutionary novelty. The reductionists, as biological determinists, see human affairs as the direct result of patterns that evolved in the past, which have created a fixed human nature that determines our behavior and social organization, to the extent that we depart from the natural at our peril. Discussions of human nature almost invariably arise from a political context, although the problem sometimes masquerades as a purely objective question about human evolution. No political theorist, not even the completely historicist Marx, has been able to dispense with the problem of human nature. On the contrary, all have found it fundamental to the construction of their worldview. After all, if we want to give a normative description of society, how can we say how society ought to be organized unless we claim to know what human beings are really like? Conservative political ideologues have no difficulty with the problem of human nature. For them all human beings have common psychic properties that are non-trivial determinants of the shape of human society. These attributes vary quantitatively from one person to another, thus determining their places in society. These properties exist as a consequence of the individual's biological nature, that is, they are coded in the genes. Since the individual is ontologically prior to the social organization, it is genetically determined human nature that gives shape to society. Wilson gives an explicit exposition of this theory. The biological determinist theory of human nature is logically consistent. The attack on the conservative theory of human nature has been not that it cannot be true, but rather that it is not true. The most superficial disagreement with conservative theory has come both from liberals and from the anarchist left. This position holds that there is indeed a biologically determined human nature and that a prescription for society can be written using knowledge of that innate nature, but that conservatives have simply got the details wrong. Whereas apologists for unrestrained competitive capitalism claim aggressiveness, entrepreneurial activity, male domination, territoriality, and xenophobia as the content of human nature, left anarchists give a contrary description, arguing as Kropotkin did in Mutual Aid, that people are really cooperative and altruistic underneath but have been coerced into competition by an artificial world. These critics agree with the conservatives that a basic set of attributes is natural to the human being as an entity in isolation, but that these attributes may be suppressed by societies that are either unnaturally cooperative or unnaturally competitive, as one's taste runs. A more subtle version of the human nature argument flows from classical Marxism. According to what little can be found in Marx on the subject, this theory holds that labor is the property that marks off the human species from all others, although it is not sufficient to specify the form of social relations. Human labor is marked by these features. It transforms the world of nature into a world of artifacts that serve human beings. This transformation is carried out socially rather than individually, and it is done by the producer first conceiving mentally the end to be achieved and the varied means of its achievement. Thus action is teleological. Labor is the use of tools and implements to effect changes of external objects by human beings cooperating to realize results which they consciously set before themselves. It is the planned domination of nature through social action. The transformation of nature and the creation of artifacts are, of course, characteristic of many animals. Birds build nests, and some even use sticks to fish out insects from holes. Moreover, ants and termites organize cooperatively to transform nature. What seems to be unique to humans is the conscious planning, the imagining of the result before it is brought into existence by deliberate teleological action. This last element is what marks off human labor from the activities of mere animals, although there is some suggestion, in Jane Goodall's observations, that chimpanzees deliberately choose sticks of the appropriate size to pull ants out of nests, that primates may also plan in a limited sense. Despite its origin in an expressly historicist philosophy, the classical Marxist view makes a curiously universal claim about the domination of nature. While it is undoubtedly true that human biology impels us to eat and drink at reasonable intervals and provides us with the material basis for meeting these needs by planning and generalizing, the degree to which human beings have attempted to dominate and transform nature, as opposed to taking it as it comes, has varied greatly. Kalahari Bushmen do remarkably little to alter the environment in which they live, although they are prudent planners in respect to consumption. It is by no means certain that the transformation from hunting and gathering to sedentary agriculture, and from agriculture to industrial production, is built into the human genome. For Marx, caught up in the fury of industrial change, and partaking of the 19th century belief in the inevitability of progress, the domination of nature seemed part of our innate makeup. Yet innate makeup is a most un-Marxist concept. A second difficulty with the orthodox Marxist view is that even if true, it is not very informative. It cannot be used to project any actual feature of human social organization, nor to say how that organization may or may not change. That is, it seems to confront the issue of human nature and promises to tell us what that nature is, only to provide a picture of human nature that is politically irrelevant. A general feature of the problem of human nature is that only very specific descriptions have political force, yet their very specificity leads quickly to their falsification from the historical and ethnographic record. Naive theories say too much, and sophisticated theories too little. A radical alternative has been to deny the existence of human nature altogether, at least in any non-trivial sense. Human beings are simply what they make of themselves. They are, in Simone de Beauvoir's Bon mot, beings whose being is in not having a being. In the hands of the existentialists, this denial of a nature leaves us with no way to understand human society, it simply is what it is. Yet even de Beauvoir was unable to hold this view consistently. At the end of The second sex. She wrote. When we abolish the slavery of half of humanity, together with the whole system of hypocrisy that it implies, then the division of humanity will reveal its genuine significance and the human couple will find its true form. The direct, natural, and necessary relation of human creatures is the relation of man to woman. Marx has said, the nature of this relation determines to what point man himself is to be considered as a generic being. As mankind, the relation of man and woman is the most natural relation of human being to human being. By it is shown, therefore, to what point natural behavior of man has become human, or to what point the human being has become his natural being, to what point his human nature has become his nature. So, the being without a being has a true being after all, as it must for de Beauvoir, who wants a conception of human nature to do political work for her. All meaningful theoretical questions are at the same time practical questions. Their significance may be a technological innovation, a therapeutic insight, or a guide to policy. But their practicality may be less obvious. They may contribute to our understanding of individual or collective selves, our notion of what can or must be changed, our capacity or necessity to act on the world, our aesthetic perceptions, our emotional responses. Or their practicality may be confined within a science and may guide how we pose other questions, plan research, or decide when we have an answer. Contrary to the positivistic notion that a question is legitimate if it is logically well defined, testable, and capable of being answered on its own terms without regard to application, we argue that a question is meaningful if what we do or feel is changed by the answer. Furthermore, it is often only by knowing what practice we are concerned with that we can frame the question in a meaningful way. For instance, we may ask, what is life? Our answers will be very different if we want to be able to distinguish organisms from rocks and furniture, or if we mean when is someone clinically dead, or if we are answering the right to life movement's question, when does life begin? The relation between inorganic and organic chemistry was important for the evolutionary question, could life arise from chemical processes alone? Usually when a large question of this sort is posed, it defies clear answer. New distinctions have to be made, and the question comes apart into many sub-questions. As one of our children used to ask when confronted with a new animal in a zoo or picture book, what does it do to children? The trouble with the question of human nature is that it is the wrong question. Partly the question reflects the analysis we bring to understanding human political and social life, and partly it carries a vestige of Platonic idealism. The evident fact about human life is the incredible diversity in individual life histories and in social organization across space and time. The attempt to understand this diversity by looking for some underlying ideal uniformity, called human nature, of which the manifest variation is only a shadow, is reminiscent of the pre-Darwinian idealism of biological thought. For Darwin's predecessors, the evident variation among organisms within a species was something to be ignored, to be seen through, in order to discover the underlying ideal form that the species represented. So human nature theory asks what underlying ideal of organization is lurking behind the apparent bewildering variety of societies. For biological determinists like E.O. Wilson, the uniformity is among individuals themselves, biological constancies dictated by the genes that determine the eventual shape of social institutions. For social theorists like Levi-Strauss, all societies have certain underlying structures in common, of which actual practices are transformations. These structures derive not from the genes but from somewhere else that is not specified but is presumably a consequence of social organization itself. The two common characteristics of all these theories are, first, they postulate underlying ideals that are common to all time and place, and, second, they locate causal forces, either in the individual or in society. They struggle over the dichotomies individual social and biological environmental. A dialectical point of view, however, rejects the ground on which these struggles are fought. First, it accepts as primary the heterogeneity of individual life histories and of social developments. Far from seeing the variations as obscuring or even illuminating the underlying uniform ideal, it assumes the contradictions within and between societies to be the motive force of human history, so that the heterogeneity itself becomes the proper object of study. Second, a dialectical analysis does not ascribe intrinsic properties either to individuals or to societies but stresses the interpenetration of individual and social properties and forces. An example of the error of the Cartesian ideal analysis is the claim that the alternative to believing in an inborn biological human nature is believing that we are all born as tabulae rasa, on which society writes its message. There is a glaring logical error here, however. The evidence offered by biological determinists that we are not clean slates at birth is the evident variation in temperament and activity in newborns, even within the same family. But this evident variation is taken as a demonstration of an inborn uniform human nature. Clearly we are not tabulae rasa. But that fact has nothing to say about human nature. The error arises from the philosophy that there must be an underlying uniformity and that it must be either innate or imposed from the outside. Since the variation among babies is innate, then the postulated similarities must also be so. The physiological needs of human beings, as well as their vulnerabilities and ways of coping with the environment, are very similar to those of other mammals. We need food a lot more than reptiles do because we have to keep body temperature within narrow limits, but gram for gram a lot less than mice because we are large mammals. We need specific nutrients, some of which are also needed by other animals, and some of which, like vitamin C, are peculiar to us because our bodies have lost the capacity to produce it. We require an environment in which we can maintain our body temperature. We are vulnerable to toxic materials and subject to invasion by parasites. Like the porcupine, however, we are relatively free of predators. We respond to stress in the same way as other mammals: increased flow of adrenaline, higher blood pressure, more rapid heartbeat. And, like other mammals, the regulation of breathing, circulation of the blood, digestion, and other functions are mediated by the secretions of glands and the unconscious activities of the autonomic nervous system. But all of our physiology is transformed by our social existence. Breathing is concerned with getting oxygen to our tissues and getting rid of carbon dioxide, but our manner of breathing depends in part on how we cope with stress. Tight, shallow breathing leaves sections of the lungs unused and increases the chances of respiratory infection. And what we breathe is the result of human industrial activity. Although breathing takes place without conscious intervention, people can control their breathing, and in disciplines such as yoga can learn to use the breathing pattern to influence other processes. All mammals live intensely, at high metabolic rates. We share with other mammals the mechanisms of temperature regulation: shivering, sweating, changing the distribution of blood between the body's peripheral circulation and the deeper organs. But we also use clothing and shelter and burn fuel to warm or cool us. The use of these cultural mechanisms to control our own temperature has made it possible for our species to survive in almost all climates, but it has also created new kinds of vulnerability. Our body temperature now depends on the price of clothing or fuel, whether we control our own furnaces or have them set by landlords, whether we work indoors or outdoors, our freedom to avoid or leave places with stressful temperature regimes. Thus our temperature regime is not a simple consequence of thermal needs but rather a product of social and economic conditions. After about 18 months, humans walk erect. Posture then determines the patterns of mechanical support and strains that influence the distribution of aches and pains in different parts of the body. But posture is very variable. Actors are aware of this and use their posture to identify the social class and sense of self of the characters they play. The mechanical stresses on the human body are not simply the passive result of anatomical changes that separate us from our closest mammalian relatives, but rather the embedding of posture into a social and psychological context. If ideas of human nature have any value, they must be able to cope with such biologically basic functions as eating and sex. Every human being eats and drinks, and all are the product of a sexual act. Indeed, the acquisition of food and of mates is considered by biological determinists to be the basis of all human individual and social behavior, since natural selection operates on differential survival and reproduction. Yet when we look at these biological functions, which we share with all other animals, we see how, like all physiological functions, they have become detached in human life from their animal significance. Eating is obviously related to nutrition, but in humans this physiological necessity is embedded in a complex matrix, within which what is eaten, whom you eat with, how often you eat, who prepares the food, which foods are necessary for a sense of well-being, who goes hungry and who overeats have all been torn loose from the requirements of nutrition or the availability of food. The ecologist, regarding Homo sapiens as a species with species characteristics, would classify it as an omnivore. It is certainly true that human dentition and the human digestive system make it physically possible for people to ingest and digest an enormous variety of plant and animal material. It is also true that Homo sapiens, as a collection of living individuals, has eaten everything imaginable. Yet it is a falsification of significant features of human existence to say that people are omnivores. Quite aside from individual idiosyncratic dietary differences, what people eat varies with geographical locality, historical changes, class position, sex, age, and many other factors, each in unique interaction with one other. Vast numbers of African peasants of the Sahelian region just south of the Sahara are virtually monophagous, being forced by a commodity system of agriculture to eat little else but millet. Mayan peasants ate almost nothing but corn and beans, as do their present-day descendants. There is some disagreement about how much wild game was in their diet and whether meat was distributed across social classes. British working-class housewives do not eat the same diet as their husbands, and Brazilian boias frias have a much more restricted diet than their employers. A fundamental ecological problem confronting all organisms is how to cope with the uncertainties of their food supply. The supply may change with the season, but also with weather conditions, often erratically. Their prey populations may peak and crash, parasites and infections may wipe out food sources, and wandering animals may encounter patches of abundance and scarcity. Animals cope with this uncertainty and variability in many ways. Some become dormant through the winter or dry season. Cold-blooded animals live slowly. Their nutritional state depends on what they've eaten over the last few months or weeks, so the fluctuations in food supply on that time scale average out, and day-to-day uncertainty becomes month-to-month reliability. Mammals and birds live quickly. They eat, process, and use up food within a day or even within an hour, so they are more vulnerable to environmental variability. One way to confront the uncertainty of food supply is to store calories as body fat. This is widespread, perhaps universal, among mammals but is subject to physical limitation beyond which the energy consumed or the awkwardness of carrying around extra weight overwhelms the advantages. Food can also be stored outside the body. Squirrels store nuts, ants gather seeds, and some ants store food in the bodies of a special caste whose abdomens swell with honey and which are consumed in hard times. External storage also has its limits. Food deteriorates, and a good cache becomes a target for microorganisms, insects, and rodents. People also can get fat and store food physically. But we have developed several new modes of adaptation, such as preserving food against decay by curing, salting, smoking, cooking, or refrigerating it. Yams, which do not store well, can be turned into pigs, which can be guarded until needed. People also redistribute food from household to household or village to village, providing some hedge against very local uncertainties on a scale smaller than the region of redistribution. This redistribution creates a network of social ties and obligations, so in a sense food today can be turned into food tomorrow by storing it in the form of social obligations that do not deteriorate with moisture. but once the food can be represented symbolically as obligations or money, two new features arise. First, accumulation no longer has natural limits imposed by the body's weight or the physical problems of storage. It is possible for the goal of accumulation to be cut loose from its nutritional base and become under some conditions an insatiable goal. Second, while non-commercial redistribution is a protection against the uncertainty of the environment, trade creates new sources of uncertainty. Fluctuations in the price of grain determine not only what is planted and how much, but also how the crops will be cared for, how much nitrogen or pesticide will be applied. And as the markets of the world become integrated increasingly into a single system, the flow of price information makes what happens locally dependent on what happens in remote regions, where neither rainfall nor wind conditions are the same. Although Canadian and Argentine weather do not influence each other, Canadian wheat does influence Argentine wheat. Market integration through the international flow of information creates interactions on a scale beyond even the most indirect ecological ones. Once the products of human labor become commodities, produced for exchange, they acquire a new set of properties beyond their physical and chemical structure or their utility. It becomes possible to produce without regard to human need, since products previously aimed at very different functions are now interchangeable as investments. Throughout history, what people eat has been determined by their place in their economy and the way in which that economy produces and distributes food. What people can eat is biologically determined. What they do eat is quite another matter. If what people eat is historically, socially, and individually determined, why they eat is equally so determined. Biologically, eating and drinking are the physical acts of nutrition. In actuality, eating and drinking have very variable relations to that biological necessity. Eating is a social occasion that cements family bonds, provides an excuse to carry on commercial exchange, and offers an opportunity to create mutual social obligations. We do not usually invite people to dinner to give them nutrition, nor do we ask them to come around for a drink to maintain their electrolyte balance. $100 a plate dinners sustain the body politic, not the body physical. What begins historically as an act of mere nutrition ends as a totally symbolic one. The cold lunch packed by the Israelites on their flight from Egypt became a feast packed with historical and religious symbolism as the Passover Seder, which through historical accident became a Last Supper, ending finally as an act of religious mystery, engaged in by hundreds of millions of Christians, with no nutritive consequences at all. In human culture there is not one meaning of eating and drinking, but the qualitative transformation of a single physical act into an immense array of social and individual meanings. The richness of meanings of food is surpassed by the ambiguity of sex. A remarkable naivete of socio-biological theory is its total confounding of sex, copulation, reproduction, and marriage. None of these is a necessary precondition of any of the others, not even copulation and reproduction, in a society with artificial insemination and in vitro fertilization in its repertoire. Marriage is a social contract entered into for reasons of property or religious ideology. Two people may marry because they love each other and want to commit themselves to each other, but the fact that such commitment takes the form of a marriage contract is a consequence of social arrangement. Sex is a form of love, of hate, of submission, of dominance, of religious piety, of commodity exchange, of the cementing of family bonds. Which of these it is depends upon individual life histories in relation to social class, sex and gender, political needs, and occasionally even the desire to reproduce. While no self-respecting biologist would confuse nutrition with reproduction, taking in food can certainly be a form of sexual activity. Again, meaning transforms a physical act. A study of the physical act itself, its biological preconditions, its evolution, its similarity to that behavior in other animals, or the regions of brain that influence it will simply be irrelevant to the human phenomenon. The diversity of meanings of actions that seem superficially to be biological acts also shows that a simple causal analysis of such acts must be incorrect. People do not eat because their genes tell them they must eat to survive, since the same person in a single day will engage in different eatings. Nor do they eat because there is a general law of social organization that dictates eating as the appropriate response to the desire for social intercourse. The well-off authors of this book do not often use meals as social occasions, although they used to, while people living on welfare can never do so even when they want to. Neither the individual nor society has ontological priority. Different slave families on the same plantation had very different numbers of children, with birth intervals that varied from 1 to 13 years. But the birth of a slave child was a completely different event from the standpoint of the slave family and from the standpoint of their owner. They are in fact two different reproductive events, one of a human life, the other of capital. The individual and the social interpenetrate each other. The individual life history is the particular pathway that the realization of forces takes, but the individual lives can develop only in the context of a social milieu. The ambiguity of subject and object, of cause and effect implied by the interpenetration of individual and social cannot be accommodated by Cartesian analysis, which takes as its first premise the alienation of subject and object. But if some universal human nature cannot serve as the measure of societies, if we cannot offer a prescription of a truly human society, what can be the objective of our political practice? What are the first principles from which to derive programs and on which to base critiques? Materialists cannot search inside themselves for more universal principles or better goals. Our starting point is the real struggles of peoples for a better life, the struggles against poverty and oppression. The core of our vision of the new is the negation of our most deeply felt suffering in the existing order. The most deeply felt suffering depends on who you are in the present society. The unemployed may see full employment as an ideal goal, the impoverished dream of plenty, the slave may imagine a world without work, while those who toil at alienating, undermining, meaningless jobs may seek a transformation of the labor process and demand meaningful, creative employment. The scorned yearn for dignity and equality, the harassed for safety, the colonized for independence. Those with the resources to prosper may see freedom from restraint as an ideal goal, while those who lack means may seek freedom. 4. The right to look for a job is replaced by the right to work, the right to shop, by the right to eat. Sometimes conditions deteriorate and become unacceptable, or the oppressed may want to enjoy those things which the society praises as the highest rewards in life but which are denied them by the rulers. People transform these elementary goals into political goals, from I am hungry to I want food to we want food to we have a right to eat. Or from he abuses me to he is a bad master to no one should be a master or slave to, and that includes husbands and wives. As elementary goals become political, their advocates expand their scope and generality, turning particular objectives into universal principles that have the power to move people deeply. The goals acquire implications beyond their original intent. All men who were created equal in 1776 were white, male, and propertied. But the slogan "some people are created more or less equal" would not have inspired a revolution. The different political goals of revolutionaries may clash with each other. The pursuit of happiness implies the right to exploit. Abundance for all, if understood in terms of contemporary capitalist consumption patterns, conflicts with the demand for a healthful environment. The need for large-scale planned development may conflict with the demand for local self-government. New objectives are created in the course of confronting these contradictions. Eventually the threshold may be crossed between left liberalism and radicalism when we abandon the proposition things are more or less okay but corrections are needed and replace it with the new conviction the system is basically unjust, irrational, and dangerous despite its secondary rewards. Then people will begin to look critically at all aspects of their lives and start to challenge the previously accepted systems of education, family structure, healthcare, division of labor, ways of making collective decisions, how we think and feel, kinds of cultural creation, ways of acquiring knowledge, patterns of personal relations, and industrial design. Once again, different goals may conflict, if only temporarily. Different sectors may push for different kinds of changes. Central planning can lead to bureaucratization, local autonomy could disrupt ecological rationality and increase inequality. Rationing under conditions of scarcity can protect equality, but with abundance it can encourage trade. There is no final state. The anti-communist habit of referring to a workers' paradise in quotes is wide of the mark in imagining that we envision any utopian endpoint. Therefore, although as revolutionaries we struggle for those arrangements that make different emancipating goals compatible, we cannot foresee with any real accuracy the problems that will arise or the new aspirations that people will have who grow up in a different society. Conclusion: Dialectics. Scientists, like other intellectuals, come to their work with a worldview, a set of preconceptions that provides the framework for their analysis of the world. These preconceptions enter at both an explicit and an implicit level, but even when invoked explicitly, unexamined and unexpressed assumptions underlie them. The attempt to analyze evolution as an interaction between internal genetic causes and external environmental causes makes the distinction between organism and environment explicit. Yet underlying that distinction is the unexamined and implicit principle that organism and environment are indeed separate systems with their own autonomous properties. We too have our own intellectual preconceptions. If we differ from most scientists, it is in our deliberate attempt to make these preconceptions explicit where we can. The earlier chapters in this book were written largely from a Marxist perspective. They reflect the conflict between the materialist dialectics of our conscious commitment and the mechanistic, reductionist, and positivist ideology that dominated our academic education and that pervades our intellectual environment. We have nowhere, however, attempted to define the dialectical method or set forth its principles in an explicit list. These chapters were not based on some clearly enumerated list of dialectical principles. Rather, they reflect certain habits of thought, certain forms of questioning, that we identify as dialectical. Nevertheless, it seems necessary, in order to pursue the intellectual program of this collection, to attempt some explicit discussion of this way of thinking. Formalizations of the dialectic have a way of seeming rigid and dogmatic in a way that contradicts the fluidity and historicity of the Marxist worldview. This is especially the case when it is set out as laws, by analogy with the laws of natural science. Yet most scientific laws establish quantitative relations among variables and serve as a basis for prediction. The laws of dialectics are clearly not analogous to, say, Einstein's equation. E equals mc 2. But rather are analogous to prior principles, the constancy of the speed of light in all inertial frames, and the conservation of momentum. Perhaps the principles of dialectics are analogous to Darwin's principles of variation, heritability, and selection in that they create the terms of reference from which quantifications and predictions may be derived. A second reason for our reluctance to formulate the dialectic in terms of laws is that it creates the illusion that dialectics are rules derived simply from nature. They are not. A dialectical view of dialectics would emphasize that the principles and vocabulary taken over from philosophers have been transformed and invoked polemically in opposition to, as a negation of, the prevailing ideological framework of bourgeois science, the Cartesian reductionist perspective. The value of the dialectic is as a conscious challenge to the major sources of error of the present, and our own description of dialectical principles is specifically designed to help solve the problems we work with in both our scientific and our political lives. Given the remarkable flexibility and capacity for novelty that characterize human thought, it is at least possible that any conclusion about the world could be reached by anyone, irrespective of the person's previous commitment to an ideology or worldview. Newton, who accepted the supernatural world of religious belief, nevertheless conceived of a world of uncompromising mechanical necessity. But it is not necessary to insist that construction of a particular model of nature needs a particular worldview to argue that ideology strongly predisposes us to see some things in the world and not others. It would have been very extraordinary indeed if a naturalist traveling with Columbus or Magellan around the turn of the 16th century had returned home with the same views that Darwin held when he stepped off the Beagle. Indeed, one can hardly imagine even sending a naturalist on a trip around the world in 1519. Ideas of cause and effect, subject and object, part and whole form an intellectual frame that delimits our construction of reality, although we are barely aware of its existence or, if we are, we affirm it as a self-evident reality that must constrain all thought. We do not and cannot begin at square one every time we think about the world. Knowledge is socially constructed because our minds are socially constructed and because individual thought only becomes knowledge by a process of being accepted into social currency. So dominant ideologies set the tone for the theoretical investigation of phenomena, which then becomes a reinforcing practice for the ideology itself. Inevitably some problems of understanding the world cannot be solved in the commonly accepted ideological framework. These are either considered fundamentally undecidable or discreetly ignored in the triumphant march of discovery. The growth of knowledge is then akin to the conquest of land by a medieval army. Cities are laid siege to, and most surrender, but a few hold out indefinitely. The army sweeps around these, leaving behind some of its troops, who settle down to a long and frustrating encirclement. This has certainly been the case in biology, where the extraordinary progress made in molecular studies has been the consequence of a straightforward reductionist program, while the understanding of embryonic development and of the functioning of the central nervous system have remained in a rudimentary state. Even evolutionary biology, which is widely accepted as a triumph of modern science, has swept a lot of problems under the rug of undecidability. The dominant mode of analysis of the physical and biological world and by extension the social world, as the social sciences have come into being, has been Cartesian reductionism. This Cartesian mode is characterized by four ontological commitments, which then put their stamp on the process of creating knowledge. 1. There is a natural set of units or parts of which any whole system is made. 2. These units are homogeneous within themselves, at least insofar as they affect the whole of which they are the parts. 3. The parts are ontologically prior to the whole, that is, the parts exist in isolation and come together to make wholes. The parts have intrinsic properties, which they possess in isolation and which they lend to the whole. In the simplest cases the whole is nothing but the sum of its parts, more complex cases allow for interactions of the parts to produce added properties of the whole. 4. Causes are separate from effects, causes being the properties of subjects, and effects the properties of objects. While causes may respond to information coming from the effects, there is no ambiguity about which is causing subject and which is caused object. We characterize the world described by these principles as the alienated world, the world in which parts are separated from wholes and reified as things in themselves, causes separated from effects, subjects separated from objects. It is a physical world that mirrors the structure of the alienated social world in which it was conceived. Beginning with the first glimmerings of merchant entrepreneurship in 13th century Europe, and culminating in the bourgeois revolutions of the 17th and 18th centuries, social relations have emphasized the primacy of the alienated individual as a social actor. By successive acts of enclosure, land was alienated from the peasant cultivators, who formerly were tied to it and it to them. Individuals became social atoms, colliding in the market, each with his or her special interests and properties intrinsic to their roles. No individual person, however, is confined to a single role in bourgeois society. The same people are both consumers and producers, owners and renters, bosses and bossed. Yet bourgeois social theory sees society as constructed of homogeneous interest groups. Consumers have their interest, labor its interest, capital its interest, the whole of society taking a shape determined by the action of these categories on each other. The alienated world is both ideological and real. Clearly, the claim that the social order is the natural result of the adjustments of demands and interests of competing groups is an ideological formulation meant to make the structure seem inevitable, but it also reflects the reality that has been constructed. Workers as individuals do sell their labor power in a market whose terms have been made by struggles between workers and employers generally. Consumers do have an interest in the commodities offered them that is antithetical to the interest of the producers. But these interest groups have been created by the very system of social relations of which they are said to be the basis. In like manner, the alienated physical world is not only a structure of knowledge, but a physical structure imposed on the world. Which one of a chain of intersecting causes becomes. The cause of a given effect is determined in part by social practice. For example, medical research and practice isolate particular causes of disease and treat them. The tubercle bacillus became the cause of tuberculosis, as opposed to, say, unregulated industrial capitalism, because the bacillus was made the point of medical attack on the disease. The alternative would be not a medical but a political approach to tuberculosis, and so not the business of medicine in an alienated social structure. Having identified the bacillus as the cause, a chemotherapy had to be developed to treat it, rather than, say, a social revolution. Sometimes problems are created in part by the very solutions invented to cope with them. The competition of certain weed species with crop plants is a serious problem for farmers, a problem that is now solved by wholesale application of herbicides. But not all weeds are bad for crops, and weed species compete among themselves. By using broad-spectrum herbicides, beneficial weeds, those that compete with harmful weeds, are destroyed along with the harmful weeds they displace, so the weed problem is partly created by the very operation that is supposed to cope with it. The same is true for insects, which are selected for genetic resistance to insecticides by the very insecticides used to control them. As a consequence, the greater the cure, the greater the problem. No way of thinking about the world of phenomena can provide a total description of the infinitely complex set of interacting causes of all events. It is our contention that the alienated worldview captures a particularly impoverished shadow of the actual relations among phenomena in the world, concerning itself only with the projections of multidimensional objects on fixed planes of low dimensionality. Indeed, it is an explicit objective of Cartesian reductionism to find a very small set of independent causal pathways or factors that can be used to reconstruct a large domain of phenomena. An elementary exercise in design courses is to make an object that is circular in one projection, square in a second projection, and triangular in the third. Alienated science deals with the alienated world of these projections, while a dialectical view attempts to understand the object in its full dimensionality. Of course, some objects, like spheres, are the same in all projections, so the reductionist strategy succeeds. The error of reductionism as a general point of view is that it supposes the higher dimensional object is somehow composed of its lower dimensional projections, which have ontological primacy and which exist in isolation, the natural parts of which the whole is composed. In the alienated world things are at base homogeneous. Indeed, the object of reductionist science is to find those smallest units that are internally homogeneous, the natural units of which the world is made. The history of classical chemistry and physics is the epitome of this view. In classical chemistry, microscopic objects were made of a mixture of molecules, each of which was homogeneous within itself. With the development of the atomic theory of matter, these molecules were seen to be made of mixtures of atoms of different sorts, so the molecules were then seen as internally heterogeneous. Then it appeared that the very atoms defied their name, because they too were internally heterogeneous, being composed of elementary neutrons, protons, and electrons. But even that homogeneity has disappeared, and the number of elementary particles has multiplied with each creation of a more powerful particle accelerator. Physicists believe that the present theory predicts all particles that can exist, but since that theoretical apparatus is only half a dozen years old, the cautious person may reserve judgment. In contrast, in the dialectical worldview, things are assumed from the beginning to be internally heterogeneous at every level. And this heterogeneity does not mean that the object or system is composed of fixed natural units. Rather, the correct division of the whole into parts varies, depending upon the particular aspect of the whole that is in question. In evolutionary reconstructions, the problem is to identify the anatomical, behavioral, or physiological units of evolution. Is the hand a unit in evolution, or is it the entire forelimb, or, on the contrary, is each finger or each joint of each finger the appropriate unit? The answer depends upon the way genes interact with each other to influence the development of the hand and the way in which natural selection operates. But gene interactions themselves evolve, and the nature of the force of natural selection varies from time to time and species to species, so the hand may be a unit of evolution at some times but not others. Moreover, the degree of functional integration or independence of fingers, hand, and forelimb will itself evolve. A unit of evolution may, by its very evolution, annihilate itself as a unit of future evolution. It is a matter of simple logic that parts can be parts only when there is a whole for them to be parts of. Part implies whole, and whole implies part. Yet reductionist practice ignores this relationship, isolating parts as pre-existing units of which wholes are then composed. In the dialectical world, the logical dialectical relation between part and whole is taken seriously. Part makes whole, and whole makes part. It seems clear that all bits of the physical world are in interaction with each other to some degree. Yet in practice much of that interaction is irrelevant. It may be that thou canst not stir a flower without troubling of a star, but in fact, our gardening does not have any effect on the sun, because gravitation is a weak force that falls off as the square of the distance. The growth of our flowers, on the other hand, is affected by the sun because photons travel across 80 million miles without losing their energy. The community in ecology does not lose its meaning as a unit of analysis nor its effectiveness as a level of interaction just because it is possible to connect every species in the world with every other one by some long chain of remote biotic interactions. The problem for the ecologist is not to divide up the world of organisms once and for all into communities, but to look for groups of species within which there are strong interactions and between which there are weak relations in particular circumstances. A single species may be part of two communities without thereby joining those communities into one. The owl as a predator belongs to one community, as a defecator it is part of a quite different one. The first principle of a dialectical view, then, is that a whole is a relation of heterogeneous parts that have no prior independent existence as parts. The second principle, which flows from the first, is that, in general, the properties of parts have no prior alienated existence but are acquired by being parts of a particular whole. In the alienated world, the intrinsic properties of the alienated parts confer properties on the whole, which may in addition take on new properties that are not characteristic of the parts. The whole may be more than the sum of its parts. But the ancient debate on emergence, whether indeed wholes may have properties not intrinsic to the parts, is beside the point. The fact is that the parts have properties that are characteristic of them only as they are parts of wholes. The properties come into existence in the interaction that makes the whole. A person cannot fly by flapping her arms, no matter how much she tries, nor can a group of people fly by all flapping their arms simultaneously. But people do fly, as a consequence of the social organization that has created airplanes, pilots, and fuel. It is not society that flies, however, but individuals in society, who have acquired a property they do not have outside society. The limitations of individual physical beings are negated by social interactions. The whole, thus, is not simply the object of interaction of the parts but is the subject of action on the parts. The dialectical emphasis on wholes is shared by other schools of thought that rebel against the fragmentation of life under capitalism, the narrowness of specialization, the reductionism of medical and agricultural theory. Holistic health movements stress the inseparability of psychological and physiological processes, the relevance to health of nutrition, exercise, and emotions, and the complex interactions of different nutrients. The ecology movement emphasizes the unity of nature, which includes us. We agree with these criticisms of current practices, but we differ from these groups in two major ways. Most of the alternative health movements focus on the individual, without integrating that individual into social processes either in analysis or program. And their organizing principle is harmony, balance, or oneness with nature. In the dialectical approach, the wholes are not inherently balanced or harmonious, their identity is not fixed. They are the loci of internal opposing processes, and the outcome of these oppositions is balanced only temporarily. A third dialectical principle, then, is that the interpenetration of parts and wholes is a consequence of the interchangeability of subject and object, of cause and effect. In the alienated world, objects are the passive, caused elements of other active, causal subjects. In evolutionary theory, organisms are usually seen as the objects of evolution. Through natural selection, autonomous changes in the environment cause adaptive alterations in the passive organism. As we argued in Chapter 3, however, the actual situation is quite different. Organisms are both the subjects and the objects of evolution. They both make and are made by the environment and are thus actors in their own evolutionary history. The separation between cause and effect, subject and object in the alienated world has a direct political consequence, summed up in the expression, "You can't fight City Hall." The external world sets the conditions to which we must adapt ourselves socially, just as environment forces the species to adapt. Biologically, the ideology of being realistic manifests itself in theories of human psychic development, such as Piaget's claim that equilibrium is attained when the adolescent understands that the proper function of reflection is not to contradict but to predict and interpret experience. To this we counterpose Marx's 11th thesis on Feuerbach: the philosophers have only interpreted the world in various ways. The point, however, is to change it. Two other schools of thought also recognize the heterogeneity of the world, but in different ways. Liberals are fond of urging that situations are not all black or white, that each course of action has its advantages and disadvantages, costs and benefits. Their solution is to see the world as shades of gray, to weigh costs and benefits on some scale that comes with a single resultant net profit or loss, or to insist that, given two extremes, the truth lies somewhere in between. In each case the differences are quantitative, and contradictions are resolved by compromise. The Taoist tradition in China shares with dialectics the emphasis on wholeness, the whole being maintained by the balance of opposites, such as yin and yang. Although balanced, yin and yang do not lose their identities in some puddled intermediate. Chinese medicine recognizes excess of yin and deficiency of yang as distinct pathologies. However, balance is seen as the natural, desirable state, and the goal of intervention is to restore balance. Therefore, Taoist holism is a doctrine of harmony rather than development. Because elements recreate each other by interacting and are recreated by the wholes of which they are parts, change is a characteristic of all systems and all aspects of all systems. That is a fourth dialectical principle. In bourgeois thought, change occupies an apparently contradictory position that follows from the history of the bourgeois revolution. The triumph of capitalism was accompanied by an exuberant, arrogant, and liberating iconoclasm. What was, need not be, ideas do not have tenure. Change, in Herbert Spencer's words, was a beneficent necessity. People could change their status, success came by innovation. But with the eventual dominance of bourgeois institutions, bourgeois society itself was seen as the culmination of social development, the final release of humanity from the fetters of artificial feudal restraints into the natural state of economic man. From that point on, change was to be restricted within narrow boundaries, making technical innovations, improving laws, balancing, adjusting, compromising, expanding, or declining. Legitimation of bourgeois society meant denial of the need for fundamental change, or even the possibility of it. Stability, balance, equilibrium, and continuity became positive virtues in society and therefore also the objects of intellectual interest. Change was increasingly seen as superficial, as only appearance, masking some underlying stasis. Even in evolutionary theory, the quintessential study of change, we saw the deep denial of change. Evolution was merely the recombination of unchangeable units of idioplasm. Species endlessly played musical niches. The seemingly sweeping changes through geological time were only prolongations of the microevolution observed in the laboratory, and all of it was merely a sequence of manifestations of the selfish gene in different contexts of selfishness. In choosing among alternative possibilities, priority has been given to the null hypothesis that no change has occurred. Until recently, models of dynamics focused on conditions for stable equilibrium. This diverted attention from the many varied ways in which systems could be unstable. Since stability requires the simultaneous satisfaction of a large number of different criteria, systems can be stable in only one way, but they can be unstable in many ways. Only recently has attention shifted to the richness of non-equilibrium processes. In bourgeois thought, change is often seen as the regular unfolding of what is already there. It is described by listing the sequence of results of change, the necessary stages of social or individual development. This shift from process to product also contaminates socialist thought when the dynamic view of history as a history of class struggle is replaced by the grand march of stages, from primitive communism through slavery, feudalism, capitalism, socialism, and on into the glorious sunset. Thus, even where deep change cannot be ignored, it is acknowledged reluctantly and denied with the world-weary aphorism, the more things change, the more they are the same. In the alienated world there are constants and variables, those things that are fixed and those that change as a consequence of fixed laws operating with fixed parameter values. In the dialectical world, since all elements are changing, constants and variables are not distinct classes of values. The time scales of change of different elements may be very different, so that one element has the appearance of being a fixed parameter for the other. For example, the formulations of population genetics take the environment as constant for long periods in order to calculate the trajectories of gene frequencies and their equilibria. But as the environment changes slowly, the equilibria themselves may be changing more slowly. Reciprocally, population ecology assumes that species are not changing genetically in order to calculate the demographic trajectories of age classes, although the equilibrium will slowly change as the genotypic composition of populations changes. Finally, community ecology takes both the demographic and genetic properties of species as constants in order to predict the equilibrium of species numbers in a community, although these may slowly change as genetic changes occur in an evolutionary time scale. Unfortunately, the time scales of these processes are often not different, so the assumption that one process can be held constant while the other changes is in error. Fisher's derivation of the Malthusian parameter for following the genetic changes in a population made the error of supposing that age distribution would remain constant during the selective process. It was not until 40 years after the publication of the genetical theory of natural selection that the demographic and genetic processes of change were finally treated simultaneously. Another manifestation of the same error is to treat the fitnesses of genotypes in populations as independent of the frequencies of those genotypes, relegating so-called frequency-dependent selection to the category of a special and unimportant case. Yet most selective processes are necessarily frequency-dependent, especially if they involve competitive or cooperative interactions. There are, of course, physical constants like the mass of the electron, the speed of light, and Planck's constant, which we regard as fixed and insensitive to the systems of which they are a part. Yet their constancy is not a law derived from yet other, more primitive principles, but an assumption. We do not, in fact, know that the mass of the electron has been the same since the beginning of matter, nor, even if it has been so constant, that its value is not an accident of the history of matter. Whether such values are indeed changing and, if they are, at what rate, is a contingent question, not to be answered from principle. The difference between the reductionist and the dialectician is that the former regards constancy as the normal condition, to be proven otherwise, while the latter expects change but accepts apparent constancy. Not only do parameters change in response to changes in the system of which they are a part, but the laws of transformation themselves change. In the alienated worldview, entities may change as a consequence of developmental forces, but the forces themselves remain constant or change autonomously as a result of intrinsic developmental properties. In fact, however, the entities that are the objects of laws of transformation become subjects that change these laws. Systems destroy the conditions that brought them about in the first place and create the possibilities of new transformations that did not previously exist. The law that all life arises from life was enacted only about 1 billion years ago. Life originally arose from inanimate matter, but that origination made its continued occurrence impossible, because living organisms consume the complex organic molecules needed to recreate life de novo. Moreover, the reducing atmosphere that existed before the beginning of life has been converted, by living organisms themselves, to one that is rich in reactive oxygen. The change that is characteristic of systems arises from both internal and external relations. The internal heterogeneity of a system may produce a dynamic instability that results in internal development. At the same time, the system as a whole is developing in relation to the external world, which influences and is influenced by that development. Thus, internal and external forces affect each other and the object, which is the nexus of those forces. Classical biology, which is to say alienated biology, has always separated the internal and external forces operating in organisms, holding one constant while considering the other. Thus embryology has always emphasized the development of an organism as a consequence of internal forces, irrespective of the environment. At most, the environment is regarded as a signal that sets the interior developmental forces going. Developmental biology is consumed with the problem of how the genes determine the organism. On the other hand, evolutionary biology, at least as practiced in Anglo-Saxon countries, is obsessed with the problem of the organism's adaptation to the external world and assumes without question that any favorable alteration in the organism is available by mutation. There is abundant evidence, however, that the ontogeny of an individual is a function of both its genes and the environment in which it develops. Moreover, it is certainly the case that no tetrapod has ever, no matter what selective forces are involved, succeeded in acquiring wings without giving up a pair of limbs. The separation of the external and internal forces of development is a characteristic of alienated biology that must be overcome if the problems of either embryology or evolution are to be solved. The assertion that all objects are internally heterogeneous leads us in two directions. The first is the claim that there is no basement. This is not an a priori imposition on nature but a generalization from experience. All previously proposed undecomposable basic units have so far turned out to be decomposable, and the decomposition has opened up new domains for investigation and practice. Therefore, the proposition that there is no basement has proven to be a better guide to understanding the world than its opposite. Furthermore, the assertion that there is no basement argues for the legitimacy of investigating each level of organization without having to search for fundamental units. A second consequence of the heterogeneity of all objects is that it directs us toward the explanation of change in terms of the opposing processes united within that object. Heterogeneity is not merely diversity, the parts or processes confront each other as opposites, conditional on the whole of which they are parts. For example, in the predator-prey system of lemmings and owls, the two species are opposite poles of the process, predation simultaneously determining the death rate of lemmings and the birth rate of owls. It is not that lemmings are the opposite of owls in some ontological sense, or that lemmings imply owls or couldn't exist without owls. But within the context of this particular ecosystem, their interaction helps to drive the population dynamics, which shows a spectacular fluctuation of numbers. What characterizes the dialectical world, in all its aspects, as we have described it, is that it is constantly in motion. Constants become variables, causes become effects, and systems develop, destroying the conditions that gave rise to them. Even elements that appear to be stable are in a dynamic equilibrium of forces that can suddenly become unbalanced, as when a dull gray lump of metal of a critical size becomes a fireball brighter than 1,000 suns. Yet the motion is not unconstrained and uniform. Organisms develop and differentiate, then die and disintegrate. Species arise but inevitably become extinct. Even in the simple physical world we know of no uniform motion. Even the Earth rotating on its axis has slowed down in geologic time. The development of systems through time, then, seems to be the consequence of opposing forces and opposing motions. This appearance of opposing forces has given rise to the most debated and difficult, yet the most central, concept in dialectical thought, the principle of contradiction. For some, contradiction is an epistemic principle only. It describes how we come to understand the world by a history of antithetical theories that, in contradiction to each other and in contradiction to observed phenomena, lead to a new view of nature. Kuhn's theory of scientific revolution has some of this flavor of continual contradiction and resolution, giving way to new contradiction. For others, contradiction is not only epistemic but political as well, the contradiction between classes being the motive power of history. Thus contradiction becomes an ontological property at least of human social existence. For us, contradiction is not only epistemic and political, but ontological in the broadest sense. Contradictions between forces are everywhere in nature, not only in human social institutions. This tradition of dialectics goes back to Engels, who wrote, in Dialectics of Nature, that to me there could be no question of building the laws of dialectics of nature, but of discovering them in it and evolving them from it. Engels's understanding of the physical world was, of course, a 19th-century understanding, and much of what he wrote about it seems quaint. Moreover, dialecticians have repeatedly attempted to make the identification of contradictions in nature a central feature of science, as if all scientific problems are solved when the contradictions have been revealed. Yet neither Engels' factual errors nor the rigidity of idealist dialectics changes the fact that opposing forces lie at the base of the evolving physical and biological world. Things change because of the actions of opposing forces on them, and things are the way they are because of the temporary balance of opposing forces. In the early days of biology an inertial view prevailed. Nerve cells were at rest until stimulated by other nerve cells and ultimately by sensory excitation. Genes acted if the raw materials for their activity were present, otherwise they were quiescent. Gene frequencies in a population remain static in the absence of selection, mutation, random drift, or immigration. Nature was at equilibrium unless perturbed. Later it was recognized that nerve impulses act both to excite and to inhibit the firing of other nerves, so the state of a system depends on the network of opposing stimuli, and that network can generate spontaneous activity. Gene action is regulated by repressors, repressors of the repressors, and all sorts of active feedbacks in the cell. There are no genetic loci immune to mutation and random drift, and no populations are free of selection. The dialectical view insists that persistence and equilibrium are not the natural state of things but require explanation, which must be sought in the actions of the opposing forces. The conditions under which the opposing forces balance and the system as a whole is in stable equilibrium are quite special. They require the simultaneous satisfaction of as many mathematical relations as there are variables in the system, usually expressed as inequalities among the parameters of that system. If these parameters remain within the prescribed limits, then external events producing small shifts among the variables will be erased by the self-regulating processes of stable systems. Thus in humans the level of blood sugar is regulated by the rate at which sugar is released into the blood by the digestion of carbohydrates, the rate at which stored glycogen, fat, or protein is converted into sugar, and the rate at which sugar is removed and utilized. Normally, if the blood sugar level rises, then the rate of utilization is increased by release of more insulin from the pancreas. If the level of blood sugar falls, more sugar is released into the blood, or the person gets hungry and eats some source of sugar. The result is that the blood sugar level is kept not constant but within tolerable limits. So far we are dealing with the familiar patterns of homeostasis, the negative feedback that characterizes all self-regulation. However, the pancreas might respond weakly to a high sugar level, which could result in diabetic coma. Or the blood sugar level may fall so low that the person is incapable of eating. The opposing forces are seen as contradictory in the sense that each taken separately would have opposite effects, and their joint action may be different from the result of either acting alone. So far, the object may seem to be the passive victim of these opposing forces. However, the principle that all things are internally heterogeneous directs our attention to the opposing processes at work within the object. These opposing processes can now be seen as part of the self-regulation and development of the object. The relations among the stabilizing and destabilizing processes become themselves the objects of interest, and the original object is seen as a system, a network of positive and negative feedbacks. The negative feedbacks are the more familiar ones. If blood pressure rises, sensors in the kidney detect the rise and set in motion the processes which reduce blood pressure. If more of a commodity is produced than can be sold, prices fall, and the surplus is sold cheaply while production is cut back. If there is a shortage, prices rise, and that stimulates production. Or if a baby cries, this tells the responsible adult that something is wrong, and he or she initiates action to remove the cause of discomfort and stop the crying. In each case, a particular state of the system, high blood pressure, overproduction, crying, is self-negating in that within the context of the system an increase in something initiates processes that leads to its decrease. But systems also contain positive feedback. High blood pressure may damage the pressure measuring structures, so that blood pressure is underestimated and the homeostatic mechanisms themselves increase the pressure. Overproduction may lead to cutbacks in employment, which reduce purchasing power and therefore increase the relative surplus. The crying of the baby may evoke anger, and the abuse of the child can then result in more crying. Real systems include pathways for both positive and negative feedback. Negative feedbacks are a prerequisite for stability. The persistence of a system requires self-negating pathways. But negative feedback is no guarantee of stability and under some circumstances can throw the system into oscillation. If there is a preponderance of positive feedback, or if the indirect negative feedbacks by way of intervening variables are strong enough, the system will be unstable. That is, its own condition is sufficient cause of its negation. Thus systems are either self-negating or depend for their persistence on self-negating processes. We see contradiction first of all as self-negation. From this perspective it is not too different from logical contradiction. Informal logic process is usually replaced by static set structural relations, and the dynamic of A leads to B is replaced by A implies B. But all real reasoning takes place in time, and the classical logical paradoxes can be seen as A leads to not A leads to A, and so on. For instance, consider Russell's paradoxical barber who shaves any and all men who do not shave themselves. If we assume that the barber shaves himself, then he belongs to the set of those he does not shave. Therefore, he is eligible to be a shaver by himself, and so we go round and round, as each affirmation is in turn negated. Material and logical contradiction share the property of being self-negating processes. The stability or persistence of a system depends on a particular balance of positive and negative feedbacks, on parameters governing the rates of processes falling within certain limits. But these parameters, although treated in mathematical models as constants, are real-world objects that are themselves subject to change. Eventually some of these parameters will cross the threshold beyond which the original system can no longer persist as it was. The equilibrium is broken. The system may go into wider and wider fluctuations and break down, or the parts themselves, which have meaning only within a particular whole, may lose their identity as parts and give rise to a qualitatively new system. Further, the changes in the parameters may be a consequence of the stable behavior of the system that they condition in the first place. As a result of the cycle of over and underproduction, businesses fail, firms merge and expand, a permanent body of unemployed people is created, and political struggles culminate in the replacement of the capitalist system with its whole dynamic. If predator and prey are in demographic balance, this may hide the prey's evolution toward better predator avoidance, thus eventually resulting in the extinction of the predator, or the predator's efficiency at hunting may evolve beyond the threshold compatible with the survival of the prey, and both become extinct. The dialectical model suggests that no system is really completely static, although some aspects of a system may be in equilibrium. The quantitative changes that take place within the apparent stability cross thresholds beyond which the qualitative behavior is transformed. All systems are in the long run self-negating, while their short-term persistence depends on internal self-negating states. The dialectical viewpoint sees dynamical stability as a rather special situation that must be accounted for. Systems of any complexity, the central nervous system, the national and world capitalist economies, ecosystems, the physiological networks of organisms are more likely to be dynamically unstable. Even systems designed explicitly to be stable, such as nuclear power plants, have shown a remarkable propensity to behave in unplanned ways. The important point here is that complex systems show spontaneous activity. Each of these systems responds to events from outside, but it is not necessary to look to external sources for the causes of movement. The capitalist business cycle does not depend on sunspots. Political unrest is not explained by outside agitators. Changing abundance of species is not evidence of human impact on the environment. And it is becoming increasingly apparent that the prevention of change in wildlife management, environmental protection, or society is, in the long run, an impossible goal. Self-negation is not simply an abstract possibility derived from arguments about the universality of change. We observe it regularly in nature and society. Monopoly arises not as a result of the thwarting of free enterprise but as a consequence of its success, hence the futility of antitrust legislation. The freeing of serfs from feudal ties to the land also meant the possibility of their eviction from the land. Freedom of the press has increasingly meant the freedom of the owners of the press to control information. The self-negating processes of capitalism are often expressed as ironic commentaries, as the realization of ideal goals turns out to thwart their original intent. Sometimes this self-negation is the consequence of quantitative changes that cross a threshold. For instance, at one time the Polish government established a policy of subsidizing the price of bread at a fixed level in order to guarantee the basic food supply. As inflation developed, the gap between the subsidized price of bread and the prices of other goods widened until one morning Warsaw was without bread. Farmers had discovered that it was cheaper to buy bread to feed their livestock than to grow feed. The very mechanisms designed to guarantee the urban bread supply were turned into their opposite. A second aspect of contradiction is the interpenetration of seemingly mutually exclusive categories. A necessary step in theoretical work is to make distinctions. But whenever we divide something into mutually exclusive and jointly all-encompassing categories, it turns out on further examination that these opposites interpenetrate. In Chapter 3 we examine the interpenetration of organism and environment. Here we note briefly several more examples. At first glance, deterministic and random processes seem to exemplify mutually exclusive categories. Many trees have been sacrificed to the cause of printing debates about whether the world, or species aggregates, or evolution, is deterministic or random. In the first place, however, completely deterministic processes can generate apparently random processes. In fact, the random numbers used for computer stimulation of random process are generated by deterministic processes. Recently, mathematicians have become interested in so-called chaotic motion, which leads neither to equilibrium nor to regular period motion but rather to patterns that look random. In systems of high complexity, the likelihood of stable equilibrium may be quite small unless the system was explicitly designed for stability. The more common outcome is chaotic motion or periodic motion with periods so long as never to repeat during even long intervals of observations. thus also appearing as random. Second, random processes may have deterministic results. This is the basis for predictions about the number of traffic accidents or for actuarial tables. A random process results in some frequency distribution of outcomes. The frequency distribution itself is determined by some parameters, and changes in these parameters have completely determined effects on the distribution. Thus the distribution as an object of study is deterministic even though it is the product of random events. Third, near thresholds separating domains of very different qualitative behaviors, a small displacement can have a big effect. If these small displacements arise from lower levels of organization, they will be unpredictable from the perspective of the higher level. And in general the intrusion of events from one level to another appears as randomness. Finally, the interaction of random and deterministic processes gives results in evolution that are different from the consequence of either type of process acting alone. In Sewell-Wright's model, selection alone would lead all local populations to the same gene frequencies, so no selection among populations would be possible. The random drift that arises from small numbers within each population would result in the non-adaptive fixation of genes. The joint effect, however, is to allow variation among local populations, which provides the variability for new cycles of selection in different directions. People have long known that random search can be an important part of adaptive processes, the trial and error procedure leading to desired results by unexpected paths. Similarly, the dichotomy between equilibrium and non-equilibrium systems is not absolute. When ecologists realized that nature changes, there was a rush to abandon equilibrium analysis as unrealistic. However, it is not at all obvious that a changing system is not also in equilibrium. The proportions of various ionic forms of phosphorus in a lake reach equilibrium in seconds, even though the total amount of phosphorus may change. Algae populations may equilibrate with the mineral level, which itself changes, changing the algae. Phenomena that are very much slower than those of interest can be treated provisionally as constant, while those that are very much faster can be treated as if already at equilibrium. In the long run it is important to see equilibrium as a form of motion rather than as its polar opposite. Our conclusion, borne out by the history of our science, is that such dichotomies are both necessary and misleading and that there is no non-trivial and complete decomposition of phenomena into mutually exclusive categories. Contradiction also means the coexistence of opposing principles which, taken together, have very different implications or consequences than they would have if taken separately. Commodities embody the contradiction between use value and exchange value. If objects were produced simply because they met human needs, we would expect the more useful things to be produced before less useful things, and we would expect objects and methods of production to be designed to minimize any harm or danger and maximize durability or reparability. The amounts produced would correspond to the levels of need. Any decline in need would allow either more leisure or the production of other objects. If objects had no use value at all, of course, they couldn't be sold. Use value makes exchange value possible. But the prospect of exchange value leads to results that often contradict the human needs that called forth the commodities in the first place. Commodities will be produced, for example, only for those who can afford them, and priority will be given to the production of those commodities with the highest profit margins. Productive innovations which make commodities easier and cheaper to make may create unemployment or ill health for workers and consumers. Thus the process of supplying human needs by the creation of commodities whose exchange value is paramount actually creates new hardship. A single proposition may have opposing implications. Consider, for example, the statement that more than half the population of Puerto Rico receives food stamps. This serves as a basis both for the party in power to justify the continuation of American rule and for the opposition to criticize that rule. On the one hand, 86 years after the United States occupied Puerto Rico, the island's economy is more dependent and less able to support its population than before. Some $5 billion are extracted annually by United States businesses in the form of profits and interest, preventing Puerto Rico from accumulating what it needs for autonomous development. On the other hand, food stamps are not available in Honduras and the Dominican Republic. For the recipient of food stamps, the direct experience is of American benevolence. It requires an intellectual detour to perceive also that the necessity for food stamps is a result of being absorbed into the American economy, that the United States is the cause of the problem that it partly ameliorates. Much of the political conflict around the status of Puerto Rico derives from the contradictory implications of the same fact. The principles of materialist dialectics that we attempt to apply to scientific activity have implications for research strategy and educational policy as well as methodological prescriptions. Historicity. Each problem has its history in two senses, the history of the object of study and the history of scientific thinking about the problem, a history dictated not by nature but by the ways in which our societies act on and think about nature. Once we recognize that state of the art as a social product, we are freer to look critically at the agenda of our science, its conceptual framework, and accepted methodologies, and to make conscious research choices. The history of our science must include also its philosophical orientation, which is usually only implicit in the practice of scientists and wears the disguise of common sense or scientific method. It is sure to be pointed out that the dialectical approach is no less contingent historically and socially than the viewpoints we criticize, and that the dialectic must itself be analyzed dialectically. This is no embarrassment, rather, it is a necessary awareness for self-criticism. The preoccupation with process and change comes in part from our commitment to change society. An alertness to the fallacies of gradualism derives from a challenge to liberalism. An insistence on seeing things as integrated wholes reflects a belief that much of the suffering, waste, and destruction in the world today comes from the operation of patriarchal capitalism as a world system penetrating all corners of our lives rather than from a list of separable and isolatable defects. And the emphasis on the social interpretation of science comes from a political commitment to struggle for an alternative way of relating to nature and knowledge that is congruent with an alternative way of organizing society. One practical consequence of this viewpoint is that the study of the history, sociology, and philosophy of science is a necessary part of science education. Universal interconnection. As against the alienated worldview that objects are isolated until proven otherwise, for us the simplest assumption is that things are connected. The ignoring of interconnections, especially across disciplinary boundaries, has been the main source of error and even disaster in complex fields of applied biology such as public health, agriculture, environmental protection, and resource management, and the cause of the stagnation of theory in these areas. Therefore we urge that an early stage of any investigation should be to trace out the indirect, speculative, and even far-fetched connections among phenomena of interest and to justify any ignored connections. Heterogeneity. The internal heterogeneity of all things and all populations of things is the complementary perspective to universal connections. Different things combine into greater, heterogeneous wholes. This perspective leads us to focus on quantitative and qualitative variability as objects of interest and sources of explanation. Then certain problems become especially appealing, such as the organization of phenotypic variability in plants and animals, the differentiation of classes in society, the recognition that plants which bear the same species name can be quite different to the herbivores that eat them, or that the same species may have different ecological significance in different places. When faced with an ensemble of things of any sort, we are suspicious of any apparent homogeneity. Interpenetration of opposites. The more we see distinctions in nature, and the more we subdivide and set up disjunct classes, the greater the danger of reifying these differences. Therefore, complementary to any process of subdividing is the hypothesis that there is no non-trivial and complete subdivision, that opposites interpenetrate and that this interpenetration is often critical to the behavior of the system. Integrative levels. As against the reductionist view, which sees wholes as reducible to collections of fundamental parts, we see the various levels of organization as partly autonomous and reciprocally interacting. We must reject the molecular euphoria that has led many universities to shift biology to the study of the smallest units, dismissing population, organismic, evolutionary, and ecological studies as forms of stamp collecting and allowing museum collections to be neglected. But once the legitimacy of these studies is recognized, we also urge the study of the vertical relations among levels, which operate in both directions. We do not know whether or not these elements of a research and educational program will in fact result in solutions to long-standing problems of biology. Dialectical philosophers have thus far only explained science. The problem, however, is to change it.